Welcome to part 2 of the blind 75 questions. In this part, we are going to cover all the rest of the videos, and if you haven't checked it out, check out the first part right here. So without any further delay, let's just get started with all the questions. Hello friends, we are not employed by FAANG company, so let's not stop lead coding till we get there. Today we are going to do set matrix zeros problem, and this problem has been asked by some of my dream companies. So companies are like Microsoft, Amazon, Facebook, Apple, Bloomberg, Adobe, and also sometime in the past there have been Google and Goldman Sachs and eBay. They all have asked this problem, and that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and it is a very well liked problem. Basically we are given an m by n integer matrix, and we are told that at any point if we identify that there exists an element that is 0, then we need to set that entire row and entire column as 0. And we are also told that we need to do it in place. So let's see it with an example. So over here in the example, we are given a matrix like this in the input, and we can see that this is the element that is 0. So because this element is 0, we will have to convert this whole row and this whole column and set it up to zeros, and we need to return an answer like this one. Same goes with this second example, that we are given a matrix like this where we are given two zeros at these two locations, and because there are two zeros, we will convert this entire row and this entire column to 0 because of this particular 0, and we will convert this entire row and again this entire column to 0 because of this particular node. So this row is common, so anyways we will just convert it to zeros, and this would be the final answer we need to return. So suppose this is the example that we are given, and let's see that what could be the most basic intuitive approach that comes to our mind. Well, first thing that comes to our mind is that we can actually start iterating over whatever this given input is, and the moment we encounter a value 0, we can just convert that column and that row where the 0 belongs to and set it up all to all the zeros. And let me show you that why it won't work. So first of all, we'll start iterating over here. We cross this node and this node. We don't find any zeros, so we are good so far. Now at this point, we identify that there exists a 0 over here, which means that for this particular column and this particular row, we will have to convert it to 0. So let's just do that. So if we do that, what we will basically do is we will remove all of these entries, and now we will convert these entries to zeros, which means that this is 0, this is 0, and this will all become 0. Now the problem will happen that after iterating this element, the moment we reach to this particular node, we will again have to convert all of these values to zeros as well. But remember that should not have been done. Why? Because originally the value over here was actually 1, which means that this particular this particular column does not need it to be converted to 0 because of this particular node. So that is the problem over here. Let's see that what could be the solution. So let me quickly draw back this to its original form. One thing we can do is we can actually create a copy of this one, and in that particular copy we can actually start making the change whenever we find a 0 in this particular matrix, so that we do not end up changing the elements before they are being visited. So let me quickly create a copy of this particular node. Okay, so now we have created a copy. Again, we'll start iterating over all these elements. We won't do anything over here. We identify that this is a 0 element. The moment we identify that this is a 0 element, we will actually make changes to this particular copied element. So now we will update the elements in this particular fashion. So all of these would be converted to 0. Now again we start iterating over this one. So this is 1, this is 1, so we are good. This is also 1, so we are good. Now this is again a 0. So because this is a 0, we will again update this row and this this column and this row in the copied node. So let me quickly make those updates, and this will be the solution. So in the end, we can actually return this copied solution where there is only one entry over here and all the other elements are 0. So this solution would work, but the issue is that we are actually using a big O of m cross n space over here. So let's try to see that can we do some improvement rather than using this additional space. Okay, so in the previous approach we used a new matrix to keep track of all the elements where the rows and columns, the entire things needed to be turned out to 0. But this is actually not necessary. Remember that at any point we identify that inside the given matrix, if there exists a 0, all we need to do is we need to convert that entire column and row, set it up to zeros, which will happen in both of these cases. So because at any point we identify a 0, the change applied to entire matrix for that particular row and column, why do we use the entire additional matrix to store all the values? This is useless. And better approach is that we can actually create another set where we take care of all the row positions and all the column positions, and all we need to care is that at any point if we identify a 0 at any moment, we simply need to enter that entry in those particular row and column positions and then convert those row and column position to 0. Let me quickly show you how we are going to do this. So over here we will start iterating all the nodes, and we identify that these particular nodes 1, 2 and 3, these nodes, they are not 0, so we are okay with this one. But this is a 0, so because we identify that there exists a 0 node, we will quickly note this position to this row and column entries. So we will add an entry over here called 0, and we will also add an entry over here called 0, right? We are good so far. Now again we will keep iterating over this given input in the similar fashion. So these two are also not 0 and this is also not 0, so we are good so far. Next we are going to do is that because this entry is 0, again we will record those positions inside this additional row and column set that we have created. And now this last entry is also not 0, which means we don't care about anything. And at the end all we need to do is we need to iterate over this additional created sets and see that at whatever position we encounter the 0 value, for that particular row we will convert it to 0, and that particular column we will convert it to 0. So first of all we will visit this hash set of rows, and we identify that okay, first one is 0. So because first one is 0, all of these entries needed to be converted to 0, so we will convert these entries to 0. So we are good so far. Again we identify that second is also 0, so again we will repeat the same thing, and we will get rid of all of these ones and we will convert them to zeros as well. Now this last one is not 1, so we are good, and we will not touch this particular column. Now we will do the same thing for this one. So this is because this is 0, we will convert all of them to 0, so this becomes 0, and this one is also 0, so we will convert all of them, and this last cell also becomes 0. And in the end we can just simply return this newly created matrix. So this is a much bigger improvement than that in the previous one we were actually storing an additional entire matrix where the space complexity is big O of m cross n. So over here the space complexity is actually improved, and we are only using big O of m plus n. Why plus n? Because suppose the number of rows are m and number of columns are n, so we are still creating this two additional hash sets with those particular element values. The question is, can we actually do something better and even not using this m plus n space, and can we actually use the space complexity to be big O of 1? And yes, there is a solution that achieves this in big O of 1 as well. So let me quickly show you how. Okay, so previously we were actually using an additional data structure like this one to keep track of all the rows where we need to change the value to zeros. So over here, suppose we identify that there exists a 0 over here, we would update that value in this particular place, and later we would know that hey, we need to convert all these values to zeros. And we were also using another data structure to keep track of number of columns that needs to be converted to 0 in the same manner. That over here we identify that this is a 0, we will update an entry over here, and we will mark this point as 0, and later we would update all of these nodes to zeros. But rather than using this separate nodes, what we can do is we can get rid of them, and we can do the same thing by using this first row as an alternative for this original additional data structure, and also we can use this first column as an alternative for that original column data structure. And basically we will do the same concept, but we won't be using any extra space anywhere, and this is a wonderful approach. Now there will be one problem with this one, and the problem would be that over here we would be using this particular row to keep track of all the columns where the value needs to be converted to 0, and same way we will have to use this particular column to keep track of all the nodes where the rows needs to be updated. The problem is that this particular position is actually a point of conflict where there exist two intersecting nodes. So what we will do is, as a solution, we would actually create an additional node, and we will use these two nodes. So these three nodes would be working in combination, and for the first column we will need to do is just use this entire first row to keep track of all the columns that needs to be updated. And let me show you that how we are going to do the things. Okay, so first of all, we will iterate over this matrix and we identify that, okay, this value is 1, so we don't care. This value is also 1, so we don't care. Now this value is 0. So because this value is 0, we will have to make change to this particular row and this particular column. But this is at correct position, this 0 for this row. So we only have to update it over here. So we will add an entry 0 over here, right? Now next thing we will do is we will keep iterating over this matrix. So we'll we'll check these three values and all of them are 1, so we are good. This is also 1, so we are good. Now this value is 0. So because this value is 0, we will have to update over here and also over here. So we will do that. So we will convert this value and convert it to 0. We will also convert this value and change it to 0. And at the end we will just iterate over this element, and this element is already 1, so we don't have to do anything. Now this is the matrix we have. All we will have to do is we'll have to iterate over this and these 6 nodes, and at any position we identify the 0, we will convert that row or that column and change it to zeros. So first of all, we will start iterating over this first row, and this is 1, so we are good. But this is 0, so because this is 0, we will have to convert all of these to 0. So let's do that. So this value would be turned to 0, and we are good. Now again we come at this position, this is also 0, so all of these values needs to be converted to 0. So we will flip all of those values to zeros as well. Okay, now we are done iterating over this first row. Now we will iterate over this first column. So for the first column we identify that, okay, this particular position is 0. So because this is 0, we will update this entire row as zeros. So let's do that. So we will get rid of this first value and we will change it to 0. Now we will iterate to this next node. So this is 1. So because this is 1, we will not touch this row, so we don't have to do anything. And because this is 0, so because this is 0, we will have to convert this entire row to zeros. But since these two nodes have already been converted to 0, we don't have to do anything, and this would be our final solution. So if we write the answer, we can actually write an answer like this one. This would be our final answer, and we can actually return this as the answer, and this solution works perfectly fine. Let's see the time and space complexity in this case. So the time complexity is actually going to be big O of m cross n. Why? Because we will have to iterate over this entire matrix, and that takes m cross n time. In terms of space complexity, we already know that we are only using this additional node. Apart from that, we are not using any additional space. So the space complexity is actually constant space, and this is the final solution. This solution is very good, and let's see the coding. First of all, we will create an additional variable, and we will create a Boolean variable, and we will just name it as first column. We will initialize the value as false. And now we'll have to iterate over the matrix, so we'll need to know the length and height of the matrix. So let's initialize two variables to store the height of row and column of the matrix. Now we'll start iterating over the matrix, and we'll start updating the value inside the first row and first column. So we will check that if inside the given matrix for the first row, if there is any element where the value is actually 0, then we will convert that and we will update the value of the first call variable. Okay, once that is done, we will also have to iterate over all the columns. So we will create another loop inside the loop. And now we simply have to check that whether at any position we are encountering any value that is 0. If there is any value that is 0, we will have to update the corresponding I and jth position inside the first row and column subsequently. So once this loop ends, all the values should have been stored inside the first row and first column. So all we will have to do is iterate over the first row and first column, and we will update the subsequent rows and columns. So we will check that if at any position the corresponding value for the I and jth position, if that is 0 inside the first row, we will have to update the element of the this particular node inside the matrix to 0 as well. And once this loop ends, we would have taken care of all the elements inside the given matrix, but we notice that we are running this loop from I equal to 1 and j equal to 1, which means that we are not taking care of first row and first column. So we'll have to take care of first row and first column. Now remember, in order for us to take care of the first row, we will have to check the very first element, which is this this particular element inside the given matrix. So we will do that. So we will check that if matrix at 0 0 position, if that is 0, we will have to update all the values inside the first row. And once that is done, we will also have to check for the first column. So for that, we actually have a variable first column, and if the first column variable, if that is true, then we will have to update the first column to 0. And after this ends, I think we should have taken care of all the nodes. So let's try to run this code. Okay, seems like a compilation error. Okay, seems like our solution is working. Let's try to submit this code. Our submission did not work for this one. Oh, we'll have to start from j equal to 1 inside this first column. So let's try to run the code again. Let's try to submit it again. Okay, seems like our solution is working, and it's actually pretty efficient compared to a lot of other solutions. I would be posting this inside the comments, so you can check it out from there. Also, I have created a repository inside the GitHub where I have posted the solution of all the Java problems that we have done so far inside the LeetCode. Okay, so this is the repository. You can go to any problem, and you would be able to find the accepted Java solution for that particular problem, and I would be posting this link inside the description as well, so you can check it out. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do spiral matrix lead code problem, and this problem has been asked by tons of my favorite companies. Companies like Microsoft, Amazon, Apple, Facebook, Google, Adobe, Uber, Bloomberg, TikTok, Walmart, Tesla, Paytm, Flipkart, ByteDance, eBay, Goldman Sachs, Robinhood, and Salesforce. So you can imagine that this problem has been really popular at top tier IT companies, and that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given an m cross n matrix, and we need to return all the elements inside the matrix in a spiral order. So suppose we are given matrix like this in a 3 by 3 matrix, we need to iterate over this given matrix in this following fashion in a spiral and return elements in that sequence. So to make things more understandable, I have drawn different matrix of different sizes, and let's see that what would be the spiral traversal for each one of them. So we will always start at the 0 0 position, and then we'll start traversing on the right side until we hit a boundary. So over here we hit a boundary, and then because we hit a boundary, we'll go downwards. Now again downwards we hit a boundary again. Again we will go in the left direction. Again we hit a boundary over here of the matrix. Now we'll again go upwards in the direction, but now this time we will not wait for us to hit a boundary. We will actually stop at this position number 4. Why? Because if we keep going in this upwards direction, we will end up at this position number 1, which is, though it is before the boundary, still this is the node that has already been visited, which means that we are traversing in a particular direction until the point where whether we hit a boundary or we hit a visited visited node. So this is a really important concept to understand. Now let's go back to the traversal. So again from this 4 we will come back at this point 5, and now from this 5 you can realize that there is no other direction this 5 can go to, and this would be the answer. So this would be the end of the traversal. Let's do the traversal for this 4 by 4 matrix. So again we start at this initial position, we start going on the right direction, then again we go downwards, again we go leftwards, then we go up until the point when we hit this visited node, again we go right, again we go down, and again we go left, and this would be the traversal. For this 5 by 5, let me quickly show you what would be the traversal, and of course it's pretty simple to understand, so I know you also know that what would be the traversal. This is how we are traversing in all three of the cases. Now remember that there are two important things to consider over here. First thing is that at any point we are traversing, we are always following a pattern in terms of the number of directions or the type of direction we are taking, and that pattern is always we start at the initial position, which is this one, and then we always go on the right side first. After going the right direction, we go downwards. So we go downwards. After going downwards, we go leftwards, and after going leftwards, again we go in the up direction. So we go upwards, then again we go back on the rightwards, again we go down, and again we go left and right up, and we keep on following until we reach to a point where all the nodes that are adjacent to any particular node, so in this case this number 10, where all the other nodes they have already been visited. In this case it would be this node number 13, where all the other nodes they have already been visited. So we are traversing until the point where we exhaust out of all the nodes that we can traverse. And let's see that what would be the approach for us to solve this problem. Like we already know that what are the directions we need to traverse into, and we are always traversing in any particular direction until the point where either we hit a boundary or we hit a visited node, which means that these things are important for us to keep track of, that this boundary or this visited node, we need to understand that how to identify them, how to keep track of them, and what are the different approaches to tackle both of these, and what would be the solution. So in order to solve this problem, there are actually two different solutions. I'm showing you both of them. You can pick whatever you want to. Both have its pros and cons, and you can discuss it with your interviewer which solution you want to pick. So let's go with the first one. Now first approach is that we actually start shrinking the boundaries and we don't care about visited nodes. How we are going to do it, let me quickly show it to you. So first of all, we always start at this initial position. We know the directions we need to take. We go right, then we go down, then we go left, and then again we go up. This is the state of direction we are going to follow. Let me also create our answer of the nodes that we are going to traverse along. So first of all, we start at this position number 1, and then we follow up until this point where we hit a boundary over here. Now the moment we hit a boundary over here, we are going to add all of these values to our answer. So let me quickly add all the nodes to my answer. And then because we hit a boundary over here and this was the direction, right direction, we know that next direction we need to go is downwards. So we start going downwards, but we are going to do one thing important over here, and that thing we are going to do is we are going to ignore all of them, and we are going to actually shrink our boundary up until this point. So originally this matrix was actually 4 by 4 matrix. Now we are going to convert this matrix to be a 3 by 4 matrix, and we are going to ignore this first row as if that never actually bothered and that never actually existed. So by doing so, what we are doing is that we don't need to take care of these elements, and since we have already added them to our answer, so they are always going to be in our answer as well, right? Now again we go downwards in the same path until the point where we hit a boundary. So we hit a boundary over here. We are going to add all the nodes to our answer. So nodes would be 8, 12 and 16 in this sequence, and again we are going to ignore all of them because we have seen all of them, and now again we are going to shrink our boundary up until this point, and we are going to ignore all of these places. So let me actually remove them, that they never existed for us. Now again after downwards we will start traversing on the left direction. So we go until this point, we will add all the entries in our answer, and again we are going to delete all of them because they never existed for us, and our boundary actually shrinks even further. and after that we start going in the upwards direction. But notice over here we don't have to care about these nodes because we have already shrunk our boundary to only consider up until this point, which means that we are going to add this values 9 and 5 and again shrink our boundary, and then we will add this value 6 and 7, again shrink our boundary, add value number 11 and then again shrink our boundary, and in the end we are only left with one value, value number 10, and we will add it to our answer, and this would be the answer that we need to return. So this solution works perfectly fine. We don't have to bother keeping track of the number of nodes visited because we are shrinking our boundary with every single iteration. And let's see that what are the pros and cons of this one. So first of all, we will try to calculate that what is the time and space complexity for this one. So time complexity is actually going to be big O of m cross n. Why m cross n? Because we have to iterate all the nodes inside the given matrix. So that is a given thing. Now in terms of space complexity, we are actually doing it in a constant space complexity. Like you can't consider this answer to be a space complexity because anyways we have to return a list of all the nodes that we have traversed. So that is part of the answer, that is not part of our algorithm, and that is why this is a very good approach. And you can discuss with your interviewer that if he is okay with this approach, you can also move forward with this one. Let me show you what would be the second approach. So for the second approach, we are actually going to keep track of the visited cells and also the boundaries, and whichever we hit first, we are actually going to change our direction. So one thing remains common is that we are always going to traverse in the same sequence of direction. So first of all, we will traverse in the right direction, then we will go in the downwards path, then we will go in the leftwards path, and then we will go on the upwards path. So this will remain common, and then we keep on repeating, and at any moment we hit either a visited cell or we hit a boundary. So originally we are at this position number 1, and we are going to mark all the coordinates of the matrix. So the coordinates of the matrix is going to be 0 1 2 3 and 0 1 2 3. Now current position of this 1 is actually 0 0, we can see over here. So what we are going to do is we are going to create a hash set, and inside the hash set we are going to first of all check that whether the coordinate that we are visiting, have we visited it already or not. If we have not visited it, we will add an entry to our hash set. So at this position number 1, we will add an entry to our hash set saying that okay, currently we have already visited this coordinate number 0 0, and we are also going to create our answer list, and inside the answer list we are going to mention all the nodes that we have traversed, which we need to return in the end. So we will add this entry number 1, and then we will keep iterating on this direction on the right side until we hit either a boundary or a visited node. Remember, either a boundary or a visited node, both the things we are keeping track of. So, and at the same time we are going to add all the entries. So in this case we would have added entries like 0 0 0 1 0 2 and 0 3. All the things we have added, we have already also added it to our answer that we have already traversed this nodes 1 2 3 and 4. And now we know that because we have hit a boundary, it is time for us to go in the downwards direction. So again we will go in the downwards direction until the point we hit a boundary, and we would have also added all the values to our hash set as well again, and also to our answer list as well. Like I am not going to bother writing all of them, but I can understand that you are smart enough to understand that. Again we go on the leftwards direction until the point we hit a boundary, and again we start going on the upwards direction. But notice that when we are going in the upwards direction, we are actually going up until this point number 5. We are adding all the values to our hash set, we are also adding all the values to our answer. Now at this 5, when we try to go this position number 1, we would first check that okay, whether this position number 1, which is located at the coordinate 0 0, have we visited it already or not. And we would identify that okay, the 0 0 has already been visited, which means that because it has been visited, we actually don't need to go and do that again. Or what we need to do is change our direction. So from this position number 5, again we would change our direction in the same manner where we would have changed our direction if we would have encountered any boundary. So then again we will add all those entries 6 and 7 and again add them to our hash set, and then we keep iterating until we reach to the end of all the entire matrix, and we would have visited all of them. Now this solution works perfectly fine. Now, but the thing is, you would immediately say that, hey, this solution actually we are using an additional hash set, which means that for the space complexity we are actually using big O of m cross n space complexity, which means how come this solution can be better? This is actually a bad solution. So your interviewer is definitely going to let you know that, okay, you can't use this hash set to keep track of all the visited nodes. In this case, what we are going to do is, there is another solution to solve this problem without keeping track of all of the visited number of nodes. So at any position, if we have visited some node, what we are going to do is, we are going to add it to our answer list first, and then we are going to change its value. And how we are going to change its values, we are going to put something random that is out of bounds, or it doesn't even make sense. So over here, suppose we are at this position number 1, and then we start traversing this 1 2 3 4. So we have traversed 1 2 3 4, we have added it to our answer, and then at the same time, the moment we are done with traversing through any node, we are actually going to change its value to something, let's say minus 100, or let's say value number false, or something like that, right? Anything that is not part, that can never be a part of this matrix, and we need to replace our value with this one. So let's say in this case we replace our value with this minus 100, considering that this would not be a part of this matrix. Like, it can be, and then you can change this value, you can discuss it with your interviewer, and then again we start iterating in the same fashion. So again we would have added all the values to our answer list, and again we would have changed all of its values to whatever the value we decided, and we are going to keep repeating the same work up until this point. And notice that at this position number 5, when we try to go upwards, we are going to check that, okay, if the value of this particular cell, if that is not minus 100, then only we can say that, okay, this node has not been visited, and then only we will add it to our answer. But the moment we find out that, okay, this value is actually minus 100, which means we have already visited this node and added to our answer already. So now we have to change our direction in the same manner where we would have changed our direction if we had encountered any boundary, and then we would follow the same path and we would be able to solve this problem. So if we see the time and space complexity, in this case the time complexity is also going to be big O of m cross n, and the space complexity is actually going to be big O of 1 constant time space complexity. Now you would argue that the issue with this approach is that we are actually changing whatever the given input is, and that is not a bad practice, that is not a good practice in when you are actually doing inside the job. But when you are giving any competitive coding interview, your interviewer might expect you to do it. So it's always good to know a better approach. Let's move on to coding now. So first of all, we are going to create an integer called visited, and we are going to assign it some random value. So let's assign 101. Also, we are going to create two variables to keep track of the number of rows and number of columns we have. After that, we are going to have a couple of variables to keep track of the row position and column position we are at, and we are going to initialize it to value number 0. Now we have to iterate over our 4 directions. So we are going to create a 2D array. We are going to name it as directions, and we are going to iterate over all the 4 directions. So we are going to have 4 coordinates that would be used to go to any direction we want to. And we are going to maintain a sequence where the first would be to go to right, then next would be to go to down, then left, and then up. Now we need to keep track of what is the current direction we are at and when we need to change the direction. So we are going to initialize couple of variables called current direction and the change direction, and we are going to assign the value 0 to both of them. So we will have to create an array list to store the result. So we are going to initialize a list of integers to store the answer. Inside our answer, we are going to add the first node of our matrix, which is located at position 0 0. And after that, remember, every time we go through any value, we will have to update that value inside the matrix, because I am showing you the implementation for the second approach I showed in the explanation video. So we will update the value of this matrix node to this visited element that we already set up. Now we will start iterating over our given matrix, and we are going to have few conditions. So first thing is we need to iterate over the given matrix. Also we have to iterate over in a particular direction, and the moment we encounter a condition where we are either reaching a boundary or reaching a visited node, we will have to change the direction. So we are going to use current direction, change direction, and make conditions around them. So first of all we are going to have a while loop, that while the change direction is actually going to be less than 2. And why less than 2? Because we have 4 directions, and at any point we can only go in one direction, and when we are the maximum amount of patterns we have is either we can go on right down or left up path, and that is what we are going to use. Once that is done, we will have another while loop that takes care of all the possible ways where we need to restrict our matrix. First 4 conditions would be to check that whether we are hitting a boundary, and the last condition is to check that whether we are hitting a visited node or not. If none of this is true, first of all we will have to reset the change direction to 0, because we are not breaking any direction. After that, we are going to update the value of row and column. Then we will add the current matrix row and column position to our answer array list, and then we will update that value for that particular row and column position to visited value. And after first loop ends, we will have to update the values of the current direction and change direction. So for the current direction, we are actually going to add a value, and then we are going to modulate it by 4. We will have to update the value of our change direction. And after both the loop ends, basically our answer array list should have all the elements, and we would have traversed the matrix, so we can simply return that. Let's try to run this code. Okay, seems like our solution is working. Let's submit this code. And our code actually runs 100% faster than all the other solutions, which is pretty nice. Also, I have created a GitHub repository where I'm storing all the problems that I have solved so far, and you can go to any problem and you would be able to find the Java solution for that, and you can use it. It's quite helpful. And I would be posting this link in the solution as well, also this solution in the comments as well, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do rotate image lead code problem, and this problem actually has very real practical applications, as we know that there are a bunch of different softwares that allows the option to rotate an image. And if we see the list of companies where I want to join in and already have asked this problem, there are companies like Facebook, Microsoft, Amazon, Apple, Google, Bloomberg, Uber, TikTok, Nvidia, eBay, Paytm, and Robinhood. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem, and basically we are given an n cross n 2D matrix which represents an image. Now we need to rotate this image by 90 degrees clockwise. Also, one more thing that is mentioned, that we need to do it in place. We do not need to use an additional 2D matrix to solve this problem. So the space complexity has to be constant in this case. Let's try to see it with an example. So over here we are given a matrix like 1 2 3 4 5 6 7 8 9, and we can see that this particular row is actually converted to this column, which means that all the nodes have been transported to 90 degrees, which means this 1 has gone to this place, this 2 has gone to this place, and this 3 has actually gone to this place. And same goes for all the other elements, that this 4 has actually gone to this place, which we can see over here, and this 7 has actually gone to this place, which we can see over here. And the same way it is shown in this second example. Okay, suppose this is the input matrix we are given, which means that this is the answer for the 90 degrees rotated matrix. Now notice couple of interesting things in both of them. Well, over here the value 1 2 3 is in a row. So over here this value 1 2 3 is actually in a column. Same goes over here, that this value 4 5 6 is in a row, but this 4 5 6 is in a column, and same goes for the 7 8 9 7 8 9. So this is clearly a pattern over here. And basically what we can do it is that if we somehow convert this input to replace all the values that are inside the rows to be inside the columns and then reverse those entries, so reverse all the rows, we would actually get a 90-degree rotated array. And let me quickly show you how we are going to do it. Okay, so suppose this is the original input. I have drawn it much bigger over here. And now what we are going to do is for every single row, we are going to place it inside the column, and every single column we are going to place it in the row, which means that currently at if we consider this position number 2, if we see the I and jth location, this 2 is actually located at the position 0, 1, representing these two values. So what we are going to do is we are going to flip the values of the 0 and 1, and same we are going to do this for this 4, which means that this 4 will come to this place and this 2 will come to this place. The thing we did for this 2 and 4 we are going to repeat for all the other characters, and then we would have an array which would have where all the rows would have been converted to all the columns. Also, there is a name for the process of converting all the rows to all the columns, and that is actually called transposing a matrix. So first of all, we are going to transpose this original given input matrix, and we will see that the result would look something like this. So this 1 will remain at the same position because this 0, 0 is at the correct place, so we can't change anything. Now this 2 is going to be replaced by this 4, which means that over here we would have 2 and over here we would have 4. Again this 3 is going to replace by this 7, so over here we would have 7 and over here we would have 3. So if we just notice right now, this row 1, 2, 3 has actually been converted to a column, and this column 1, 4, 7 has actually been converted to a row. We are going to repeat the same process now, and now this 5 will not have any impact because the position is actually 1, 1. But for the 6 and 8 we will actually have to swap their values, that now over here we would have the value number 8 and over here we would have value number 6, and this 9 will remain at the same position because the value is 2, 2, which means we can't do much about it. And now basically now we have created all the rows and converted them to different columns. Now the next idea is that we are going to put this in the reverse order, and if we reverse the rows for this transposed matrix, we can clearly see that we would get a 90-degree rotated answer. Let's do that. So over here the values would be 7, 4, 1. If we reverse this particular row, same thing we will do for this one. So the answer is going to be 8, 5, 2, and again for this one, the last row, the answer is going to be 9, 6, 3. And if we see, this is actually same as the answer we had achieved before, and I just draw all these 3 different matrices to give you an example that how we are going to do the things. But basically all of this activity can be done in place inside the single matrix. All we will have to do is we'll have to use a temporary variable to first of all swap the elements in this fashion, and then once that is done, we will need a temporary variable to replace the values inside the given matrix and reverse the rows. If we see the time and space complexity for this approach, basically for the time complexity we will have to iterate over all the elements inside the given node to create this transpose matrix, and once the transpose matrix has been created, we will have to reverse all the elements, which means that the time complexity in this case is going to be big O of n cross n, but we will have to repeat this process 2 times. So which means we can say that big O of n cross n times 2, but in general we can just write it as big O of n cross n, and this would be our solution. In terms of space complexity, as mentioned earlier, we are not using any additional space, which means we are doing it in a constant space complexity, and this is a very good solution. Any interviewer would be really impressed with your approach, and this works for all the different n cross n matrix. Now let me quickly show you another solution for the same problem where we don't need to do like this transposing activity, and we can actually solve this problem in a single go. So for the second approach, we are going to do things a little bit differently. First of all, I have drawn over here a bunch of different matrix of different n size. So n is equal to 1, 2, 3 and 4 I have shown you. And now we are going to see that if we rotate them 90 degrees, can we see some patterns over here? So suppose we have a matrix of the size number 1. If we rotate this 90 degrees, it makes no sense. The value is going to still remain same. So we are going to keep it as 1. Now for this n is equal to 2, if we rotate this matrix by 90 degrees, actually the thing is going to happen is that this one node is going to shift one value to the right, this two node is also going to shift one value to the right, 4 and 3, all of them are going to shift one value to the right, and the answer in this case is going to be, okay, so first of all we'll shift one over here, one value to the right, 2, and then 4, and then 3. So this is the 90 degrees rotated angle for this n is equal to 2. So basically what we have done is we have rotated all the values one place to the right, okay, for the outer layer. And in this case, since we only have 4 elements, which means the layer is only 1, we are good. So when we get to this n is equal to 3, things becomes a little bit interesting. And interesting how? Because we have the cells located on the outer layer and we have one cell that is located in the inner layer. Now when n is equal to 1, when the number of cell that is located inside the inner layer, we know that the value is going to remain same. So even if we 90 degree rotate this particular element, it is still going to fall over here on the same place. We are not going to do anything special with this one. But for these other values, we will going to apply the same logic we applied over here, where over here, where because n was 2, we had to rotate all the values 1 degree to the right or one place to the right. In this case, because n is equal to 3, we are going to rotate all the values to the two elements to the right, okay, and this would be the answer. So if we see in this case, this 1 is going to come at this place, this 2 is going to come at this place, this 3 is going to come at this place, and same thing is going to keep on repeating for all the other elements. And that is how we are going to find its solution. So let me quickly draw the solution for this outer layer over here. This is the answer for the outer layer of this matrix. And because in the inner layer we only have one element, and for one element we don't have to do anything special, the 5 is going to be at the same place, and this is going to be the solution, that we rotated all the elements couple of places to the right. Now in this case, n is equal to 4. So obviously for the outer layer, you can imagine that the pattern we are going to follow is going to be the same, that we are going to rotate all the elements 3 steps to the right. Okay, so that is clear. But for this inner layer, we can actually see that this time we have a set of 4 values, which means we have a 2 cross 2 matrix inside. So over here we are going to use the same logic we used over here, where we are going to rotate them 1 step on the right. So first let's do it for the outer layer, and then we will do it for the inner layer. So the rotation for this outer layer is completed. Now for this inner layer, we will have to rotate them 1 times based on whatever we have seen when n was 2. So we are going to do the same thing. This is the answer of 90 degree rotated angle, which means one thing we can see over here is that we can have 4 pointers starting at this 1, 4, 16 and 13, and rotate all these values in place by using a temporary variable. Once that is done, we can repeat the same process for this value number 2, 8, 15 and 9. And again, we will keep on rotating them sequentially at the same time in place. And then we would be able to fill out our outer layer. Once that is done, we will come inwards and we will start filling the inner layer based on whatever the number of n we have. And that is the approach we are going to take. Okay, so suppose we have a 3 by 3 matrix, and I'm going to show you what is the approach we are planning to take. Now this additional matrix I have drawn, that is only for the understanding purpose. Actually we are going to do everything in just one single matrix, but I'm just going to show you that what are the value changes happening and how we are going to use this temporary variable to fix our problem. So first of all, we are going to store the value of this 1 inside our temporary variables. Okay, so the value inside the temporary variable is 1. Now what we are going to do is, first of all, we are going to project this value number 7 to this place 1. So this becomes 7 and this becomes 7. Currently this is the scenario. Now we are going to project this value number 9 over here, which means that this 7 is going to be replaced by value number 9, and this is also 9 at this at the current moment. Again we are going to project this 3 to this 9, which means that the value of this 9 is going to be replaced by 3, and this is going to remain 3. And now at the final moment, we are going to take whatever the temporary variable we had, and we are going to put it in this place, which means that this value is going to be 1. So at a single iteration, we have actually shifted values of all of these 4 places in its correct position. again we are going to repeat the same procedure for these 4 values, which means that over here now we are in the next iteration. Now the value of the temporary variable is 2. Now because the value of the temporary variable is 2, first of all we are going to project this value number 4 to this place number 2, which means that currently both values are going to be 4 4. Then we will project this value 8 to this 4, which means that this is already 8 and this value becomes 8. Then we will project whatever value of 6 we had at this position number 8, which means that this value would become 6 and this is already 6. And at the end we are going to take whatever the temporary variable we had, we are going to project that value over here, which means that this 6 is going to be replaced by this value number 2. And once that is done, essentially in 2 iterations we have taken care of all the values that were placed out in the outer layer, and we are done with this one. Now only thing we need to consider is this inner layer, and because for the inner layer n is equal to 1, which means that we can basically leave the value as it is, and this is the answer. And this is how we are going to able to rotate the entire element in 90 degrees in just like very few iterations. We don't have to do like transpose matrix and then replace all the values and change all the values. So even if we see the time and space complexity, in this case the time complexity is going to be big O of n cross n, but we only have to do it single times, and space complexity is going to be big O of 1 because we are only using an additional temporary variable to store some values. Apart from that we are not using anything special to store any values. So we will initialize a variable called n, and we are going to store the length of the matrix for this one. Once we have that, we will have to iterate over this given matrix, and we are going to create 2 for loops to iterate over this given matrix. Now remember, we only have to iterate over half of the matrix. We don't have to do much work, which means that we are not going to iterate from int I is equal to 0 to I is equal to n. We are actually going to do it I is less than or equal to n plus 1 by 2. Now you will ask that why n plus 1 by 2? Because in the condition where the given n is odd number, we will have to take care of that scenario as well. So first of all, we are going to create a temporary variable, and we are going to store value of one of the elements inside this temp variable, and then we will start working on the flip operation for the remaining 3 elements. Once that is done, we will start iterating over all the elements. And once this loop ends, basically we would have rotated our matrix 90 degrees angle for all the elements. Now the question comes that how did I get this value of I and j? Actually I could explain it to you, but I would expect that you draw any 3x3 or 4x4 matrix on paper and try to see that how we are getting these values of I and j, because that would be a very good exercise for you. Anyways, I would be posting this code in the solution, so you would be able to check it out, but still I would expect that if you do it by yourself, you would never be able to forget it. Now let's try to run this code. Okay, seems like our code is working. Let's try to submit this code. And tada, our solution is actually 100% faster than a lot of other solutions, and basically we are solving this problem pretty efficiently. Again, I would be posting this in the comments, so you can check it out from there, and there I would ask you to figure out that how we are getting these values of I and j compared to this value of n, and that would be a really good exercise for you to do at home. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do word search lead code problem, and if we see the number of companies where I want to work at who have already asked this question, there are companies like Amazon, Twitter, Microsoft, Uber, Bloomberg, Facebook, TikTok, Snapchat, Google, Apple, Samsung, Roblox, Goldman Sachs, ByteDance, and eBay. So these are really popular companies, and this problem is really popular because it has very real life applications. We have all played games like crosswords and Wordle on our phones and on the newspapers and different kinds of stuff. So that is where this problem is associated with, and we are going to see that how to solve this one. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given an m cross n grid of characters called board, and we are also given a string called word. Now we need to see that if this word can be created based on whatever the number of characters we are given on this board, and if it does, we need to return true, else we need to return false. Also, we are given a note that the word can be constructed from letters sequentially adjacent cells, where adjacent cells are either horizontally or vertically neighboring. And we are also told that same letter cell may not be used more than once in order to create that word. So let's try to understand this with an example. Over here we are given this big board, and on this big board we are told that we need to find the word A, B, C, C, E, D. So if we see over here on these marked values, so this starts with the word A, the neighboring word is B, the neighboring word is C. Again, we are told that we can horizontally or vertically see the words. So if we go vertically downwards, we see another C, and then we find another E, and at the end we find D, which is also adjacent to E, which is this letter, and this is basically part of this given board. So in this case we can return true. Now suppose if this word if we were not able to construct this word, we would not return true and we would return false. So let's see that what would be the optimal approach to solve this problem. Well, we have actually solved similar problems like this in the past using DFS and backtracking, and this is what we are going to do for this problem as well. Let me quickly show you how. Okay, so suppose this is the custom example we are given, and we need to find the word spider to see that whether it exists on this given board or not. And the idea is actually quite simple. What we are going to do is, first of all, we are going to take the first character inside this word, which is S, and we are going to iterate over this matrix until we find this first character. The moment we find the first character from whatever the place is, then we will keep on trying to find the next letter, the next words inside this word, to see if it exists in the neighboring node or the neighboring cell of the board inside this given matrix. And if somehow we are able to reach to the end of this word, we can return true. If we don't reach the end of the word and we actually reach the end of the matrix, we can return false. So the idea is actually quite simple, and there are just few tweaks we will have to use in between. So first we will start iterating over this matrix, trying to find this word number S. Now this is not S, this is not S. Over here we find the first value as S. So because this is the first value as S, now we will have to try to see that whether this P exists or not in the neighboring node of this S. We can clearly see that P exists. But before doing that, what we are going to do is we are actually going to mark this node as visited. So one way to do is to use some visited hash set and store all the values, but that is just causing strain on and to have an extra memory usage. Rather than doing that, we are going to actually modify this input, and we are going to mark it something like hash or something, which is an invalid value and it can never be there. So which means at any point we encounter that this value is hash, we don't need to go back to that place. Now we will start iterating over the neighbors of this S. So neighbors of S can be these three places. If we try to look at these three places and we are looking for the alphabet P, so P is present over here, which means that so far we have found S and P. Now we will update our value to I, and we will try to look for I in this P's neighbor. Also we will mark this node P as like hash, so we don't come back to this place again. Now this P has only two neighbors because this neighbor S has already been visited because its value is hash, so we can't do anything about it. Now we are looking for this letter I, and we find the letter I over here, which means again we will mark this as hash. We will update the value of word we are looking for. The word we are looking for now is D. We'll try to find the neighbors of I, and in the neighbors of I, okay, we don't find anything over here. This is not D, and this has already been visited, which is hash, which means that there is no neighbor of I that contains this value D, which means that now we haven't found the word so far, and we still have matrix to go to that we haven't visited so far, which means that now we will backtrack from this I to the position we were originally at, which means that from this I we came from P, from this to this P we actually came from S, and now we can say that okay, even in this S it does not lead to us to find this word, and then we will again proceed with our search. So again we are trying to find this letter S again and not the D, because we did not find anything in the route. which means that now, okay, this P is not S, this I is not S, this T is not S. So we are good so far. Now at this position we find a letter S, which means that, okay, this S has been found. Now in the neighbor of this particular cell, we will have to find the letter P, and we are going to mark this S as hash as a way to identify that this has been visited. Now what are the neighbors of S? These four are neighbors of S, and the one value we can find where the P exists is this one. So again we will repeat the same process. We will mark this as a hash. We'll try to find the word I we will find over here. So again we will mark this as a hash, and we will try to find D in the neighbor of this I. So we find D over here. So again we will mark this as hash. We will go update the word we are looking for, and now we will try to search for E inside this D's neighbors, and we can find it over here. Again mark this and then try to find this R. So R we actually find in the neighbor of this one, and this is the correct R, which means that now we are able to reach to the end of this word list, and we can return true in this case, saying that, okay, this actually exists inside this given board, and we will be good. So this solution works perfectly fine. Let's see the time and space complexity with this one. So for the time complexity, actually the time complexity is a little bit tricky to find. Why? Because the time complexity is actually big O of n, which is the number of cells. So for every single cell we will have to iterate at least once. So n is given, but then we will have to repeat the same process for 3 times to the length of L in the worst case scenario. Why 3 times to the length of L? Because notice that at any single position, suppose we were at this position number D, and we need to see that, okay, whether the next value E exists or not. So we need to check 3 places, not this one, because this already has the value hash, which means we won't check this one. But in theory we might have to check at all 3 places, and imagine if all 3 of them had the value E, we might have to explore the paths on all 3 of them in order to find the next value R. So that is why at every single position N, we actually have 3 different options to see that whether this word exists or not, and this L is actually length of the given word. So that is why this is the time complexity. In terms of space complexity, we actually need to store the value inside our space until the time we reach to this entire word. So it would be big O of L, where L is the length of the word that is given. And this time and space complexity works perfectly fine, and I hope this solution makes sense to you. Let me quickly show you that what would be the coding for this one. So for this word search problem, we will actually have to create a backtrack public method that will call itself, and recursively we will try to achieve its answer. So there are some variables that we will need in both in this boolean exist method and also in the new backtrack method that we are trying to create. So let me define some variables that are global and that we can use in both the methods. And the variables we are going to create is to store the value of this board, and we will also need the row and column size of this given board character array. Now we have these, we will assign values to all these 3 variables from these given input endpoints. Once we have this, we will have to iterate over this board character array. So we are going to assign 2 for loops, and for both the for loops we are going to have the I and j value iterate up until the point of this rows and columns, and inside this for loop we will call our backtrack method. Now inside this for loop we are going to call our backtrack method, and we are going to have backtrack method return a boolean reply either true or false. And inside the backtrack method we are actually going to pass in the values of the current row position, current column position, word we are trying to find, and the index value we are currently at. So for the index value we would initially start with the position 0, and we would increment it every single time inside our backtrack method. And if at any case this returns true, we can simply return true in this case. And somehow if we are able to complete this loop and get out of it without returning true, which means word does not exist, so we can return false. Once this is done, now we will create our public boolean method called backtrack. Now first of all we will check that what is the condition where we will need to return true. So if at any point we identify that the index value is actually greater than or equal to word length, which means that we have already found that the current word already exists inside our given character array, so we can return true in this case. So now we will try to find the terminating conditions, and inside the terminating conditions, first of all we will check that whether the row and column position are they going out of bounds or not. If they are going out of bounds, we can return false immediately. If that is not the case, we will try to see that the current value we are looking at inside our board, if that value is not in sync with whatever the index value of the word we are looking for. If that is not the case, we can also return false immediately. So if any of these conditions are true, we can return false immediately. None of these conditions are true, which means that the current index value actually matches the value of that row and column position inside the board, and now we will have to iterate over the neighbors of this current row and column value inside the board. So in order to iterate over the values of the row and column, we are actually going to have two arrays called row direction and column direction, and that will help us navigate all the neighbors of any particular cell. Also, before moving to the next element, we are going to mark the current row and column position to have a value called hash, so we avoid checking the same element twice. Okay, once this is done, we will also have a boolean variable called return, and initially we are going to initialize its value to false, because basically we are going to call the backtrack function for all the four neighbors of the current cell. So for that we will keep track of this ret variable, and we are going to run a loop to iterate over all the directions, and we will add the values of these row direction and column direction to subsequent row and column positions inside this recursive call to our backtrack function. We will also update the value of the index, because we can determine that we have already find the word inside the previous index, and that's why we are calling the next index where value to be searched inside the neighbors of any given row and column position. And also at any point, if we identify that the answer of this return function is actually, or this return variable is actually true, we can break out of that particular element immediately, and we don't have to check all the other neighbors. So we will put that condition as well. Once that is done, basically we are done with the checking part. Now the only thing we need to do is we will have to update the value of the row and column position to whatever the value that was originally there, and in the end we can simply return whatever the answer we got for this ret function. This is pretty much it for both our backtrack method and also our main method, and this should be able to solve our problem. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code, and our solution works as expected. And I would be posting this in the comments, so you can check it out, the solution from there. Hello friends, we are still not employed by FAANG companies, so stop lead coding till we get there. Today we are going to do longest substring without a repeating character lead code problem, and this is actually number 3 problem in the lead code, and also very popular problem. As you can see the number of companies that have already asked this problem. So if I just check the companies where I want to get a job and I have already asked this question, there are companies like Amazon, Microsoft, Facebook, Bloomberg, Apple, Google, Spotify, Uber, Goldman Sachs, Yahoo, Walmart, eBay, Lyft, ByteDance, Morgan Stanley, and Paytm. So that's why I am paying my utmost attention to solve this problem. I hope you also enjoy the video. So this is a LeetCode medium problem, and also one of the most liked problems on LeetCode. Basically we are given a string s, and we need to find the length of the longest substring without a repeating character inside this given string. So suppose in this example we are given a string like this. And in this case, if we check that what is the longest substring without a repeating character, that is this one, ABC, and the length of this is 3. We can also conclude this one as well. This has also length of 3, and we can return either of them, but the answer in this case we are going to return is actually 3. Let's see that what would be the different approaches to solve this problem. So suppose this is the input that we are given, and let's see that how can we solve this in a brute force manner. Well, the most basic idea is that we can take this input and take every single substring that is possible, and then check on all of those substrings that whether there are any repeating characters or not, and whichever the substring with the longest length we found without any repeating characters, we will just present it as an answer. So if I just show you by an example, in this case the number of substrings we can make is, okay, let's start from this A. So from this A we can make a substring of A, we can make a substring AB, we can make a substring ABA, we can make a substring ABAT, dot dot dot, and so on and so forth. We can make all of these substring. Next substring we will make starting from this value number B. So from B we can make B, BA, BAT, BATM, and so on and so forth. So in this case, the longest substring we would be able to make is actually this one, BATM, that is of length 4, and this is the answer in our case. So even if we use the brute force approach, eventually we would have found this substring by comparing all of the bunch of different substrings that we would have created, and then we would have written 4 in this case. But what is the issue with this approach? Well, the issue is actually quite trivial, that we are actually doing a lot of unnecessary work, and we are trying to find a lot of different substrings. Even if we just see the time and space complexity in this case, the time complexity is actually going to be big of n cube. Why n cube? Because we are going to do n square work to find all the substrings, and then we will have to do n work for every single one of them to find that whether there exists any repeating character or not. So this is a really bad approach. Let's see that what is the improvement we can make. To optimally solve this problem, we are going to use very important concept called sliding window, and in addition with 2 pointer. What we are going to do is we are going to have 2 pointers called left and right, and these left and right pointers, we are going to have them to follow a very important property, and that property is that between these values of left and right, all the elements has to be unique. If at any moment we encounter that there is a duplicate entry, which means that we will update the value of L to the point where the duplicate entry is mitigated or it's eliminated, and then we will again keep on progressing with this right pointer. Let me quickly show you how we are going to do that. So first of all, left and right both are going to start at the same position. Now we are going to make our right pointer move to the next element until the point where we find a place that is actually repeating. So we are now, our right pointer is at this position, our left pointer is at this position. So far we have 2 elements in our substring and both are unique. So because both are unique, we are good up until to this point. Also at the same time, we are going to have an answer variable where we are going to store the length of the maximum substring we were able to find with all the unique characters. So far initially this value was 1, but now we have found that there are actually 2 elements for this substring that has all the unique elements so far. Now we are going to update the value of our right pointer again. So right pointer will come over here. Now again right pointer is here, but at this point, okay, we need to check that, okay, amongst this A and B, does A exist somewhere? And we know that A exists over here. Now you will quickly ask me that, okay, in this case, since we only had 2 elements and we were comparing this A, it was really easy for us to identify. What if we had like 10 elements like this, and then we are comparing this A, and we need to check that whether at all these 10 positions does this A exist or not, and that would make things really inefficient, and that would be big of n square time complexity. So what we are going to do is we are going to have a visited hash set, and inside this visited hash set we are going to store all the characters we have found so far between L and R, and we are going to keep on adding until the point we find a repeating character. So initially this only had the value A when we are at this point, then we added a B. So far inside our hash set we actually have A and B, and now when this R pointer comes at this position A, first of all we'll check that whether A exists or not, and we realize that, okay, A exists inside this hash set, which means that amongst this substring we cannot add this value A because A exists over here. So now what we are going to do is we are going to remove A from this our set, and we are also going to update our left pointer to remove this value A. So okay, we ignore this a, and now our left pointer is at this position, our right pointer is at this position. So far the values are b and a, and now we are again going to add this value number a over here because this right pointer is here. Okay, what is the length so far? So the length is still 2. So because length is 2, we are not going to update in our answer, because in our answer the length is also 2. Now we are going to update our right pointer to come to the next element, and when we update the right pointer, it comes over here. So this t does not exist inside our hash set, so we will add entry t over here, and our we will update our answer as well. So now our answer becomes 3. Now again we will update our right pointer to come over here. So when the right pointer comes over here, we will have an entry m. So again we will add the value m over here inside our hash set because it does not exist before, and we will also update our answer to be of length 4 so far. Now again we will add our right value over here. So when we add the right pointer over here, and at this moment this is a, so we try to check that whether a exists in our hash set or not, and we can realize that okay, a exists already. So immediately, because a exists, now we will have to move this left pointer up until the point where we encounter this a. So okay, this b, we can ignore this, and we'll jump our left pointer. Okay, left pointer comes over here, and again this is a. So again we will ignore this, and then we will come for the left pointer to be over here, which means that left pointer is going to be here and right pointer is going to be here. And also at the same time we will have to remove this b and a from our hash set that we were currently visiting. So currently the entries we have is t and m only, and then because this right is at this position number a, so we are going to add an entry for a. Now we are going to update the, and so far the length of this one is actually 3, so we don't need to update in our answer. And then again we are going to update the right pointer. So right pointer comes over here, this is n does not exist inside the hash set, so we will add an entry called n over here, and then this length is actually 4, so answer is 4, so we don't need to update so far. And then if we try to do next to this right pointer, we come to the end of the list, and the string is empty now. So because we are done iterating over the entire string, now all we need to do is return whatever the answer we found in this case, and the answer we found in this case is 4, and that would be our final solution. So if we see the time and space complexity in this one, it's actually really efficient. So in terms of time complexity, we are actually completing all of these things in a single iteration, so it's actually big O of n. And in terms of space complexity, we are using this additional hash set to store the value, and the space complexity at any given moment is actually going to be big O of whatever the answer we have, or whatever the longest increasing subsequence we have. Because remember, at any moment we are only having that whatever the maximum number of unique characters in the substring we have. The moment we increase the moment we encounter a repeating character, we are actually getting rid of all of them. So that's why the space complexity is going to be big O of whatever the longest repeating character we have found so far. So first of all, we are going to check couple of edge cases, that if the given string is empty or if it only has one character, then we will return. So now we are going to initialize couple of variables called left and right, and we are going to initialize its value to 0. We are also going to initialize a variable called answer, and by default we are going to have the value as 0, and we are going to initialize a hash set of characters. So first of all, we are going to run a while loop till the point where right reaches to the end of the string. First of all, we are going to initialize a character variable, and to find the value of that particular index. And then we will check that whether this value exists inside our hash set or not. So if the value exists inside our hash set, we are going to remove it from our hash set, and we are also going to update the value of our left pointer. And if the value does not exist, we are going to add it to our hash set, and then we are going to calculate that whether the current answer we have is actually greater than whatever the answer we had before. And we are going to do right minus left plus 1. And at the end we are going to update the right pointer as well, and that should be it. So when both of these loop runs and after it ends, we should have our answer inside the answer variable, so we can simply return that. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's try to submit it. And our code runs as expected. I will be posting this solution inside the comments. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do longest repeating character replacement lead code problem that contains very important properties related to string based problems. If we see the companies where I want to get a job and that have already asked this question, there are companies like Google, Amazon, Uber, Adobe, Facebook, Apple, Bloomberg, and Microsoft. So some of the top tier IT companies. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given a string s and we are given an integer k. Now we are told that inside this given string s, we can replace any character with any other character in the English language, and we can repeat this operation k times. Now, after repeating this operation, what is the main purpose of this question is that we need to return the length of the longest substring that contains the same letter by doing this replace activity, and we need to return that length. Okay, so now we will try to understand this problem with this example. So suppose we are given our s is equal to a, b, a, b. And we are told that k is equal to 2, which means we can replace any two character with whatever two characters we want. So in this case, we have two options. Either we replace these two b's with value number a, then we will get a string that looks like a, or we can replace these two a's with the letter b, and then we will get a string. Our concern is we don't care what is the value of the string. Our aim is to find the longest substring that contains all the repeated character, and we need to find the length of it. In both the cases, the length of these two is actually 4, and this would be the answer we need to return. So this is what the problem is asking us to do. Let's take one more example to make our understanding more clear. So suppose our given s is equal to hp, h. If this is the case, and our given k is equal to 2 again in this case. So now if we see the options we have, we can replace like these two p's with the value h. So that will give us a string like h. And so if we see the longest substring that contains the same letter, the length in this case becomes 5. Second option we have is that we choose any two h value, suppose these two, and we replace it with value number p. If we do that, we will get a substring that looks like this. So in this case, if we see that what is the longest length of the subsequence that contains the same letter, it's actually 4. So this is 4 and this is 5, and we need to return the longest. So that's why this is the most optimal way to approach this problem in this case, where we are going to replace these two p values with the letter h, and we don't do this p operation. So there are few ways to solve this problem, and there is also a brute force way to solve this problem. So first I'll show you the brute force way, and then we will see that what would be the optimized approach. First of all, we identify that what is the thing that we want to find. We want to find a substring, and then we want to replace the characters, and then we want to find a substring that contains the longest length with the same characters, right? So first approach we can take in the brute force is that we take every single substring that is possible. So even if we just see that substrings that starts at a, we will get substrings like a, b, and a, something like this. Again, if we see substring that starts with b, we will get b, a, and so on and so forth. So we would end up with bunch of different substrings. Then we will start this replace operation on all the substrings, and eventually we would find some substring that will look like this a, or this b. And in any case, we would be able to return the length as 4. Like, okay, this solution would work and we will get the desired result, but there are a lot of issues with that. Even if we just see that for a single character, we end up with like so many substrings, and we still have more substrings to go to. So this is a very inefficient approach, and we should avoid doing it at all costs. Okay, before we come up with the optimal solution, first of all, we will have to identify that what is our need. Our need in this case is that we are given this string, and we are told that we can replace any two characters inside this given string with any other characters because k is equal to 2. Now we need to find a substring where all the characters contains the same value, and because they contains the same value, we need to return the length of it. So first of all, we will have to identify that what is the substring where we can actually create all the characters of the same length. So first of all, let's see that can we apply this thing on this whole substring for this entire string of all the 5 characters, and this given k is equal to 2. So first of all, we will try to identify that what is the number of occurrences of every single character. So a occurs 2 times, b occurs once, c occurs once, and d also occurs 1. So which means that because a occurs most of the time, our logical or rational conclusion is to create a substring where all the characters are a, because in that case we will actually have one additional character. If we try to create all the characters with value b, c or d, obviously we are always going to fall short by one character, because the value of a actually appears twice, which means these 3 things, they have less significance compared to this a, because a is the most repeating character. And why I'm putting so much emphasis on most repeating character, because this along with this k and the length of the string or substring defines that whether any substring we can convert it to all the repeating characters or not. Let me show you how. Suppose in this case we consider all these 5 characters. Even if we replace any 2 characters, in this case we have 3 characters to replace from. If we replace any 2 characters, no matter what happens, we won't be able to create a substring where all the 5 values are actually a. Why? Because we only have the option to replace 2 elements, and there are 3 different elements that contains different values. So how we come up with this value that there are 3 different elements that contains different value than a? Well, what we did was we took the length. So length in this case for this substring is 5. So we took the length of this substring minus, we subtracted the most occurred character. So most occurred character in this case is a. So length 5 minus a 2, and this we get 3. So at any case, this value, if that is greater than or equal to this value number k, which means that this particular substring we cannot do anything about it. We cannot convert into a valid or legitimate substring where all the values contains the same character. But if we just shorten our search, if we try to search in these 4 characters, okay, now what is the breakdown of the number of occurrences of every single character? Well, a still occurs twice, b occurs once, c occurs once, but d is not appearing, so we ignore this one. Now in this case, the length of this is equal actually 4, which means that if we apply the same formula, that length minus whatever the maximum occurred value, so maximum occurred value is still a, which means that we do 4 minus 2. So 4 minus 2 is 2, and this 2 is actually equal to whatever the value of k is. Because this is equal to k, and in this case we can define that for this particular substring we can actually convert it to all the characters being same by using this replace function. And if we just replace this value b and c, we will get actually a substring that is all the a's, and this is the answer. So basically this is the critical part. Now remember that in order to generate this, what are the things we needed? We actually needed that what is the current length of the subsequence that we are following, or what is the length of the substring that we are doing. We actually need to know that what is the maximum occurrence of any particular character in any given subsequence. And we also needed that what is the value of k. Based on it, we were able to identify that whether any subsequence can it be converted to having all the characters to have the same value or not. And based on this concept, so formula we can create is that a valid subsequence is a subsequence where the length of the subsequence minus the most occurred character. If this one is actually less than or equal to whatever the value of k is, if this is true, then we can say that this is a valid substring, and the length, whatever the length of this particular substring is, that is also the length of the substring which contains the most repeated characters. Let's see it with an example. Okay, suppose this is the example that we are given and we want to solve this one. First of all, we are going to see that what is the formula that we have to use. Well, the formula we have to use is that for any subsequent to be valid, what we are going to do is we are going to do length minus whatever the max occurrence in that particular subsequence, and we will see that if that value, if that is less than or equal to k, if that is less than or equal to k, whatever the length is, we can treat it as our answer, and whatever the maximum answer we find so far, we will conclude it as our solution. We already know this formula. Now we need to see that how can we implement that. Basically, we are going to use a sliding window plus 2-pointer solution. And inside this solution, what we are going to do is we are going to have two variables called left and right to be initialized at the first position. We are going to update the right value to the next element. Then we will check that whether the substring is valid or not. If the substring is valid, we will calculate that what is the answer. We will update the answer. Again, we will move the right value, and again we will move the right value. Again, we will move the right value until the point when the substring is not valid. The moment the substring is not valid, we can conclude that now we need to shrink our substring. So basically, suppose the R is now at this position, we will have to update the value of left. So we will ignore this element and we will move our left value over here, and then subsequently we will keep moving on, and every single time we will keep track that what is the maximum answer we have found so far, which is the longest repeated character substring, the length of it. And whenever the R reaches at the end of the list or at the end of this string, we can conclude that whatever the value we have stored in the answer, we can return it as the answer. So now, because we are using this 2-pointer approach, we know that at any given moment, what are the things we need? Well, we need a couple of things. First thing we need is we need this length. So length we can identify based on the difference between this left pointer and right pointer. That gives us the length of the current substring. Now we need to know that what is the maximum occurrence at any given moment of any particular element. So we don't know that, right? So what we can do is we can actually create an array of size 26. So one for every single character in the English language, because we know that there are only 26 characters. And whenever we find any value on the right side, we will add that value to our array. Or if we move any character on the left side, we will reduce that value from our array. So at any given moment, we would always know that what is the maximum value we have at any given position. And let's see by an example that how we will complete this operation. So let me quickly show you an example that how we will iterate over for this given example. Let me clean this up a bit. Okay, so initially our left value and right value are located at these two positions. We are also going to have an array to store the maximum occurrence of any single element. So currently I'm just showing you the elements that are coming in, but that is the idea that we will keep in mind. So first of all, currently the value is p. So we will add p over here, and we will notice that okay, the occurrence of p is 1 time. Just this is for understanding purposes. When we do the code, it would be slightly different, and I will explain it to you when we would be coding. Now so far this list has to be valid because there is only one character, right? Now we will update the value for r. So this is x, and x is also present 1 times. Now we will see, so current length of this string. So now r is located over here. Okay, so current length is actually 2. And what is the k value? K value is also 2 because that is constant, so that won't change. And what is the maximum occurrence of any character so far? So maximum occurrence is still 1, as we can see over here. So maximum occurrence is 1. So if we apply this formula, 2 minus 1, so 2 minus 1 is actually 1, and 1 is less than or equal to value of k, so that is true. So because this is true, we can say that the length of at least 2 characters can be part of the answer. So we will mention that in the answer. Now again we will update the value of r. So now r comes over here. Because r comes over here, we will update the value of q over here, and we know that it occurs 1 time. Again, so the length, so the current length is actually 3, and the maximum character is still 1. So we will do 3 minus 1. So 3 minus 1 is again 2. 2 is still less than or equal to value of k. So this is also true. Because this is true, the current length can be part of the answer. So we will update our answer to have the value 3. Now we will again update the value of our r. So now r will go over here, and this is x. So for x value, we already have 1 as its occurrence. Now x has the occurrence 2 times. So we will update the occurrence of maximum number over here called 2 times. The length also increases, so length will become 4. Now again we will try to see that what happens with our equation. So we will do 4 minus 2. So 4 minus 2, this is 2. 2 is still less than or equal to k, which is 2, which means that we can update the answer to the value 4. We will update the answer to be 4. Now again we will update the value of our r. Now r moves 1 value to the right. Now this is y. Y is occurring 1 times. Now the current length is 5, and the maximum value we have is x, which is 2. So far we are good. Now we will try to do 5 minus 2. So 5 minus 2 is actually 3, which is greater than k, which means that this condition is not satisfied. So because this condition is not satisfied, what we need to do is we need to update the left element. So we will update the left element over here. So now left comes at this place, but because we are updating the left element, we will also have to remove this one p over here. So we will remove p from here, and now we will update the value. So now length will become 4. Again, maximum occurrence is still 2. So 4 minus 2, that is 2. 2 is still less than or equal to k, which is good. So far we are good. Now again, we will update the value of our r. So now r comes at this place. Because r comes at this place, the occurrence of x comes to 3. Now because this comes to 3, we will update the value of maximum occurrence to be 3, and we will update the length to be 5. Now we'll do 5 minus 3. 5 minus 3 is 2. 2 is still less than or equal to k. So because 2 is still less than or equal to k, we can update our answer as well to the whatever length we have found, which is 5. So we will update our answer to be 5. Now again, we will update the value of our r comes over here. Now this is a we don't have any entry, so we will add an entry for a and we will call it as 1. Now in this case, the length is 6. Length is 6, but maximum number of occurrence of x is still 3, which means that now we can do is 6 minus 3. So if we do 6 minus 3, 6 minus 3 is equal to 3. 3x is actually greater than k, which means this condition is not satisfied. So now we will have to update the value of our L over here. So now we will get rid of 1x. So because we are getting rid of 1x, the current maximum occurrence we have so far is 2. Okay, now our left is located at this position. Now the length is 5, and the maximum we can make, maximum occurrence is 2. So again, 5 minus 2 is still 3, which is greater than k. So again, we will have to update the value of our left. So now this time left comes over here, and we will ignore this q, which means the value of q becomes 0. So I'll just remove that entry. Now again, this time the length is actually 4 and the maximum occurrence is 2. So 4 minus 2 is still 2, which is actually less than or equal to k. So because this is less than or equal to k, we know that okay, length 4 is can be our answer, but our answer is already 5. So there is no point in updating length to be 4. Okay. Next, what we are going to do is, now this time we will have to update the value r. So when we update the value r, we actually reach to the end of the string, and because we reach to the end of the string, whatever the value we have stored in the answer, we can return it as our answer. So in this case, the answer is going to be 5 from this sequence, and we can mention that after doing 2 word replacement, the maximum substring we can make that contains all the same characters inside this given original string is actually of length 5, and that is the solution. If we see the time and space complexity for this one, the time complexity will actually be big O of n, where n is the number of characters that are present inside given s. Now you will think that okay, in order for us to find the maximum occurrence, actually we will have to iterate over this entire array, and it might take like there are 26 entries, so we might have to do this work 26 times. But the thing is, we are actually going to use a clever trick over here. What we are going to do is, at any moment we update our right pointer, at that moment only we are going to update our maximum occurrence, because remember, our maximum occurrence can only increase when we update the value of our right. Whenever we update the value of our left, we essentially decrease the whatever the maximum count we have, which means that our maximum count is never gonna go high. So that's why by using this clever trick, we can actually reduce the time complexity to big O of 26 times n to only big O of n, and you will see it in the coding. Also in terms of space complexity, we can conclude this actually 2 times. We can either conclude this to be big O of 26 because we are storing an array of 26 characters, or we can consider this as big O of 1 or constant space, because this 26 is a finite number. This is not an infinite number. So that is why depends on your interviewer how he wants to treat it, and that way you can take it forward. Now let's move on towards coding now. First of all, we are going to create an integer array to store the occurrences, and we are going to name it as occurrence. Now we will create few variables. So first of all, we will create variable left and right, and we will initialize it to value number 0. Now we will create a variable called answer, and we will initialize it to 0 as well. Also, we will initialize a variable called maximum occurrence. Now we will run a for loop on all the characters of given string. So first of all, we will calculate that whether we need to update the maximum occurrence or not. So now we will check that whether the current substring, if that is valid substring or not. So we are going to use an if condition. First of all, we are going to check that whether the length, so in this case length is going to be right minus left plus 1. So if the length minus whatever the maximum occurrence is, if that is greater than k, which means that if that is greater than k, which means that the current substring is not valid. If that is not valid, we will have to update the value of left variable. And we will also have to decrement the value that is located at current left counter on the given string. Once that is done, for every single update, we will have to check that whether our answer is the longest string or not. So we will check that what is the value of our answer. That should be it. So after this loop ends, basically we should have our answer stored in the answer variable, so we can simply return that. Let's try to run this code. This should have an occurrence. Okay, seems like our solution is working as expected. Let's submit this code. Oh, our solution is not working. Oh, we need to decrement the value first before we update this left pointer. So let's try to run the code again. Okay, let's submit it again. Seems like our solution is working as expected. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do minimum window substring problem, and if we see some of the companies where I want to get a job, there are companies like Facebook, Amazon, LinkedIn, Microsoft, Lyft, Airbnb, Apple, Adobe, Google, Snapchat, Flipkart, ByteDance, Spotify, TikTok, Bloomberg, Uber, Pinterest, and Goldman Sachs, who have already asked this question. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem, but it is also a very well liked hard problem. Basically, we are given two strings called s and t, and we are given the lengths m and n respectively for each s and t strings. Now we need to return the minimum window substring of given string s such that every character in t, including all the duplicates, that is the key part, is included in the window that we have created from this s. And if there is no such window, then we need to return the empty string. So if we try to understand this with an example, if we take this example, for instance, we are given a string s that looks like this, and we are given a t that looks like this. Now we need to return a substring in this given s such that this a, b, c is present. Now we don't care about the order of this a, b, c. They can be in any order in the new substring that we are trying to create, but we need to return the smallest substring. So if we see one of the substrings that where this a, b, c is present, we can find a substring that looks like this. If we see this particular substring, for an instance, we can see character a, b, and c is being presented. But the thing is, the question is this the minimum window substring? No, this is not the minimum window substring. Why? Because there exists actually a smaller substring where a, b, c is also present, and we can take one more substring that looks like this. So this substring is smaller than this first one, where also a, b, and c is also present, though they are in different order. But this is again not the minimum substring. There is actually a substring which is b, a, and c, where all the values of a, b, c is present. That is continuous substring of this s, and this is the minimum substring where we can find all the characters that are present in t, and we need to return this as an answer. If we see couple of more examples over here, suppose we are given s is equal to a and t also equal to a, we can simply return a as the substring because that is the only substring we can create. Now if we are given s is equal to a and t is equal to double a, which means that there is no way possible for us to create double a from this single a. So in this case we need to return an empty string. So now since we have understood the problem, let's see that what would be the different approaches to solve this problem. So first of all, I'll show you the brute force approach, and if you directly want to check that what is the optimal solution, I have already provided the timestamp, so you can directly jump onto the optimal solution as well. Okay, suppose this is the s and this is the t we are given. We are looking for a substring inside this given s which contains all the letters of this t, and we need to find the minimum length substring for that. Now we can clearly see that there is one substring HBPO which contains all of the elements that are present in T, but the smallest substring we need is actually OBH, which contains all the elements of this T and that contains the smallest length. The brute force way to solve this problem is that we actually start creating every single possible substring out of this given string S. So we can create substrings like, we will check that okay, this can be a potential answer, we will put it as a potential answer and we will mark its length. Now eventually we would find a substring that looks like this OBH, that is the correct answer, and then we would return this answer as our solution. So this solution will also guarantee to provide us the right answer, but this right answer is actually very costly. Why very costly? Because we know that it takes big O of n square to actually create all the substrings, and for every single substring we will have to check that whether it contains all the elements of T or not, which means we will have to multiply this by the whatever the length of T is, which is let's say m in this case, which means that we are actually essentially doing big O of n cube work to solve this problem, which is very expensive. Okay, suppose this is the example that we are given and we are trying to find that what is the minimum substring inside this given S where all the characters of this T is present. So to optimally solve this problem, we are actually going to use sliding window technique with 2 pointers. So now I have presented the input in a slightly different format, and I have also created that what is the answer we are going to store, because remember in the answer we need to return that what is the minimum substring, and for any minimum substring we need the left pointer and right pointer value, and we also need the length, and we will only choose the minimum length. Now initially we are going to have our left and right both pointers starting at the first position, and now what we will have to check is that we are going to have our right pointer go on the right side until the point where we create a substring where all of these A, B and C are present. The moment we do that, we will note down that what is the answer we have found so far, what is the minimum length, what is the left pointer, what is the right pointer. Once we do that, we will start updating the value of the left pointer to go on the right side until the point when this condition is no longer true and we are not able to make ABC in the given left and right string, and again we will update the process on our right portion, and then again we will try to see that whether we can find a better substring or not. So let's see this approach in action. So now to achieve this approach, what we are going to need is that we already have our 2 pointers left and right over here. Now we need to check that at any given substring whether this T is present or not. So if we for every single substring try to check that whether all of the characters of T is present or not, it takes a lot of time. One quick way to do it is that we actually create a hash map for all the characters that are present inside this value number T, and inside the hash map we note that what is the elements and what are the number of occurrences they have. So in this case, for this T hash map, we actually have 3 characters only and we have 1 occurrence of each of them, so we are going to note it somewhere so it becomes easier for us to record. Now at the same time, for any substring that we create, we will also have to check that whether we have all the satisfied words inside our substring or not. So again we are going to create a hash map for our substring that we are creating as well, and inside the substring hash map we are going to keep on adding the values as we move forward. Now to check hash map every single time is not a very good approach. A better approach in this case could be that we already know that what are the number of unique characters we need inside this hash map. So why don't we just create 2 variables called the number of unique characters. So we just name it as unique that are present inside this T hash map from this given original input, and whatever the substring inside the substring, whatever the unique characters that we have already been able to create. So let's just say that this name is create, and we will keep track of it, right? I'll just show you that how we are doing everything when we keep moving forward on the with our example. So initially left and R both are at this position, and currently we will note that okay, A is not present inside our given substring, so we will add an entry for A, and so far we have received 1 occurrence so far, right? Now originally this T hash map had 3 unique characters, so we are going to note that there are 3 unique characters that we have to find in any given substring, and so far because this current right position is at A, we have already found one of the characters of the required occurrence, right? So we will note down that okay, we have already received one of the characters. Now our right pointer is going to the next element because we haven't satisfied our full condition. So now we identify that okay, this value is actually B, so we are going to add an entry over here inside our substring hash map, and we are are going to say that we have found one occurrence of b, and this one occurrence of b is already also required inside this given hash map as well. So we can note down that okay, out of this 3 required, we have actually found 2 unique characters that are needed, right? We are good so far. Now next thing we are going to do is that again over here we are going to update the value for right pointer. We encounter that this value is actually a, so we are going to add one more entry to our required pointer. So over here we have found 2 occurrences of a, but that does not solve our problem because our unique and create are still not same. So now we are going to update the value of our r again. So now again r is at this position x is not present over here, so we will add an entry for x is equal to 1, but this x is actually not present in this t hash map, so we can't do anything about it. Now again we will going to update our value of r. So r is at this position. Now because r is at this position, remember that this is the value of c is actually 1, c was the remaining value inside this t hash map. Now we have 3 unique characters that were needed, and we have already created 3 unique characters inside this given hash map. So now we are going to treat this substring as our answer, because remember we needed to have the values a, b, c, and a, b, c are actually present over here. This is a, this is b, and this is c inside this given left to right substring. So we have found one potential answer. So first of all we are going to check that okay, what is the length of this one. So length in this case is 0, 1, 2, 3, 4. So length is actually 5, and the left pointer is at 0 position and right pointer is at 4 position, and we are able to add this entry to our answer because we don't have anything before. So that's why we were able to add an entry to our answer. Now we are going to update our left pointer until to the point when this condition is no longer true. So now because previous value of left pointer was over here, and now we jump to this place. So now left pointer is at here, but the moment we updated the left pointer, we will also have to remove the value of our reduce the value inside our substring hash map. So now a there is only one occurrence of a. So far this condition is already true because both this 3 and 3 is matching, right? Now again we are going to update the value of our left pointer to one more character. So now left pointer is over here. Now this b is actually 0. So we are going to remove the entry for b. Now because we remove the entry for b, we have only created 2 elements that are needed inside this substring from this position 2 to position 4, which is a and c. We don't have b entry, which means now we will have to update the value for right pointer until we find the b. Now lucky for us, b is actually very next to this right pointer. So now right pointer is over here and b is actually over here. So b is 1. We will add an entry over here, and now we have already created all of 3 elements needed rather than 2, and we are done with this case, right? So which means we can say that this new substring is also a potential answer. And let's see that whether this substring is actually better than our previous answer or no. How can we determine that? Remember, the aim of this question is to find the minimum length of the substring. So we are going to compare the length of this one. So length of this one is actually 4, and the current answer we had was actually of length 5, which means it is in our interest to update the length over here. And the moment we update the length, we will also have to update the left and right pointer over here. So left pointer currently is at 2 position and right pointer is at currently at 5 position. Now we have found a potentially better answer. Now again we are going to update our left value because we have already found the answer. So now left comes over here, which means we will have to reduce this value of a. So again we are going to reduce the value of a. So a is now 0, so there are no occurrences of a. Because there are no occurrences of a in this new substring, we have only created 2 elements out of this 3 unique characters that we are needed, and which we can see in this particular substring from this position number 3 to position number 5, that we only have c and b, we don't have a. Now we are going to update the value for right pointer. Now again when we update the value for right pointer, lucky for us, we are actually able to find one a. So we will add an entry inside our substring hash set that okay, now we have found one character. Now we can say that we have created all 3 characters that were needed. Now this is also potentially a new substring, and can this be a better answer? So we'll check. Okay, in our length we already have an answer of 4 inside our answer array that we have stored, and this is also an size of 4. So which means that there is no point in updating our answer. We already have the same answer with the same length. So we are going to go to the next case. So now again we increase our value of left. So now left is again at this position. So we will have to ignore this x because we already got rid of it, which means that we have already traveled all the values so far. And now we are at CBA. Now CBA, again this is all of these 3 elements that were needed, and we already have that, which means that this is also potentially a better a better substring that we have found, and the length of this is actually 3. So because the length of this is 3, this can be a better answer. So we will note it down. So this is 3. Now left pointer value is 4 and right pointer value is 6. So we have found a potentially better answer. Since we have already found an answer and we know that this is a valid substring, now we'll have to update the value for left pointer. So once we update the value for left pointer, we are actually going to ignore the C. So now we get rid of the C inside our hash set. Now we also get rid of this L, and now we have taken care of all of these elements so far. Now we only have BA, which means we only have 2 elements out of 3 that we needed. Now again we will have to update the value for right pointer. So again we update the value of our right pointer over here. We find that okay, this value is actually C occurrence is 1, which means we have created this element actually 3. All of this is successful. Now we check that okay, length of this is actually 3. We already have an answer of length 3, which means there is no point in updating that. Now we will update the value for left pointer. We will ignore this B. So if we ignore this B, now we only have 2 elements out of 3 needed. So because we have 2 needed, we will have to update the right pointer. So now when we update the right pointer, we are actually going to be at the end of our string, and because we are at the end of our string, we can actually break out of the loop. And the moment we break out of the loop, which means that whatever the value we have stored inside the answer, we have the left pointer, we have the right pointer. So all we need to do is we need to return the substring. So if we return the substring in this case, we will have to return the substring that looks like this. So the answer in this case is actually going to be CBA, which is the minimum substring that we can achieve that contains all the elements of the T that are present over here. And remember, over here we are using hash map and substring hash map to find the answer. In order to make our lives easier, we have created 2 elements to know that what are the unique characters that we need to compare. In case, because this was a string and we know that there can be only a finite number of unique characters, which is 26, we were able to use this technique. But your interviewer is for sure going to ask you that rather than having a string and having finite number of unique characters, you are actually going to have millions of hash code characters or something like that. In that case, you will not use this technique, and you will actually just simply have to check over the hash map for every single substring that you are going to make. So this is one of the approach where we can find the optimal solution, and it works as expected. If we see the time complexity is actually going to be O of whatever the length of string is plus whatever the length of T is. And why we are able to achieve this time and space complexity? Because we are using this technique. So that makes our lives a little bit easier. If we see the space complexity is also going to be actually big O of the whatever the size of S is plus whatever the size of T is, and this also works. Because we are creating 2 additional hash maps and we need to take care of that space into account. But overall, this is still much bigger improvement in compared to our brute force approach. Now there is one more approach to solve this problem. That whatever the input that is already given, first of all, whatever we create the same hash map we create for this element number T, which means that we actually use the same hash map that I have drawn over here to compare all the values of T. But for this value number S, actually remember that we only need to find the substring of characters that are present in T. But so if that is the requirement, why do we even bother checking this element X or any other element that is not one of these values? So a better way to solve this problem is to create another hash map where we ignore this X and we only keep character inside this given string that are also present inside this given T. And in this particular hash map, we also identify that what is the index value for every single element. So in this case, we will determine that okay, this A is actually present at 0th position. Then again we have a B that is present at 1st position. Again we will mention that there is an A that is present at 2nd position, and so on and so forth. And then it will make our lives a little bit easier and we can solve this problem. But I don't think in an interview, even if you show this approach, they are going to completely reject your suggestion. So that is why I am choosing this one. Let me know in the comments if you want me to solve the other approach as well, where we are only going to use the unique characters that are also present inside this given T. So first of all, we are going to check some edge cases. If the given string is empty, or if the length of the given T is actually greater than length of S. If that is the case, we can simply return as empty string. Now if that is not the case, we will create a hash map to store the value of this t string inside the hash map for all of its characters. We are going to name it as map t. Now we are going to run a for loop across this given string t, and we are going to add all the entries to our map t. After the loop ends, we are going to create a variable called required that gives us the number of unique characters that are present inside our given map t hash map. Now we are going to initialize bunch of different variables to keep track of different things. So first of all, we are going to initialize variable called left and right to keep track of our 2 pointers. Once that is done, we will create a variable called create that defines that what are the number of variables that we have created so far that are also present inside the given t. And we are going to initialize an integer array to store the value of answer, and we are going to initialize the first value as -1 inside the answer, where we are going to keep track of the length of current substring, and we are going to have 2 more entries to store the value of left and right pointer, and we are going to initialize those values as 0 as well. We will also create a hash map to keep track of all the values that we have found so far inside the current substring. And now we are going to run our while loop across the string s, and we are going to run it until the right pointer reaches to the end of the string. So inside our loop, first of all, we are going to add an entry to our hash map for any particular given substring. After adding a value to our substring, now we will check that whether all the elements we have added in the substring is that element also present inside our map t as well. If that is the case, we can increment the value of number of characters that we have created in our substring that are also required inside our map t as well. So if this condition is true, we will update the value of our create variable. Now after updating that, we will also have to check that whether the current substring, if that is valid or not, and by valid I mean that whether the required and create has the same value. If that is the case, we will have to update the left pointer, and we will have to shrink our size. Also we will have to add entries to our answer array as well. So we are going to run another while loop that while left is less than or equal to right, and the required is and created are same. We are going to check that whether we need to update our answer or not, and we are also going to update the value of the character c variable to help us in doing a lot of other things, and we are going to assign it the value of the current left pointer. Now we check if we need to update the answer. After updating the answer value, we will also have to remove the entry from our substring map because we are updating the left pointer. And after removing the entry, again we will have to check that whether the value of our entry that we just removed, did it caused us to reduce our create variable, which means that have we removed any entry which was also present inside our map t hash map as well, which was required for us. If that is the case, we will have to reduce the value of our create variable, and it could make us break out of this loop as well. In any case, we will have to update the left pointer, so we'll update the value of left pointer. And after that is done, we are done with the inner loop. In the outer loop, we will have to update the value of right pointer, and that's it. So basically after this loop ends, essentially we would have taken care of all the scenarios that are needed for this loop, and now we will work on returning the answer. So for the answer, we will have to check that if the value of answer of 0 is equal to -1, which means that we are not able to find any value that were suitable to create as a valid substring. If that is the case, we will return an empty string. If that is not the case, we will return the value inside our answer array for this left and right pointer value, which means answer of 1 and answer of 2. But we will have to do right plus 1. Why plus 1? Because the indexing works from 0 to r, so that's why we will have to add one more entry to our right. Let me try to run this code. Oh, we made some mistake in generating the answer. Okay, seems like our code is working. Let's try to submit this code. and our code runs as expected, and I would be posting this solution in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do valid anagrams lead code problem, and if we see some of the companies where I want to work at who has already asked this question, there are companies like Amazon, Facebook, Spotify, Bloomberg, Microsoft, Goldman Sachs, Apple, Affirm, Google, Tesla, Snapchat, Yahoo, and Uber. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem and also very well liked problem. Basically we are given two strings s and t, and we need to return true if they are anagrams of each other. If they are not anagram, then we need to return false. Now first of all we have to understand that what is an anagram. An anagram is basically a word or phrase that is formed by rearranging the letters and putting them in a different position, and typically we use all the original letters exactly once. So if we try to understand it with an example, suppose we are given a word like bat. So this is the original word. If we just rearrange all of these B, A and T in some other format and keep all of them in the same amount of occurrences they are already present, so we can make some words that looks like TAB, BTA, ATB, TBA, and so on and so forth. So these are all words, they are actually anagrams of this original word bat. And how we can identify that? We can identify based on if we see the number of occurrences of all the characters, they are in the same number of occurrences even in the anagram letters as well. So if we try to understand it further, we're using couple of examples. Over here we are given two examples. So this is the example one. We are given two words that are anagram, and t is equal to something like this. So if we want to check that whether these two are anagrams of each other or not, what we can simply do is we can start cancelling out or comparing the letters. So AA is present, NN is present, again AA is present, G is also present, R is also present, A is also present, and M is also present, which means all of the letters that are present in S, they are also present in T in the same amount of occurrences, which means we can return true in this case, saying that there exists an anagram and S and T are anagram of each other. Now in this case, S is equal to rat and T is equal to car. If we try to repeat the same example, okay, R is present in both, A is present in both, but this T is not present in this string, and this C is not present in this string, which means these are not anagrams of each other, and we need to return false in this case. So let's see that what would be the different approaches to solve this problem. So the first approach to solve this problem is actually a brute force way, and in the brute force what we are going to do is we take this string S. This string is comprised of 3 different characters. So what we do is we make all the possible characters that we can make from this given string S. So we can make characters like A, C, B, B, C, A, B, A, C, C, A, B, so on and so forth. So we would be able to make bunch of different possible words out of this given string S, and then we compare all of them with this given T. And at any point, if we encounter that there exists a word over here which is this BCA is also present in this all the different pairs we created, if that is the case, we will return true in this case. If it is not present, we will return false. So the solution would work perfectly fine. We will get the desired result, but the thing is, our aim is not to get the desired result. Our aim is to get a desired result at a convenient cost, so which is not following for this particular scenario. And if we see the time complexity for the brute force approach, it's actually big of n square. Why n square? Because in order for us to create all of these different pairs, it takes us n square time to do it, and that's why we will have to find a better approach. Better way to solve this problem is that we sort the given string S and given string T, and once we do that, we will get a sorted string, and then all we have to do is just compare these two sorted strings, because if they are anagrams of each other, they should be exactly same. If they are not anagram of each other, they would not be same. So in this case, if we sort the string S, we will get a result that looks like A, B, C, D, and if we sort the string T, we will also get the result that looks like A, B, C, D. And both the cases, since both the strings are same, we can conclude that this is an anagram of each other, and we can return true in this case. If they are not same for any reason, we will return false. So this solution would work perfectly fine, and we will also get the desired result. If we see the time complexity in this case, the time complexity is actually going to be big O of n log n. Why n log n? Because first of all, we will have to convert this string to sorted string, and sorting takes n log n time. So that is the general time complexity. Now this is still a better approach than our brute force solution, which had the time complexity of big O of n square, and we are actually doing much better, and this is a vast improvement on this. Now we will have to check that is there any way to solve this problem in actually big O of n, and yes, there is the problem. Let me quickly show you how. Okay, so for the optimal approach, we are actually going to use an additional data structure array, and we are going to initialize an array of size 26 for the 26 characters inside the English language, and we are going to initialize all the values to have the value of 0 as the beginning. You will understand that I haven't drawn 0, but you understand that default value is going to be 0. Now the idea is we will start iterating over the string s and this string t. For any single character we identify in this string s, we are actually going to increase that corresponding value inside this given array. So suppose we encounter over here this s, then whatever the initial value of this s is going to be 0, we are going to initialize and increment its value to 1. Again, if we encounter the value I, again we are going to increment the value for this I as well. Now inside this t, we are actually going to do things in the reverse order, and we are going to reduce the value. So the moment we identify any single value, we are actually going to reduce that value from this array. And because we are using the same array, if they are anagrams of each other, remember they have the property that their number of characters and their occurrences should be same. So if they both are same, basically we at the end of our iteration, all the characters inside this given array should have the value 0. If at any point we encounter any value where the value is actually greater than or less than 0, we can determine that these two are not anagrams of each other. So after the explanation, let's try to run it with an example. So first of all, we identify that okay, this character is actually s. So initially the value of this character s is going to be 0, so we are going to mark it as 1. And over here this character is actually l, so the value of this l is going to, we will have to reduce it. So for the character l, we are going to mark its value as -1. So now okay, now next character is I. So again we will increase the value of I to 1, and over here this value is I again. So now we will reduce the value of I as well, so the value of I will remain 0. Now our next character is L. So for L we are going to increase the value. So over here if we increase the value becomes 0. And over here the next character is S. For S we will have to reduce the value. So if we reduce the value becomes 0. Now next character is E, and over here it's T. So for E we will have the value increased to +1. For T we will have value decreased to -1. Again the next character is N and E. So for N we will have the value increased to +1, and for E we will reduce one value, so this value will become 0. Now the last character is T and N. So for the T we will have to increase the value. So original value of T is actually -1, so we will increase it to 0, and this value of N is actually, we will have to decrease it. So the value of N currently is 1, so we will reduce it to 0. Now if we see over here, all the elements where you can see that there are some entries, they are the ones that are the number of characters that are present in this S and T, and all of their value is 0, and by default all the other characters inside this given array was also 0. So it becomes much easier for us to determine that whether they are anagrams or not of each other. In this case we can return true that yeah, they are anagrams of each other. This is the best approach and most optimal way to solve this problem. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n. Why big O of n? Because we will have to iterate over all the characters in S and T one time, and then we will have to iterate over this given array one time to determine if all the entries are 0 or not, and both takes n times. So actually we are doing like 2n work, but we can generalize it to be big O of n. In terms of space complexity, well, this you can argue with your customer, with your interviewer, because we are actually using an array of space 26, so it's like big O of 26, which is a constant value, so you can also consider it to be constant as well. Now whenever you will propose this solution inside the interview, your interviewer is definitely going to ask you that rather than this S and T having only English letters which are 26 by a finite number, what if we had a hash code or some other random characters that has millions of value? If that is the case, we will keep track of a hash map, and for hash map every single entry. If we encounter it inside the string s, we will do the increment operation. If we encounter it in string t, we will do the decrement operator, and eventually we would find our answer. So the logic is gonna remain same. This is just the one thing that you will have to understand. Now let's move on to coding. First of all, we are going to check an edge case that if the length of string s and length of string t, if they are not the same, we can return false immediately. If that is not the case, we are going to initialize our array of size 26 and we are going to name it as count. So now we are going to run a for loop across string s and string t, and we are going to increase our counter for any character that is present in string s, and we are going to decrease our counter for any character that is present in string t, and we are going to do both the activities inside the same for loop. For any character that is present inside the string s, we are going to increase its value inside the counter. Character that is present inside the string t, we are going to reduce the value. And after this loop ends, our counter variable should have the correct values. Now we need to iterate over all the elements inside the counter variable, and we need to check that whether is there any value where the counter value of that particular element is not 0. If we encounter any non-zero item, we can return false immediately. And if we break out of this loop, which means we did not find any entries that were non-zero, so we can return true in this case. Let's try to run this code. Okay, seems like our code is working as expected. Let's submit it. And our code is pretty efficient, and I'll be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do group Anagrams LeetCode problem, and this problem has been really popular at some of the companies where I want to get a job. There are companies like Amazon, Microsoft, Facebook, Apple, Google, Affirm, Snapchat, Goldman Sachs, Uber, Bloomberg, Netflix, Instacart, ByteDance, and Twitter have already asked this question. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given an array of different strings and we need to group the anagrams together. Now we can return the answer in any order, so which is good for us. And we are also given the definition that what is an anagram. Anagram is a word or a phrase that is formed by rearranging the letters and then it turns out to be a different word. So if we take an example, suppose we are given a word like bat, then we can say that these all are actually anagrams of this original word bat, because the B, A and T, they are all occurring in all of them in the same number of occurrence that it is present in this bat. So now after understanding that what an anagram is, let's try to see some examples to understand that what this question is asking us to do and what is the expected answer we need to return. If we take this first example, essentially we are given s is equal to array of string that looks like this. Now over here I have clearly marked all the groups that can be potentially done in separate colors, so you can clearly look at them. But the thing is, let's try to understand. So first of all, we are given this word EAT, eat. If we see what are the number of occurrences of characters, there are characters E, A and T occurring 1 times each. Now same thing happens for this word TEAT and for this word ATE8, which means we can conclude that all of these 3 words are actually anagrams of each other, and we can group them together in one single group. So that we are done with all of these 3 elements. Now next item we see there are 2 words tan and net. Again TAN, this all 3 of them are occurring once, these 3 characters for both of these values, so we can also group them together. Now for this BAT bat, we actually don't have any other value that we can consider it as an anagram, so this particular string will be a group of itself, which means in this case we can return an answer that looks like this, and we can return this as an answer. So clearly you would find that this answer, actually the sequencing is done slightly bit different than what is the answer given in this output. And the reason for doing that is that I wanted to show that we can return answer in any order. So that is the important part over here, that is specified in the question, that we can return the answer in any order. So that's why I ordered them differently, but as long as the groups are correct, we are good to go. One better way to solve this problem is actually by using sorting. And how we are going to use the sorting is that we are actually going to create another array for every single entry that is present inside this original S, and for all the elements that are present over here we are going to actually sort them in alphabetical order. And then all we have to do is just we will have to iterate over this newly created array once, and we only need to find that what are all the similar pairs or all the similar values, and then we can simply return them as answer, and that makes our life much more easier. Let me quickly show you what I'm suggesting. So based on this array we will actually create a sorted array, and the sorted array is going to look something like this. So now we have created our sorted array, and which we have derived from this original S. Now all we will have to do is we pick up any word or any string, then we just have to compare with all the other strings and find that which strings contains the same value. Whichever string contains the same value, we will take their values from the original string because we know that they're index values, and then we can group them together. So the idea is, first of all we'll take this string AET, then we find that okay, this and this, both of them, so the strings located at position 0, 1 and 3, they are all part of this original string that should be in the single group. So we will group them together. So in the answer we will mention eat, t and 8 as one group. Then again we will repeat the same process. So we find this ant and ant, so again we will group the whatever values located at this string at this index 2 and 4, and for we find the values 10 and net, and in the end we will return this bat because it's the single one. So this solution would work fine. We will get our desired answer. If we see the time complexity, in this case the time complexity is actually going to be big O of n log n, just to create this original sorted string, multiply by k, and this k is actually the biggest length of the string that we will have to compare, and this would be the final time complexity. So this is much bigger improvement than our brute force approach, which was giving us the big O of n cube time complexity. Now let's see that can we improve any further in this one as well. Okay, before we come to the optimal solution, we will have to ask a very important question, that how do we determine that any two words are anagram of each other or not? Suppose we are given two words like ABC and CBA. We can clearly see that they are actually anagrams of each other, but how can we explicitly define that yeah, they are truly anagrams of each other? Well, we can define that based on the number of character repetition in each one of them. That any character that is present in this ABC, it is also present in the CBA in the exact same number of occurrences that both in both the words. So in other words, A, B and C is present exactly once in this particular word, and it is also exactly once present in this particular word, though the arrangement is different, and that makes them anagram of each other. Now you will ask that why am I dragging so long on this pretty trivial question that we already know the answer to? Well, we are actually going to use it to our advantage, and the good thing for us is that English language only has 26 characters. So because English language has the 26 characters, we are actually going to use it to our advantage. We are actually going to create an array of all the values that are initially located as 0, and that is going to be of size 26. Now any character that we identify in any single string, we are actually going to add it to our array, and we are going to increase the value of that particular character sequence, and then whatever the answer of that array is, we are going to put it in a string, and then we are going to use it as a key for our hash map, and then we are going to do some interesting things. So let me quickly show you that what is the full plan. Suppose over here we are given an array that looks like this, right? Now we have this given word ABC. So what we are going to do is, initially all of these values, they are defined as 0 by default. But now we are given this ABC. So first of all, we take this A, we increase its value to 1. Again, we get this B, we increase its value to 1. Again, we get this C, we increase its value to 1. Now all the other values, they are 0 so far. So for this particular character, we can actually create a string based on this given array of 26 words. So string would be maximum of size 26, which means it is a defined finite number, which means we can create that. We will get a string that looks like this 111 and then remaining 23 zeros. Again, we are given this word CBA, right? So again, what we are going to do, first of all, we identify this character C. So we are going to mark its value as initially this was 0. So we are going to mark it to 1. Again, this B, again, we will mark it to 1. And again, this A, we will mark it to 1. All the other values would be 0. So even for this one, the string that we are going to generate is going to look like this 111 and 000. Now the idea is that we will create a hash map. Now inside this hash map, as a key part, we are actually going to keep track of whatever the string that we are building. So let's just name this as string builder, that we are building a new string. That would be our key. Now in both the cases, notice that for this ABC and for the CBA, this string value is actually going to be the same, that it would be 111 followed by 23 zeros in both the cases, which means that they both have actually same key value, which means that over here, okay, this is 111,000 23 times. But in both the cases, as the value, we are actually going to keep track of a list, and inside this list we are going to store original words that were presented as an input for this original array string that we built. So over here, first of all, we will have an entry that looks like ABC, and then we will have an entry that looks like CBA. Now we already have both the values that is part of the same group, or they are, and which is an anagram of each other, would be in the list value, which means that makes our life much more easier. That in the end, all we need to do is just we need to return this whatever value we have stored in the list. Let's do this with one of the example that we have been following so far. So I'm not going to show you the whole ordeal with the array because that is too time consuming. I'm just going to show you that what would happen inside the hash map. So this is our hash map. Now as a key, we are going to have some string value. So first of all, we get this value eat. So suppose for this value number eat, we get the string that looks something like this, right? Whatever the value is. Now this same value is going to look for this t and for this 8, which means that these values eat, then t and 8 would be a part of the same value group inside this hash map for the same key. Again, same thing will happen for this tan and nat. So even again for this tan and nat, suppose we get some value, that string that looks like this, right? I'm just drawing a bunch of gibberish, but you get the idea. And we will add an entry for tan and nat because they both will have the same number of occurrences of characters. And in the end, for bat, we won't have any entry, so we will have a new entry over here, and where we will add the value bat. Now in the end, all we have to do is just iterate over all the values that are present inside this hash map and return it as our answer. And this would be the optimal solution we are going to use. If we see the time and space complexity for this one, the time complexity is actually going to be big O of n times whatever the maximum length of k is. In terms of space complexity, we are actually creating an additional hash map, so that's why that is going to take some additional space. But this is also going to be big O of n times k, where k is the longest length of any given string and n is the number of string that are present inside the given input. So first of all, we are going to check an edge case, that if the given string is empty, we are going to return an empty array list immediately. Okay, if that is not the case, we are going to initialize our hash map, and we are going to take string as key and list as value. Also, we are going to initialize our array of size 26, and we are going to name it as count. Once that is done, we are going to run a for loop across the given input string. So first of all, we are going to initialize our array with value 0. After doing that, we are going to iterate over this given string s, and we are going to add all the characters inside this given array by adding their value from 0 to 1. After doing that, we are going to initialize a string builder to store the string value that we have retrieved inside this character array. Now we are going to run across the count array, and we are going to add all the values to our string builder. Also at the same time, we are also going to add a hash before all the elements inside this given count array, and that is something per language trick that changes. For Python, you won't have to do it. Once this is done, we are going to assign this new string that we created as a key for our hash map. Now we are going to check that if this entry for this given key already exists inside the hash map. If it does, we are simply going to add whatever the string s that we are iterating over. And if the entry does not exist, we will create one value inside the hash map, and then we will add this value s for this given key. And we are done for this for loop. Now all we will have to do is return all the values from this answer map and return it in the manner that is asked inside this given question. So we will have to return a list of lists. Let's try to run this code. Okay, seems like our solution is working as expected. Let's try to submit this code. And our code works as expected. I'll be posting the solution in the comments so you can check it out from there. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do valid parentheses lead code problem, and this problem has been asked by some of the companies where I want to work at. There are companies like Amazon, LinkedIn, Facebook, Microsoft, Bloomberg, Spotify, Adobe, Google, Apple, Uber, TikTok, Goldman Sachs, Twitter, Netflix, Twitch, Tesla, ByteDance, Lyft, and Airbnb have all asked this question, so that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode easy problem and also one of the most liked problems on LeetCode, and that is because this problem actually solves one of the very real life application where a compiler has to check that whether the code has valid parentheses or not, and so that's why a lot of companies like to ask this problem as an interview question. If we understand the problem, basically we are given a string S that contains just these three types of parentheses: opening parentheses and closing parentheses, and we need to determine that if the given input is actually a valid input or not. We are also given the definition that what counts as a valid input, that if the opening brackets are closed by the same type of closing brackets, and also we are told that the opening brackets must be closed in the correct order. So let's try to understand this with some examples over here. I have drawn a bunch of different potential examples, and we will see that if they are valid or not. So first of all, if we see this example, we know that okay, we have two opening brackets and we have two closing brackets. We can consider this as a valid string, so I'm just noting it as V. Now again, in this case we have two different types of opening brackets and we have two different types of closing brackets, so this is also a valid string. Now in this case, this is an opening bracket, this is an opening bracket, we have corresponding closing brackets. Again we have opening and closing brackets, and again we have opening and closing brackets. So everything is in order and the same kind of brackets are opened and correct in proper shape and size, so we can consider this also as a valid format. Now if we come to this example, this is an opening bracket, this is also an opening bracket, but we only have a closing bracket for this original opening bracket, so we can consider this as invalid option. So we get an idea why it is invalid. In this case we have three opening brackets and only one closing bracket, so again this is an invalid string. And in this case, actually if we see the number of opening brackets and number of closing brackets, they are actually same. So we have one opening bracket and one closing bracket, again one opening bracket and one type of closing bracket, but this is still invalid. Why it is invalid? Because this bracket, this curly bracket, is actually opened before this particular round bracket, so that's why it has to be closed before this round bracket closes. And in this case, this round bracket actually closes first before this curly bracket is being closed. So this is very important property that we will have to keep track of, and that is why we are told that we need to keep track of the order in which they are opened and closed, and then only we can determine that whether they are valid or not. So this is also an invalid formula. So let's see that what would be the potential solution. So let's start from the very simple example and see that what would be the intuition behind building a solution. Suppose we are given an example that looks like this, where we are given all of the brackets that are of the same kind and we are given some opening brackets and some closing brackets. Well, we can clearly see that this is a valid approach, and how we can determine is that we can actually create a counter. And what this counter does is that at any given moment we identify an opening bracket, we are actually going to increase the value in this counter, and at any given moment if we encounter a closing bracket, we are actually going to decrease the value in this counter. And at the end we have to check that whether the value inside this counter, if that is equal to 0, which means we can determine that the same number of opening bracket and closing brackets are present, and then we can say that the string is actually valid. If that is not the case, we can say it is invalid. So if we see that in action, first of all we have three opening brackets, so we will increment the value of this counter 3 times, and if we do that we will get the counter value to be at 3. Again, now we identify a closing bracket, so now this value from 3 becomes 2. Again we identify two more closing brackets, so again it gets decreased 2 more times, and then we get the final counter value to be 0. And because we get this value as 0, we can say that okay, this string is actually valid string, and the same number of opening and closing brackets are happening. So this is one way to identify a solution, but in this case the complexity is actually very simple. Why? Because we are only using one kind of opening and closing brackets. In our original problem we are actually told that there are 3 different kinds of opening and closing brackets, and we will have to keep track of them. Also we need to keep track that in what order they were opened and closed, and that order also has to be maintained. So it is not just as simple as keeping track of counter, that we create 3 different counters for all single type one of them, and then we see that at the end whether this value is 0 or not. We also have to keep track of that what is the order they were opened in and they were closed in. For the optimal solution, we know we need to take care of two things. First thing is we need to check that whether the opening and closing number of brackets are same for each three different types of parentheses or not. Second thing we have to take care is that what is the order in which they are opened and closed. So first let's tackle the first problem. We know that for every single opening bracket there has to be a closing bracket and they are always in pair. So now to quickly look them up, we are actually going to use a hash map. Now inside our hash map, we are actually going to have all of these closing brackets as the keys and their opening brackets as corresponding values. So we are going to have three entries. Now we have to take care of their order and number of occurrences. So the idea is we are actually going to use another data structure called stack. And the stack is actually going to be very helpful to us. So let's try to understand this with an example that how we are going to use the stack over here. Suppose we are given an input that looks like this. Okay, so I'm going to show you two examples on how we are going to solve this problem. So first let's take this example, and the idea is that at any given moment we identify an open bracket, we are going to add that value inside our stack, and at any moment we are going to encounter a closing bracket, we are going to pop a value on from the stack, and then we are going to see that whatever the value we popped out, if that is the same value that is for any given hash map value we have inside the string for that particular closing bracket. So let's see that in the action. First of all, we identify these three opening brackets, so we are going to add all of the entries inside our stack. So first we will add a curly bracket, then we will add these two brackets. Once we are done with this one, now we have a closing bracket our hand. The moment we identify a closing bracket, remember we will have to pop the value out of our stack. So we are going to pop the value out of the stack, and the value we have popped out is actually this one. Now for this closing bracket, we are going to see that what is the value of that bracket inside our hash map, and the value of that bracket is also like this, and we are going to compare these two elements, that whatever we took out from the stack and whatever we got from this hash map, and both are same. So because both are same, we can say that okay, we are good so far. And now so far we have actually taken care of these four elements, and now we are on this element. Again, this is also a closing bracket, so because this is also a closing bracket, we will have to pop a value out, and we are going, if we pop a value out, we will get a value that looks like this, where we are arrived from our stack. And now we are going to check that for this particular bracket that we were iterating over, what is the corresponding value inside the hash map. So the key is this one and the corresponding value is this one. So the value we found from our hash map is also this one, and they both are same. So because they both are same, we can say that okay, we are good up until this point. Now we are iterating over this curly bracket, so we again pop, and also I have forgot to delete this value. Now again we pop out a value from our stack, so now we don't have this value over here, and we have a bracket that looks like this. Again, for this closing bracket, the value inside our hash map is also an opening curly bracket, and both are same, so we are good up until this point. Now we are only up to last two characters, so this is also an opening bracket. The moment we identify opening bracket, we will add an entry to our stack, and now this is a closing bracket, so again we will pop this entry out. After popping this entry out, so this is the value we popped out from the stack, and then we will compare from our hash map. So the value is this one, and both are same. So we are at the end of our string, and because we are at the end of our string, we are going to check that whether inside the stack we have any entry or not. We don't have any entry, so we can return true in this case, and we can say that the given string is actually valid, and this would be the answer. Now let's take one more example where the string is not valid and see that what we are going to encounter in this case. Suppose we are given a string that looks like this. So in this case, we have two opening brackets and one closing bracket. So first of all, we identify that this is the opening bracket. We are going to add an entry over here. Again, we encounter an opening bracket, we are going to add an entry over here. Now we encounter a closing bracket. The moment we encounter a closing bracket, we are actually going to pop out the value from our stack, and the value we popped out is actually a curly opening bracket. Now for this closing bracket, we actually have a corresponding value inside our hash map that looks like this one. Now these two are actually not same. So the moment we identify that these two are not same, we can immediately return that this string is actually invalid and the parentheses are not in correct order. So we are done with this one. Time complexity is actually going to be big O of n, where the n is not the number of entries present inside the string, and even in terms of space complexity, because we are using a stack and hash map, but we don't care about hash map because it has finite number of entries. But for the stack, the values will be dependent on big O of n as well, on the number of entries present inside the string. Now let's move on to coding. So first of all, we are going to initialize our hash map, and inside the hash map we are going to store the values for three different brackets that we are given. Okay, we are done with this one. Now we are going to initialize our stack and we are going to name it as stack as well. And now we are going to run a for loop across the given string. So first of all, we are going to initialize a character C, and that is to keep track of whatever the character we are looking over inside the given string. Now we are going to check that if the current bracket is opening bracket or closing bracket, which means that if the key value is present inside this mapping bracket, then we can define that it is a closing bracket. If not, then we can define it as an opening bracket. So if the value is not present inside this mapped bracket key, which means that we will have to push the current value inside the stack. If not, which means that the value is actually a closing bracket, and then first of all we are going to pop the value out of our stack, and then we are going to compare it with whatever the value pair inside the map bracket we have. And if the stack is empty, we can return false immediately. So in the else condition, we check that if the stack is empty, we can return false immediately. If not, we are going to pop out a value from the stack, and we are going to name it as top element. And now we are going to check that whether that is the same value that is present for the map bracket value key. And if the values are not same, we can return false immediately as well. And if that is not the case, eventually if we get out of the loop, then we will have to check that whether the given stack is empty or not. If the stack is empty, we can return true, or else we can return false. Let's try to run this code. Okay, seems like our code is working as expected. Let's submit the code. And our solution is actually pretty fast compared to a lot of other solutions. So I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do valid palindrome LeetCode problem, and if we see some of the companies where I want to work at who has already asked this question, there are companies like Facebook, Amazon, Microsoft, Apple, Bloomberg, Spotify, Adobe, TikTok, Google, and Uber. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem, and basically we are given the definition of what a palindrome is. We are told that after converting all the uppercase letters into lowercase letters and removing all the non-alphanumeric characters, if the string reads same as forward and backward, then we can determine that any given string is a palindrome. Now we are given a string S, and we need to return true if the given string is palindrome. If not, we need to return false. So let's try to understand this with an example. Over here we are given a string that looks like this, where you can see that there are some alphanumeric characters as well, which we will have to get rid of. This is only put there just to add some sort of additional complexity. Apart from that, it serves no purpose. This is the original string that we are given. Now if we convert all the uppercase letters to lowercase and remove all the alphanumeric characters, we will actually get a string that looks like this. And if we see for this particular string, if we start going from the front and even going from the back, we will see that all the characters that are present from the front, they are also present from the back in the same order. So that is why we can determine that this string is actually a palindrome, and we will return true in this case. We are given another example that looks like this. Over here we can also see that there are some alphanumeric characters which are the two space values, so we will have a string that looks like this. And over here, if we try to see that whether this is a palindrome or not, currently this R matches, A matches, C matches, but this E actually does not match over here, and over here actually we have an A. So that's why this is not a palindrome, and we will return false in this case. So let's see that what would be the approach to solve this problem. Now suppose this is the example that we are given, and we need to determine that whether this given string is a palindrome or not. The approach I'm suggesting is, first of all, we iterate over this given string. We get rid of all of these characters that are alphanumeric. Once we do that, then we will create a new string that is actually reverse of this original given string. And now we have two strings at our disposal. All we have to do is compare both the strings. If they are same, we can determine that they are actually palindrome, and we can return true. If they are not the same, we can return false immediately. So let's see that in the action. So first of all, we are going to create a string from this original input string, where we are going to get rid of all of the non-alphanumeric characters. Once we are done that, now we are going to reverse the string. So we are going to create a new reverse string from this original given string, and we are basically reversing whatever this given input is. In this case, if we compare this given reverse string and whatever the string we are given, they both possess the same value, which means we can determine that this given original input is actually a palindrome and we can return true in this case. So this is one of the solution where we can work with, and this solution would work as expected, no issues with that. Let's see that what would be the time and space complexity over here. So for the time complexity, actually first of all we are iterating over this given string to remove all of the alphanumeric characters, and then again we are iterating over this given string to create a new reverse string, which means that we are essentially iterating over this original string 2-3 times and comparing it, and basically we are doing big O of n work, but actually we are doing like big O of 2 times n work. In terms of space complexity, because we are creating this new original reverse string, so that is why we are also consuming some space. So that's why the space complexity in this case is also going to be big O of n, where n is the number of characters that is present inside this given string. So this approach is okay, it's justified, it works as expected, but the question is, can we do something better in terms of space complexity and even in terms of time complexity? And yes, there is a better approach, and let me quickly show you how. Okay, so for the optimal solution, what we are going to do is, suppose we are given an input that looks like this. Now over here we are actually going to use a 2-pointer solution, and we are going to have a left pointer and a right pointer, and initially the left pointer is going to be located at the leftmost position and right pointer is going to be located at the end of our string. Now at any given moment we are going to compare that what is the character value of left and right pointer, and we are also going to check that whether this given left and right pointer, if there is that like a non-alpha numeric value. If that is the case, we will just like increase the value of left or right pointer, and if both the values are same, essentially we will move the left pointer on the right side and we will move right pointer on the left side, and we would keep on doing this process until left and right are adjacent to each other before right crosses the left. And if we are able to reach to that point, we can determine that this is actually a true and valid palindrome. If that is not the case, we will basically return false at any given moment if we identify that left pointer and right pointer character values are not matching up. So let's see that in action. Suppose this is the string we are given. Currently the left is located at this m and right is located at this small m, but in both the cases we are only dealing with lowercase English letter. So even if we encounter an uppercase English letter, we would convert it to lowercase English letter. We would treat it like this. So this m is equal to m. So far we are good, which means we will have to update the value of left and right pointer. So now this left pointer is going to go to the next value, which is over here, and this right pointer is going to go to a previous value, which is over here. Now at this position right, we actually identify that this is not an alphabet, so we would again update the value of right pointer and we would ignore this case, and this time right pointer comes over here. Now because both of these are valid alphanumeric value, we will try to see that what are their values, and both are located a, which means they are same. So if they are same, again we are good up until this point. Again we will update the value of left and right pointer. So now left pointer is at D and right pointer is actually located at this column over here. So because this is not an alphanumeric value, again we are going to ignore this and we are going to update the value for right pointer. So now right pointer would end up at the same position where left pointer is. If we again compare the value, both are going to be DD. So again we are good up until this point. Now we don't have to do it, but because in our algorithm we are specifying that we need to check before right pointer crosses the left, and in this if we do one more iteration, essentially right would come and left would come over here, which means that they would be crossing each other, and which is not what we want. So we have already concluded that all the characters inside this given string, they are actually part of a palindrome, and we can return true in this case, and this is the approach we are going to take. Now if we see the time complexity in this case, the time complexity is actually going to be big O of n only, because we are completing everything in just single iteration. We are having our left pointer move to the right side and we are having our right pointer move to the left side, and we stop when they meet. Now in terms of space complexity, we are actually doing it pretty efficiently. We are only using couple of pointers to store in our space, so that's why it's only a constant space that we are consuming, and this approach is much better approach, and we will conclude this as to be an optimal solution. Now let's move on to coding. First of all, we are going to initialize couple of variables called left and right, and we are going to assign the left to be value 0 and right to be value to the end of the string. So now we are going to run a loop that while left is less than right. So now first of all we are going to check that if the current value on the left side, if that is not alphanumeric, we will have to update the value of left pointer. Same thing we are going to do with the right pointer, but we are actually going to reduce the value for the right pointer. And if we identify that both left and right are correct letters, we are going to check their values, and if they are not same, we can return false immediately. If they are same, we will continue updating the loop. So if that is the case, if the characters are not matching, after converting them to lowercase, we can return false immediately. And if that is not the case, we would update the values of left and right pointer. And once this loop ends, essentially if we get out of the loop without returning false, we can simply return true. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code is actually pretty efficient. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop LeetCode until we get there. Today we are going to do longest palindromic substring LeetCode problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Google, Adobe, Apple, Bloomberg, Goldman Sachs, TikTok, Uber, ByteDance, LinkedIn, Tesla, and eBay. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and also one of the very well-liked problems on LeetCode. Basically, we are given a string S and we need to return the longest palindromic substring that is present inside this original given string S. So in order to understand this problem, first of all, we'll have to identify that what is a palindromic string. And a palindromic string is basically, as the name suggests, any string that forms a palindrome. And we know that palindrome is any string where if you read it from left to right or right to left, the number of sequences is same. So in this case, ABA is actually an example of a palindromic string. Also ABBA is also an example of palindromic string, because in either of these two cases, whatever side you decide to move along, the number of character occurrences remains the same. So that's why they are palindrome. And now our aim is to find the longest palindromic substring inside this given original string S. This is not a very good example to understand, so let me create a custom example. In this case, we need to find that what is the longest palindromic substring. So if we see the string S by itself, it's actually not a palindrome. But if we see these three values A, B, A, and we get rid of this B and D, we can actually create a palindrome, which means in this case, we can return the answer as A, B, A to be longest palindromic substring that is present inside this given string S. And this is exactly what we need to return. So now let's see that what would be the different approaches to solve this problem. In order to understand the brute force way, we'll have to identify that what is the thing we need. We need the longest palindromic substring that is present inside this original given string S. So the aim is that we need to find a substring. So why don't we just use the brute force method and we find every single possible substring that we can make out of this given example S. So we can make bunch of different substrings. Let me just draw some substrings over here. So these are some of the substrings that we are able to generate from this original given string S. Now our aim is to find that what is the palindromic substring. If the substring is palindromic, we will find its length and then we will try to find the longest palindromic substring in that way. So we can clearly see that in this case, this ABA is going to be the answer for this longest palindromic substring, and eventually we would be able to find the solution using the brute force method. But what is the issue with this? Like, issue is actually pretty evident that even for this 4-character string, we actually had to create bunch of different substrings, and out of all of those substrings, we will have to find some effort and resources to find that what is the longest palindromic substring. So that is just waste of time and energy. If we see the time complexity, in this case, the time complexity is actually going to be big O of n cube. Why m cube? Because it takes n square time just to create these substrings. And after doing that, we will also have to identify that whether those given strings are actually palindromic substrings or not, and which is the longest amongst all of them. So that also takes n time. So that's why the overall we can write it as big O of n cube time complexity. So let's see that what would be the better approach to solve this problem. Well, before we come to the optimal solution, first let's build some intuition behind achieving that optimal solution. The idea is that we need to find the longest palindromic substring. Now there are two possibilities. We could have an odd number of string that is a palindrome, or we could have an even number of string that is actually a palindrome. Now in each cases, the middle value is actually providing some interesting results. And the thing is that in both the cases, the palindromes are actually built around these middle values. How? Let me quickly show it to you. Well, if we just take this madam for an example, over here we can actually conclude this D to be a substring in its own, and because this is a single character substring, we can actually conclude this to be a palindrome as well, because if we read from this left direction or right direction, in each cases we are going to get the same result. Now if we add these two A's to this D, we will also get the substring that looks like this A, D, A. Now in each cases this D remains common, but the left value and the right value, because they both are same, we can conclude this string to be a palindrome as well. Now again, if we repeat the same process and we add this M and M, again because they both are same and we are adding at the corners, so if we add them, we will get a value that looks like this. Now this D originally was a palindrome. After adding this AA, it remained palindrome because both character had the same value. And again after adding this MM, again the whole thing remained the palindrome because they both had the same value. Now in this case, if I extend and if I add a value that looks like X and Y over here, so this X and Y is actually not same, so this whole thing will not be a palindrome, but this middle portion will actually be a palindrome. And in this case, because we had odd number of characters that are forming a character, we actually have just one value that we can consider as middle value, and all the other values from this middle value are actually just a bunch of set of characters who both have same values. Let's take an example for this even number case. Now in this case, actually we have two middle values, and the two middle values are BB. Now if we were to consider this BB, this is actually a palindrome in itself, because again by definition, even if we go from left or right, in each cases we are reading the same value. Now again this AA, both are same value and they are actually same value that corners our original given middle values. So if we form a value that looks like this BB was already a palindrome, and the two values we added, they are also same. So because they are same, this whole thing actually becomes a palindrome. And again, just like this case, if we add an X and Y over here, this whole thing will not be a palindrome, only this ABBA would remain palindrome. So now after knowing this solution, actually it becomes really easy for us to identify that what would be the optimal solution. Suppose this is the example that we are given and we are trying to find the optimal solution for that. So what we are going to do is we are actually going to expand on the corners, and we are trying to see that whether the left and right value of any middle value, if they are actually same or not. If they are same, we can consider the whole part to be part of any palindrome. If they are not same, then we will move on to the next value and start doing the same process. Now there could be two possibilities. We could have an odd length palindrome where we will only have one middle value, or we could have an even length palindrome where we will actually have two middle values. So in each cases we will have to take care of them. So I'll be showing you the odd example first, and then I'll show you the even example. And basically it's slightly different idea, and I'll just show you when we go there. So first of all, we are going to take this value X. Now we are going to expand upon the corners. So we are going to see that whether this X could be the middle of a longest palindromic substring. If that is the case, then we will expand upon this X. So we will try to see its left value and right value. The left value is actually null and right value is actually M. Now this left and right, they are not same, and also this middle value is actually not same with this right value, and it's also not same with this left value, which means in each cases this X is actually not part of the middle of longest palindromic substring. So we will get rid of it and we will move on to the next value. Now we are at this value number M. Again we try to see the what is the left and right value. Left is actually X, right is actually A. Again they both are not same and none of them are same with this M, so which means that now we will move on to the next value. Next value is actually A. Again the left value is M, right value is D, nothing is same, so we will move on to the next value because this is also not a part of the palindrome. Now we are at this position number D. Now if we take the left and right value, the left value is actually A and the right value is also actually A. So because this left and right value is same, this D could be a middle of any palindrome. We don't know if it is the longest palindromic substring or not. Now the longest palindromic substring that we have found so far is actually of length 1. Why length 1? Because any character in itself is also a palindrome, remember that. So that's why now we have this new substring that looks like this ABA. This is also a palindrome, and we will try to see that whether it is longer than whatever the existing palindrome we have, which is true that this ABA is actually longer. So we will have to update the value of this AB over here, saying that this is the longest palindrome we have found so far. We will keep on expanding on its corner. So far the values we have is ABA. Again we will move on a left and right pointer. So this is M and this is also M. So because they both are same, again we can consider this to be a palindrome. And the previous longest palindromic substring we had was ABA, but this is actually greater than that, so we'll update its value. And now the longest palindromic substring we have found so far is Madam, MADAM. Now again we will go and repeat the same process. Over here we will have the value Y, and over here we will have the value X. So these two are not same. So because these two are not same, now we are no longer forming a palindrome, so we will have to get out of it. So we will just move on to the next value, and if we move on to the next value is actually A. So again this A, the left value is D and right value is M, so this is not a palindrome. We will go back to M. M is also not part of any middle of any palindrome, and this Y is also not part of any middle of the palindrome. So now we are done for our example so far. And in this case, whatever the answer we have found over here for the longest palindromic substring, which is MADAM, we will return this as our answer, and this solution would work as expected. Now this was the case of odd number of palindrome that is being the longest. Let's see the even number of palindrome. So in this case, again we are going to repeat the same process. First of all, we'll take this X, we take the left and right value. Again we don't find anything interesting, so we'll move on to the next value. Now next value is A. Again we check left and again we check right. We don't find anything, right? So we'll move on to the next value. Now again we are at this position number B. Now we are at this position number B. If we check the left value, we find A, but if we check the right value, we actually find another B. So because these two are same, actually the combination of these two B's could be the middle of the longest palindromic substring, and that is going to be true in this case. So we are going to expand on a little bit differently now. Now we are going to have this BB as the middle of the longest palindromic substring we have found so far, and we will repeat the same process. So we will try to find that what are the left and right values. So left value is A and right value is also A. So again this is A, B, B, A, because these two are same, and this middle portion we are just consider it to be the middle. So this is also forming a palindrome, and the longest palindromic substring we had so far was only of length 1, and then when we found this BB, it become of length 2, and now we have this ABBA, so this is of length 4. So because this is of length 4, we will have to update the longest palindromic substring we have found so far to be ABBA. Now again we will repeat the same process. So if we again go left and right, this is actually X and this is Y. So now these two are not same. Because these two are not same, so now we will just get out of it. We will again check with this A and Y. We don't find any palindrome, and we would be done with this one. So in this case, we would return this ABBA as part of our answer, and that would be the final solution. So the time complexity in this case is actually going to be big O of n square. Now why n square? Because we will have to iterate over every single value to see that whether that is the middle of the longest palindromic substring or not. That takes n time, and if we will have to iterate over all the values on the left and right side to see that whether it's the longest palindromic substring or not, which means that in the worst case scenario, we might have to iterate over n square times to find the answer. In terms of space complexity, we might have to keep track of big O of n characters at any given moment, where n is the number of characters present inside the string. Now this is actually a much bigger improvement compared to our brute force approach, which had the time complexity of big O of n cube actually. And now let's move on to the coding. First of all, we are going to check some edge cases. If that is not the case, we are going to run a for loop across the given string. For the any value we are iterating over, we don't know that whether it is the middle of the longest palindromic substring of an even length or of an odd length. So at any given time, we are actually going to have two variables that call a function, where we are going to check that whether the odd length or even length palindromic substring, can it be the middle of any palindrome. And so first I'll create two variables and we'll name it as len1 and len2, and we are going to call a function called check palindrome. Inside this function, we are going to provide the value of given string s, current position of I, and we are considering this to be an odd length, so that's why we are considering I to be the middle element. Also, we are going to create a variable called length2. We are again going to call the check palindrome function. We are providing the value of string s, we are also providing the value of I, and we are also providing the value of I plus 1. Why plus 1? Because remember that in the even length palindrome we actually have two middle entries, and that is how we are going to do it. And also we are going to have a variable called length, where we are going to keep track of the maximum length of palindrome we have found so far. Remember that amongst these len1 and len2, at any given moment, if we identify that there exists some valid palindrome and we have found the maximum value, we might have to update the value of the maximum variable. So we are going to check for that condition as well. For that we actually need two pointers called left and right, and we are going to check that whether the given length we are getting, if that is greater than the left and right length we have already found so far. The thing is, we haven't declared these variables yet. So first of all, let me quickly declare these variables, and we are going to initialize their values as 0. We are going to update the value of the left pointer, and that will be decided based on the value of I. So we are going to do I minus whatever the value of current length we have found. We need to do it divide by 2. The thing is, we don't know that whether that length is odd or even, so we will subtract it by one value and then we will divide it by 2. So in any case we will get the correct result for the left pointer. And for the right pointer, we are actually going to do I plus whatever the length we have found divided by 2, and this should give us left and right pointer to create the desired substring. And after we run out of the loop, we will simply return the substring. So now we are done with most of the logic in the main method. Now we'll just have to create this check palindrome method. So let's assign the value L and R for the ease of our use. Now we are going to run a while loop that until the point when we have a valid palindrome, we will keep on reducing the value of left and updating the value of right, and we will check that whether both values are same or not. We'll also take care of some edge cases. While the existing value is a valid palindrome, we will reduce the value of left pointer and we will update the value of right pointer. This while loop, we will return the whatever the length we have found so far. This should do it. Let's try to run this code. We will have to update the value of this right pointer by 1. Let's try to run the code again. Okay, seems like our solution is working. Let's submit the code. And our code works as expected. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do Palindromic Substrings lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Facebook, Amazon, Twitter, Google, Microsoft, Uber, Goldman Sachs, Apple, Bloomberg and LinkedIn. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given a string s and we need to return the number of palindromic substrings that exist inside this given string s. Lucky for us, we are given the definition that what a palindrome is. Basically a palindrome is a string that reads the same from backwards and frontwards. So suppose we are given a string like this GG. If we read it from the backwards or frontwards, in both the cases the answer remains the same. Also one more example, ABA. This is also an example of palindrome because in either case we read it, the answer remains the same. Now a quick question for you guys, that whether this character B, is this an example of a palindrome or not? And the answer is yes, this is also a palindrome. Why? Because if we read it from the left and also read it from the right, we get the same result. But if we are given a string that looks like this AB, this is not a palindrome because if we read it from the left and from the right, the answer is not the same. So these are some of the examples of a palindrome. We are also given the definition of a substring, but I don't think that it is necessary to define. It is actually pretty trivial. Now let's try to understand this problem with an example. Suppose we are given a string S that looks like the CABA. Now in this case, we need to find that what are the number of palindromic substrings that exist. So we can clearly see that we have a palindromic substring that are These four characters are actually palindrome in itself, because as I mentioned earlier over here, that even a single character is also a palindrome in itself. So we already have four palindromic substrings so far. But if we notice over here, we also have one more palindrome, that is this ABA, and that is also a palindromic substrings, which means that in this case we need to return 5 as our answer, that we can actually make 5 palindromic substrings for this given string s, and this is what we need to return. So let's see that what would be the different approaches to solve this problem. Suppose this is the S we are given, and we need to find that what would be the brute force solution for this problem. Well, we have to understand that we need to find all the existing palindromic substrings that are present inside this given string S, which means we need to find the substrings. So what we can do is we will make all the possible substrings that we can make from this given S, and then we will check that whether that substring is a palindrome or not, and simply we will get our desired answer. So if we see that in action, for this particular string, we can actually make substrings that looks like these. So these are all the substrings that we can make from this given string S. Now all we have to do is check that whether any given string is a palindrome or not, and in this case we will find that these four strings are palindromes, and also this string is a palindrome. All the other strings are not palindromes, and then in the end we can return 5 as the answer for this problem, and that would be a valid answer for this problem. But what is the issue with the brute force approach? Well, the issue with the brute force approach is that the time complexity in this case is actually going to be big O of n cube. Why n cube? Because it takes n square time just to make these substrings, and then it takes n time to check whether a substring is a palindrome or not. So cumulatively this is a very bad time complexity, and we will have to find a better approach. So before we move for the optimal solution, first of all we'll have to build some intuition behind it, that how to identify a palindrome. Well, in the palindrome there could be two possibilities. The palindrome could be of odd length or it could be of even length. First let's see that what would be the scenario in the odd length. So suppose we are given this character O. This is a palindrome in itself. We have already identified that, because if we read it from left or right, we get the same result, right? Now if I decide to add two more characters XO, XX at the edges, this still remains the palindrome, which means that because both of these x's were same, and this middle value was a palindrome in itself, this whole thing actually became a palindrome. Again, if I take it even further, if I add two more characters BB, again this whole thing still remains a palindrome. And if I keep on adding same values, as long as they are same, this will always remain the palindrome. But the moment I add a value that likes A and B, now this whole thing is not a palindrome, because these two values are different. But this portion is still a palindrome, and also the smaller portion still remains the palindrome, which means we can define that the palindromes are like an onion, where the middle value remains the same, and because of the middle values, all the other subsequent values where the values are actually same, the palindromic property is sustained. Why I'm giving so much explanation for that is you will see it in the optimal solution. And in the odd cases, we only have one value as the middle character, but inside the even character, suppose we are given a value like BB. So this is a palindrome in itself, and both values are same. Because both values are same, this is an even length and this is an even length palindrome. Now again I decide to add two more characters XX. Because they both are same, this still remains the palindrome. Again I add value AA, this is also a palindrome. But the moment I add a value that is different, like X and Y, now this whole thing is not a palindrome, but this middle portion still remains a palindrome. So that is the important property, that in case of odd length, we have a middle character of the palindrome that is a single character, and all the other characters has the same value. In case of the even length palindrome, we have two characters that are same. So that is important, two characters, they are both same, and then all the other characters, they are also same as well, and a smaller palindrome is forming a larger palindrome. And let's see that how can we use this property to find an optimal solution. So suppose this is the example we are given, and we need to find the optimal solution for that. The idea is that at any given character, we are actually going to see that whether could this be a middle of any palindrome, and if it is the middle of the palindrome, we are going to keep on expanding our palindromic search, and we are going to keep adding our answer result. First of all, let's see for this character number C, that can this C be part of any middle of the palindromic substring or not. Well, we already know that this C is a substring in itself, because if we read it from left or right, we get the same result. And we are also going to have a variable called answer, so initial value was 0. Now because this C is a palindrome in itself, we are going to add the value to our answer as well. Now we are going to see that whether the C is a middle of the palindrome or not, which is not. Why? Because if we see the left of the string and right of the C, this is actually a null value and this is A, which means both are not same. So because both are not same, this is not part of any middle of the substring. Now we are going to have this value a. Again we are going to repeat the same process. Well, a is a palindrome in itself, so we are going to add the value to our answer first of all, so this becomes 2. Now again we are going to check that whether this a is the middle of any palindrome or not. We also have to check for both the cases that could this be of odd length palindrome or an even length palindrome. So for odd length palindrome, like the both left and right value would be same, and for even length palindrome the value would be same with that itself. So first of all we are going to check with this a. So the left value is c and right value is actually b, so both are not same. Also they are not same of this a and b, which means this is not an odd length palindrome and even length palindrome, so we are good to go. Now we will move on to the next value b. Now this next value b is a palindrome in itself, so we will update the value inside our answer to 3. After doing that we are going to check that could this be the middle of any palindrome or not. So we will check the left and right value. Left value is a and right value is also a. So because these two are same, we can define that this b is actually part of the middle of the palindrome, which is of odd length, and we are going to keep on expanding our palindrome. So now this b a b, so sorry, now this a b a is also palindrome, so we will update our answer immediately. So answer becomes 4 now. Now again we will keep on expanding our palindrome. So if we do a left and right over here, the left value is c and right value is actually null, so these two are not same. Because these two are not same, we no longer have a palindrome, so we will break out of the loop. Now again we still have one more character left to check. So again we will check for this value number a. So a is a palindrome in itself, we will put the answer as 5. Then again we will check that whether this a is that a middle of any palindromic string or not. So we check left and right value. Left value is b and right value is actually null, which means these two are not same and they're not same of this a as well. So immediately we will break out of the loop and we can return, and the next value over here is actually null, which means we don't have anything. We have reached to the end of the string. So this is the answer we need to return in this case, that 5 would be the answer, and we will return that. Let's see one more example s, where we will find the even length palindrome. So over here again we are going to repeat the same process. So first of all we'll take this character number c. Can this c be part of the any middle of the substring or not? So this is not part of any middle of the substring, and we will have an answer variable. So first of all we'll initialize it to 1 because c is a substring in itself. Now we'll move on to the next value a. So a, where a, if we check the left and right pointer, left is c and right is b, so these two are not same. So immediately a is also not the middle of any new palindrome, but it is a palindrome in itself. So again we will update the value to 2. Now again we are at this position number b. Now at this position number b, if we compare left and right values, so left value is a and right value is b, so these two are not same, but these two are actually same. So we can define this bb to be a middle of a palindrome, and this is the property we are going to use, right? And by the way, for this b, first of all we'll update the value to 3, and now we have this bb, that is a middle of the palindrome. Now immediately we will check the left and right value. So left value is a, right value is also a. Again these two are same, so this is also palindrome, so we'll update our answer again. So this becomes 4. Now again we will check the left and right value over here. So left value is c and right value is actually null. So in this case these two are not same. Because these two are not same, we will break out of the loop and we will say that okay, so far we have found something decent. So right now again we are at this position number b. Now remember that this becomes a little bit tricky, that it becomes easy for us to, if we check over here, this left value is actually b and right value is a. So again these two are same, but we should not fall for this trap because we have already concluded this bb to be a middle of the palindrome, so we will not consider this one. And this is also not a palindrome, which means that the answer we will only update by 1, and that this value by itself is a palindrome. And at the end we will check for this value number a, and a is a palindrome in itself, so we'll update the value to be 6. But in the left and right there is nothing, so we won't do anything with that, and in the end we will return this answer 6 to be the final answer. And this is the solution we are going to use to find all the palindromic substrings inside any given string s. This is the final optimal solution. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n square. Why n square? Because it takes us n time to iterate over all the values, and for any single value we might have to iterate over all the remaining values, so that takes n square time. But this is still a big improvement compared to our brute force approach, which had the n cube. If we see the space complexity, in this case the space complexity is actually going to be big O of n, because at any given point we might have to store all the values of n. First of all, we are going to initialize a variable called answer, and we are going to assign the value as 0. Now we are going to create a for loop and iterate over the given input. Now we have two possibilities. Any single character inside this given string s could be the middle value of any odd length palindrome or an even length palindrome. So we are actually going to make two calls to our check palindrome method, where we are going to return a value that whether this given string is a palindrome or not, and we are going to add that value to our answer variable. And inside this method we are going to pass the value of our string s, and we are also going to pass the character position of the middle variable. So the odd length palindrome would have the same middle value, so we will pass on that, and for even length we are going to pass two values. So over here we will pass I, and we will also pass I plus 1 to be the middle characters. Basically after we get out of this loop, we should have our answer ready, so we can simply return that. Now let's create this check palindrome method, and we will initialize a variable called count to count the number of palindromes we encounter. Now we are going to run a while loop, that while the left and right pointer are in bounds and not out of bounds, and while their character positions are same, so which means they satisfy to be the palindrome. If that is the case, we will keep on updating their values, and we will keep on adding our count variable, and in the end we will return the count variable. So let me quickly type that. So this condition defines that whether this given string is a valid palindrome or not. If that is the case, we will decrement the value of our left pointer, we will increment the value of our right pointer, and we will increment the value of our count variable. And once that is done, once we get out of this loop, we simply need to return the count variable, and that's it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently, and I would be posting this solution in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do encode and decode strings LeetCode problem, and as you can see, this is actually a LeetCode premium problem. If we see some of the companies who have already asked this question, where I want to get a job, there are companies like Facebook, LinkedIn, Google, Square, Uber, Microsoft, and Apple. So all of my favorite companies have asked this question, so that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given a list of strings. Now we need to design an algorithm where we are actually encoding this given list of strings into a single string. Then we are told that that single string is supposed to be sent over a network, and then when we get back to the second machine, we need to decode that given string into the original list of strings. So let's try to understand this with an example. So suppose we are given a string s, where we are given bunch of different strings that looks like this. So after this, we will actually create an encoded string. Now this encoded string is combination of all of these four items, and it is just a single string. So let's say that this is the encoded string we have created. Now after creating this encoded string, we need to write a function to decode the string as well. And after we decode the string, we should get a response that exactly looks like this, and this would be the original decoded string we would get. And this is what we need to return. So we need to return the algorithm to encode the string and also an algorithm to decode the string. So let's see that what would be the different approaches we can take. Okay, suppose this is the original string we are given, and we need to encode the string and decode the string. The idea is we are actually going to use an extra character, and where we are going to use an extra character, we would put it where one string ends before other string starts, and we will keep on repeating the same process. And all we have to do is, so that would be the way to encode the string. After encoding the string, when we have to decode, we will just simply take that character, and the moment we reach that particular character, we would know that okay, this is the place where one string ends, so we would create a new string for that, and then we will repeat the same process. So let's see that in action. So first of all, suppose we take this character that looks like this hash, right? I'm just taking any random character. The idea is you can discuss with your interviewer that what kind of character you can take. So suppose I take this hash. Now I do encoding string. So the encoded string is going to be AB. Then the moment I identify that this string ends over here, I would put a hash, and I would keep a continuous string. Now I realize that okay, this is a new string B, so I would add a value B. again I would put a hash. Now again this value is C, again I would put a hash, and again at the end I would find this value A, B, C, and that would be the end of the string. So now I have created an encoded string. Now if I want to decode the string, the decoding would work like this. So first of all, I'm iterating until I find that this is a valid string. So valid string is AB. Now I realize that, okay, this is the hash, and hash is the character that I put it as an extra character as an encoding mechanism. So I would remove this hash and I would treat this as a single string. Now I would again start creating a new string. So again I find this value B. The moment I encounter the string hash, I would treat this B to be a separate string. Again I would encounter this value C, and again I would encounter this value ABC, and this is the way we are going to encode and decode the string, and this solution would work as expected. If we see the time complexity, in this case the time complexity is actually going to be big O of n. Why? Because we will have to iterate over all the characters that are present inside this given string S to first of all encode and then decode. So overall it would be 2n, but we can generically write it to be big O of n. Now if we see the space complexity, in this case the space complexity is actually not that much, because we anyways will have to create an encoded string and decoded string, and all we are doing is just using an extra space to solve this problem. So this is pretty simple to me. Okay, suppose this is the string we are given, and the idea is we are actually going to add 4 bits that are going to store the length of any given substring, and then we are going to keep on repeating the same process, and we are going to create the encoded string. So let me quickly show you what I am suggesting. First of all, we would have an encoded string where first 4 character is actually going to store the information that what is the next length of substring that is coming that we are going to iterate over. So in this case, this is actually length 3. So if we add it in binary, it's represent as 0, 1, 1. So we are actually going to have 0, 0, 1, 1 to be the length, and then we are going to store these 3 characters as A, B, C. Okay, now we are done with that. Again, now this ends the first substring. So now this is of length 2. So length 2 becomes 0, 1, 0. Now we are going to do the same thing, and then we are going to store this value AB. And now this is also of length 2. So again, we will repeat the same process, and we are going to store the value of X and Y, and this is the encoded string. What we have done basically is we have actually created block of 4 bits that keeps the information that, okay, in the next subsequent value, these are the 3 characters that you will have to iterate over, and that is how we are going to decode it. So let's see the decoded string in action. In the decoded string, first of all, we are going to iterate over this given encoded string. Now we iterate over these 4 characters, and we find that, okay, value is actually 3, which means that next 3 characters are the characters of one of the substrings that we will have to separate. So we will iterate over these 3 and put it in a substring, and we will get a substring like A, B, C. Again, we will iterate over these 4 characters, and we realize that the value is actually 2. So because 2, we will have to iterate over these 2 elements, and we would get the value A, B. Now again, we would iterate over this next 4 bits, and we find that value is actually 2 again. So we will iterate over 2 more characters, and we will get the value XY, and then we would have a decoded string. So this is also another way to store all the values. Now this solution also works as expected, but I don't think that anyone is able to come up with this in the interview. So I just showed you this approach just for the explanation purposes, but actually I'm going to, in the coding, I'm going to show you the first approach that I solved earlier. So first of all, we are going to do the encode function. So let's take care of some edge cases first. If that is not the case, we are actually going to take a random variable that is not part of this original given string. So we are given the condition that there could be 256 characters inside the ASCII character for this given string I. So what we are going to do is we are going to take the 257th character as the character that is a separator between any two strings. So first of all, let's just create a string called a separate, and we are going to assign the character 257 to it. Now we will start building our string. Now we will iterate over this given list of strings. So first of all, we are going to append the value of whatever the string we are iterating over, and the moment this string ends, we are going to add the separate character. Once this loop ends, basically we should have done with encoding our string. Now all we have to do is just delete the last character because that would be an additional room. And once that is done, all we have to do is just simply return this new string builder we have created. So now we are done with encoding our string. Let's decode our string. if this given string s is actually of size whatever the located at 258, which means we are dealing with an empty string list. So in that case we will simply return a new array list and we should be done. If that is not the case, which means that we have a separated string, so let's just assign a new character. All we have to do is just return an array list where we are going to separate based on this given separate character, and that's it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our solution is actually pretty fast compared to a lot of other solution. It's not most optimal because I did not choose the approach 2, and let me know if you want to see the code for approach 2 as well. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do maximum depth of binary tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Microsoft, Google, Facebook, Apple, Bloomberg and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem and also very well liked problem on LeetCode. If we understand the problem statement, basically we are given the root of a binary tree and we need to return its maximum depth. Now we are also given the definition of what a maximum depth is. It is basically the number of nodes along the longest path from the root node down towards the farthest leaf node. That is the depth of the tree. And if we try to understand this with an example, suppose we are given a tree over here that looks like this. In this case, the maximum depth is going to be 3. Why? Because the nodes at the root level is currently at position 1 or height 1. The root at this level is at depth 2 or height 2, and root at this level is actually at depth 3. So in this case we need to return 3 as the answer because 3 is the maximum depth we can get from this root node. So let's see that what would be the different approaches to solve this problem. Okay, suppose this is the input we are given and we are trying to find the maximum depth for this particular given tree. Suppose this is the root of the tree. If you want to find the maximum depth for this tree, the answer is going to be 4 because of these two nodes. We can see it clearly over here that over here the value is 1, this is 2, this is 3 and this is 4, and this is the answer we need to return. The question is, before we return this answer, we will actually have to build some intuition behind it. And the intuition is, suppose at this position number 5, if we want to determine that what is the maximum depth over here, well, what we can do is we will check on the left side, we will check on the right side, and whatever has the greater number of nodes on either side, we will actually take that as maximum depth and we will do it plus 1. Well, in this case, the 6 and 7 both are located at the same position. 6 and 7, none of them has any children, which means that over here we can determine that this is actually 1 and this is also 1. So on the left side and on the right side both values are actually 1. So what we can do is we can do 1 plus 1. So 1 plus 1 will give us the answer that the maximum depth at position number 5 is going to be 2. So in this case, okay, we have found the maximum depth over here to be 2. Well, if we take this value number 4, well, at this value number 4 it does not have any more children. If it does not have any more children, which means we can determine the maximum depth in this case is going to be 1. Well, now we have these two values. That now based on these two values, it becomes pretty easy for us to identify that what is the maximum depth at this position number 2. All we will have to do is we will take whatever the maximum value amongst these two is. Maximum value is actually 2. So what we can do is we can do 2 plus 1, and 2 plus 1 is actually going to be 3. So we can determine that 3 is going to be the maximum depth we can achieve at this node number 2 if this was to be the root of the given tree. And for this position number 3, the maximum depth we can achieve is only 1 because it does not have any more children. So that is a given fact. Now we have these two information. Now it becomes pretty easy for us to identify that what is going to be the maximum depth at this position number 1. And all we will have to do is take the maximum amongst these two values. So maximum value is going to be 3, and all we need to do is just plus 1. So if we do 3 plus 1, we will get the answer 4, and 4 would be the correct answer in this case, and that is what we are going to return. So the maximum depth we need to find, we can simply do it by using this method. Well, now if you see, for this particular solution we are actually able to achieve this solution, but what we are doing is that at any given position we are seeing that what is the left max value or right max value, and whichever is greater amongst either one of them, we are taking that and we are adding 1. Well, now again we are repeating the same process, that we are taking the left max and right max value, and again we are adding 1. So which means that in order to solve a bigger problem, we are actually solving a smaller problem and then again a smaller problem. So basically we are doing it recursively, and that is how we are going to solve this problem using recursion, which is very powerful and it is highly used in different kinds of tree problems. So that is how we are going to solve this problem, and this would be the optimal solution we can use. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n, because we will have to iterate over every single element in order to get the answer. And if we see the space complexity, in this case the space complexity is also going to be big O of n, because we might have to store all the values inside our recursive function. And this approach is actually very good, it works as expected. There is also one more approach which uses stacks, and that does not use recursion, it actually use iterative function. So let me know in the comments if you want to see the stack solution as well, and I can also explain that. But for now, if you show this recursive solution in any interview, the interviewer would be more than happy. So let's move on to coding now. So first of all, we are going to take care of a edge case. If that is not the case, we will have to call our recursive function. First of all, we are going to have an integer called left max that is going to take care of the left subtree for any given root position, and we are going to call our recursive function again. And same we are going to do for the right subtree as well. We are going to create a parameter called right max. And in either case, all we have to do is simply return whatever the maximum value we are able to find, and then we will add 1 to it. And this should be it. Once we get out of the loop, our solution would be done. So let's try to run this code. Okay, seems like our solution is working. Let's submit this code. And our code runs as expected, and it's actually pretty fast compared to a lot of other solutions. So I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do same tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Google, Bloomberg, Apple, Microsoft, Facebook and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem, and as the name suggests, same tree, the problem is self-explanatory, but let's go over it. That basically we are given two roots of a binary tree called P and Q, and we have to write a function to check if they both are same or not. So let's try to understand this with couple of examples that are given over here. Here we are given this two trees P and Q, and in this case we can see that both of these are 1, both of these are 2, and both of these are 3. So we can say that okay, they are actually same, and we can return true in this case. But for the second example, if we see the P and Q values over here, for 1 is same, so root values are same. But if we see over here, this is actually 2 and this is actually 2. Despite being the same value, the positioning is not same, because this is actually the left child of this given P tree, and this is actually the right child of this given Q tree, which means that these two are not same. So in this case, we will return the false, and this is what we have to achieve. So let's see that what would be the different approaches to solve this problem. So solution of this problem is actually quite simple, and if we see the approach 1, we are going to use an iterative approach. In the iterative approach, what we are going to do is we are going to iterative over both of these given trees in the same manner, and we are going to keep on checking subsequent nodes of every single position. At any given moment, if we identify that any single node does not match, we can return false immediately, and if somehow we can reach out to the end of the tree and iterate over every single nodes, we can return true in this case. So let's see that in action. So first of all, we are at this for this P and Q tree. Currently we are at this root position, so we will check that value, and both of them are actually 1, which means we are good so far. Now we are going to iterate over on the left side. So on the left side, this value is actually 2 and this value is also 2, so again we are good. Now again on the left side, this value is actually 3 and this value is also 3, so again we are good so far. Now we go back, and now for this position number, we also have a right subtree, or so we will check that right position. This is 5 and this also has a right position, which is also 5. So far we are good. Now again we go back to this root node. We still have this right side that we haven't traversed, so this node is 4 and this node is also 4, so again we are good. And at the end, this node is 6 and this node is 6. Now we don't have any more nodes to go back to, so essentially we have traversed over all the nodes inside given both the trees, so we can return true in this case. And this is the approach we are going to take. Let's see what would happen in a scenario where trees don't match up. So here I have drawn that example as well, that over here all of these nodes are same, but actually this node and this node, these two are not same. So because these two are not same, the moment we iterate over all of these nodes and eventually we would reach to these positions, we can return false immediately in this case. So this approach would work as expected. And if we see the time and space complexity in this case, the time complexity is actually going to be big O of n. Why big O of n? Because we will have to iterate over every single node inside the given tree for both P and Q trees. And the space complexity would be big O of log n. That is because this is a binary tree. Well, in the second approach, we are actually going to solve this problem recursively. And the idea is at any given moment we have to identify that whether given two trees are same or not. The thing we are going to do is we are going to compare their root nodes. If they both are same, we will have to compare their entire left subtrees, that they have to be the same, and also we will have to compare their entire right subtrees, that as they also have to be the same. And if that is the case, we can define that tree to be the same. But if we take a look at for the left subtree, again we are going to repeat the same process, that even for the left subtree we are going to compare the root nodes. If they both are same, then we are going to compare their left subtrees and their right subtrees to be the same. So essentially we are doing the same thing repeatedly for different kinds of input, and recursion is the best way to approach that. And also your interviewer is going to expect you to do this recursively, because that would be more efficient way of doing it. So let's see that in action. So the idea is at any given moment we are going to compare the root node. So over here root node is same. Because root node is same, we will have to check that whether the left subtree is same and right subtree is same or not. So first we will do the left subtree. So now for the left subtree we have these two trees for P and Q respectively. So again we will check the left node. So left node is this 2 and this is also 2. So they both are same. Now we are going to check the left subtree and right subtree again. So this both of these are 3, so we are good. Now we will have to check the right subtree. So right subtree is also 5 and 5, so again we are good. Now again, so far we have calculated the entire left portion, but we haven't calculated the right portion. So now we will do that. So again for the right subtree, this value is 4 and this value is 4. So again they both are equal, so we are good so far. And then these values are 6 and 6, so again we are good so far. Now we have iterated over every single node recursively, that is the important part, and we have found all the values to be the same. So because they were same, we can return true in this case, and everything is good. And at any given moment, suppose we identify that any single node does not contain the same value as its counterpart, then the moment we are comparing these two values, we can return false immediately, and that would be the solution for this problem. If we see the time and space complexity in this case, the time complexity is also going to be big O of n, because we will have to iterate over every single value, and the space complexity is going to be big O of log n. So the time and space complexity is not different than the iterative approach, but recursive approach just is a lot less coding, and I will also be showing that in the code. So first of all, we are going to check that if the given P and Q both are null. If both are null, we will have to return true, because essentially they both are same. If that is not the case, and if any of either P or Q is null and the other one is not null, then in that case we will have to return false. And if both values exist, then we will have to compare their values. And if both values are not same, we can return false immediately. If that is not the case, we will have to iterate over left and right subtrees of a subsequent P and Q trees. So now we are going to make our recursive call. And that's pretty much it. Let's try to run this code. Okay, seems like our code is working as expected. Let's submit this code. And our solution runs pretty efficiently. It's actually 100% faster, but if that is not the case, because runtime is 0 millisecond, that's why it's showing 100% faster. I would be posting this in the comments, so you can check it out from there. Hello friends, we are now employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to invert a binary tree lead code problem, and if we see some of the companies where I want to work at who have already asked this question, there are companies like Amazon, Facebook, Google, Apple, Bloomberg, Microsoft, Uber, Goldman Sachs and LinkedIn. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is the LeetCode easy problem and also very well liked problem on LeetCode. Basically we are given the root of a binary tree and we need to invert the tree and return its root back. So let's try to understand this with a couple of examples. First of all, we'll take this example. So over here we are given a tree that looks like this, where this 2, 1 and 3 are part of the tree, where 1 is the left child and 3 is the right child. So if we invert this tree, we will get an answer that looks like this, where 2 remains the root because it is the root node, but this 3 that was originally the right child will become the left child, and this 1 that was originally the left child will become right child, and this is what we need to return. Let's take a little bit more complicated example. So over here we are given the root to be 4. Now we are given that the left child and right child of this 4 is actually 2 and 7, and further down we are given more left child and right child for this 2 and 7 as well. Now if we invert those all of them, we will actually get a result that looks like this, where 4 remains the common, this 7 that was originally the right child will become the left child, and this 2 that was originally the left child will become right child, and same thing will happen for these leaf nodes as well, and this is the answer we need to return in the answer. This is what the problem is asking us to do. Let's see that what would be the different approaches to solve this problem. Before we come up with the optimal solution, let's understand a very important concept. Suppose this is one of the kind of a binary tree we are given and we need to invert this tree. Well, if we see over here, we are given a root node, then again we are given some left child and we are given a right child. Now further down, for this left child and right child, they also have the children of their own and they also form a bigger binary tree. So at any given moment, suppose we are given this root node, we are given this left child and we are given this right child. So if we want to invert this tree, all we have to do is whatever this right child is and whatever this left child is, if we just swap them or if we invert them, basically we are at least done with this root level and with this left child and right child level. Now again, if we further break down that, suppose this is the left child, now we are treating this left child as a root. So suppose now this is the root and this is the left child and this is the right child for this root. So again, if we want to invert them, what we can do is we can take whatever the left subtree and right subtree is. So in this case, for this root, the left subtree is going to be this, the right subtree is going to be this. If we swap them, essentially we have taken care of up until this level for this inverting part, and same way we can keep on repeating the process. So now this becomes our root. Again, we flip these two values, and even for this level we have taken care of inverting the binary tree. So this is what exactly I'm suggesting us to do in order to solve this problem, that we starts breaking this given input into bunch of smaller inputs and start inverting binary tree in that manner. So the idea is that for every single time we will have a root node, we will swap its left and right child, then again for if there exists any left or right child, we will repeat the same process and keep on swapping those values, which means that we are actually doing the changes recursively. We can actually solve this problem pretty efficiently. Let me quickly show you how. Suppose this is the input we are given and we are trying to invert this binary tree recursively. So what we are going to do is, suppose we will take initially this as the root node, and for this root node we actually have a left child and we actually have a right child. So what we are going to do is we are going to swap its values, and we are going to swap the entire left subtree and entire right subtree. Then at any given moment, as long as we have some nodes, we are going to keep on treating them as different root nodes, and then we will keep on flipping their values or their children's values, and at the end we should have a completely inverted binary tree. So let's see that in action. So first of all, this is the root node and this is the left and right subtree. So what we are going to do is we are going to swap the values. So we will have a tree that looks like this. Okay, so far treating this as root tree, we have actually swapped these left subtree and right subtree, and we will get a tree that looks like this, where you can see that this value 3 and 2, they are actually inverted, but their subsequent children values, they are not inverted, and we will still have to repeat the same process. So let's see that in action. So now again, what we are going to do is we are going to treat this 3 to be root child, and we are going to repeat the same process with the 6 and 7. So if we invert them, we will get a tree that looks like this. Now we are going to treat the 7 to be the root node. If we treat the 7 to be the root node, actually it does not have any children, which means we don't need to flip any more values. Now again, we will treat this 6 to be the root node. If we treat the 6 to be the root node, again it does not have any more children, so we can skip that. Now we will treat this 2 to be the root node. So if we treat this 2 to be the root node, it has children, so we will have to swap their values, and we will get a value that looks like this. and we would have taken care of both of them. Now again, this 5 and 4 does not have any children, which means we can't do anything about it. And then in the end, this is going to be the answer we need to return. So we can simply return the root value, and basically we would have inverted the entire tree recursively. So that is the approach we can use as an optimal solution. There is also one more way to iteratively approach this problem, but the thing is, I believe that for tree kind of problems, the recursive approach is better than the iterative approach. Let me know in the comments if you want to see the iterative approach as well, and I can make a separate video on that. If we see the time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree, because we will have to iterate over every single tree to invert them. Now if we see the space complexity, well, at any given moment, because of the recursive function, we might have to store bunch of different node values, and that would depend on the height of the tree. So basically the space complexity is going to be big O of h, where h is the given height of any binary tree. So because we are going to solve this problem recursively, first let's create the terminating condition, that if the given root is actually null, we can return. If the given root is not null, we are going to make the recursive call for right and left values. So for right tree, we are going to make the recursive call to the same function with the right child. Same thing we are going to do for the left subtree. After that, we are going to replace the values of left and right subtree. So now that should have taken care of all the cases, and now we can simply return the root value. And that should be it. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our solution is actually pretty efficient. It's actually 100% faster than all the other solution, and that is because the runtime is actually 0 millisecond. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do binary tree maximum path sum lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, DoorDash, Facebook, Microsoft, Google, ByteDance, TikTok, Snapchat, Twitter, Apple, Uber and LinkedIn. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So despite being a hard problem, this is a very well-liked problem on LeetCode. Basically, we are given the root of a binary tree and we need to return the maximum path sum for that particular non-empty path. So we will have to understand a couple of terminologies over here. We will have to understand that what a path sum is, and before we understand that, we will have to understand that what a path is. Lucky for us, we are given definition of both of them. So a path is a binary tree sequence of nodes where each pair of adjacent nodes in that particular sequence has an edge connecting them, and we are also told one very important thing, that any single node in that sequence can at most appear once. We are also given the note that it is not necessary that path has to go through the root of the node. Okay, so over here I have drawn a couple of different trees, and I'm going to show you some examples of what a valid path is and what an invalid path is. So first of all, this is a valid path. And for that, we'll have to understand that why this path is a valid path, because all the three nodes that are connected in this particular path, they are adjacent to each other. They all have an edge connecting to them, and they all appear at most once and nothing more than that. Now, this is also a valid path, and this is also a valid path. This is also a valid path, and this is also a valid path. Both paths are valid as well. And the path that looks like this is also a valid path, and the path that looks like this is also a valid path. Now let's see some examples of an invalid path. Suppose I start up my journey over here. I go up, I go down, I go to the left child, and then again I try to go to the right child. Again, this is an example of an invalid path because this node appears twice as well. Now we know many examples that what a valid path is. Now let's see that what the problem is actually asking us to solve. After understanding the definition of a path, we are going to understand the definition of a path sum. Basically, it is the sum of all the nodes that are present inside this given path. So that is actually quite simple to understand, and the problem is actually asking us to find the maximum path sum that we can make out of given binary tree. So now I have drawn three different trees to understand the maximum path sum for each one of them. So first of all, for this particular tree, the maximum path sum is going to be this path. And why? Because all the nodes are positive, and if we take the sum of these three nodes, it's actually going to be 5 plus 4 plus 9, which becomes 18, and this is what we need to return in the answer. If we take the second example, things are not as easy as the first one. Why? Because we are dealing with a negative value over here. So in this case, even if we try to do the same path that we had drawn over here, this won't work, because the sum of this is actually going to be, which is not the most optimal path we can achieve. The most optimal path in this case is going to be this one, and the sum is actually going to be 5 plus 4 equals to 9. And in this case, we will have to return 9. So in this case, the maximum path actually is going to be this one between these three nodes. Why? Though there is a positive value over here, if we were to include this positive value, the path we would make would looks like this. And that would actually go through this root value, which has the value of negative 11, which actually brings the total path down or total sum down. So that is why it is not in our best interest to include this node, and that is why the maximum path in this case we can achieve is amongst these three nodes, where the sum is actually going to be 10 plus 8 plus 2 equals to 20, and that is what we need to return. Now, before we come up with the optimal solution, I'm going to show you a few different concepts with various examples. So first of all, we have an example of tree that looks like this, where in this case all the nodes are positive, which means things are a little bit easy for us, and our aim is to find the maximum product sum we can achieve, right? So the idea is, at any given portion we have the root information. Now from this root information, what we are going to do is we are going to see that what this left subtree has to offer and what this right subtree has to offer, and then addition of all of them should give us our maximum product sum. So in this case, this left subtree does not have any more children. It only has one node, which means it can, the maximum value it can contribute towards the maximum path sum is going to be 5. So we have the value 3 already from this root. Then we gain this 5 from the maximum path sum, and then again we gain this 2 from this right subtree. So the total maximum path sum we can achieve is going to be 10, which is the answer in this case. And since all nodes were positive, it is in our favor to include all the nodes. So that is one way to do it, right? And this is a very simple example, so we are able to understand it quickly. Now let's try to see that what would be the approach in a little bit more difficult scenario. So suppose we are given a tree like this. In this case, we actually have a negative value. So if we apply the same logic over here, this left subchild has -5 to offer, this right subchild has +2 to offer, and this root value is actually 3. So maximum path sum based on the previous logic would actually become 0 if we just do sum of all the values. But that is not what we are going to do. We are also going to check at any given moment that whether the value that is being contributed, if that is less than 0 or not. If that is less than 0, immediately we are going to discard this value, which means that we are not going to consider this -5 to be part of this maximum product sum. And in this case, what we are going to do is we are going to do this 3 plus 2, because both values are positive. So in this case, the answer we are going to get is 5. So we gain one more important thing, that whenever we see minus values, we are going to ignore that from our maximum production, because they don't add any more value over here. Now one more thing we need to consider. What if we have multiple nodes, and then what should be our approach in that case? Okay, suppose we are given an example like this. In this case, what should be our approach? Well, we want to find the maximum path sum. So again, we are going to repeat the same process. We are going to see that for this root node, what does this left subtree has to offer? It has to offer maximum 5 value. So we are good up until this point. For this right subtree, actually we will have to calculate that what is the maximum value it can offer. And how we can do it? We are actually going to take this root value, because that is going to be the part of this right subtree for sure. So we already have value as 8 over here. Now from this 8, we actually have two options to be included for our maximum path sum. We can either do 8-2 or we can do 8-1. So in this case, obvious choice is going to be 2, because this value 2 is actually greater than with this value 1. So in this case, we are going to ignore this 1 and we are going to keep this 2, which means that we can do 8 plus 2 to be 10. So in this case, we can determine that this actually has the value 10 to give towards maximum path sum. Now the question will come to your mind is that why in this case we only choose value 10 and why not we chose value 11? Well, what if under what circumstances can this value become 11? It can become 11 if we include all these three values to be part of this maximum path sum. But we already know that this goes through the root value, which means that if we were to include all these three values to make the value 11, it won't work, because then the path would look like this. It would go from 5 to 3. Okay, so far we are good. Then again through 8. Now from this 8, we cannot include both 1 and 2, because suppose we try to do it, we include this 1 and then we try to go back to 2, we come up at this 8 again, and we know that that cannot be part of a path sum. So that is why we only have the option to choose either 1 or 2. So that is the important detail over here. That is why for when we were calculating the maximum contribution this right subtree can make, we only had two options. Either we could do 8 plus 2 or we could do 8 plus 1, but not both of them. So just remember that. That is why I showed you this example. So in this case, the maximum contribution we can get from this right subtree is going to be 10. So now let's calculate the maximum path sum in this case. So the maximum path sum is going to be, the root node is 3 plus this left subtree can contribute value 5 and plus this right subtree can contribute value 10. So the answer is going to be 18, and this is what we need to return in this case. So far we have understood, we had gained very good understanding of many different cases. Now let's consider one more case where the things become a little bit more interesting. And why it becomes interesting? Because so far we are under the impression that we have to take this root value as part of the answer. But what if that is not the case? What if we encounter some possibility where this root value does not need to be part of the main maximum path sum that we take? Then how do we approach that? So let me quickly show you an example for that as well. Okay, this is the last complicated example. Now in this case, we are again going to apply the same logic to find the maximum path sum, but we are going to do some interesting things. So first of all, we have this root value to be -3, right? Now we are going to see that what is the leftmost contribution it can get. It can get 3 as the contribution in this case. Now again, for this portion, we are going to see that what is the rightmost contribution it can get. The rightmost contribution it can get in this case is going to be this 8 plus 2. So 8 plus 2 is going to be 10 so far, right? Now if we see over here, actually this is not the most optimal way to approach this. Why? Because this path actually gives us the maximum path sum. So let's see that how can we actually determine that. Well, when we are traversing, we are actually going to have a variable called path to keep track of what is the current maximum value we have found so far, and whether do we need to include a new root. And new root in this case is going to be the condition where we actually refrain away or move away from the original root we were using. Because if we were to use this root node, there is no way for us to use all of these three nodes. So that's why what we are going to do is, we are first of all going to see that if we use this current root, what is the maximum value we are gaining. So the maximum value we are gaining in this case is going to be 3, which is this one, plus 10, which is the contribution we can get from this right subtree. So 3 plus 10, and let me get rid of this maximum path sum for now. So 3 plus 10 plus whatever the root value. So root value in this case is -3, which is in this case the total value is going to be 10. But now when we are traversing, or when we were calculating the maximum contribution we can gain from this right subtree where the root node is actually 8, the value maximum we can gain from over here is actually going to be this value 8 plus it has the its left subtree is contributing value 1 and its right subtree is contributing value 2, so which both are positive values, and their total is actually 11. So this is 11 and this is 10. Then why are we so keen to keeping this root to be part of the optimal solution? We should not put it in the maximum path sum, and this is exactly what we are going to do. Then we are going to choose a new path, and this new path, the value is 11. So then we are going to have a maximum path sum variable where we are going to keep on updating the value, and we are going to update the value to be 11, and now it does not have any further more nodes to check for, and then we are going to return this 11 to be the answer. And at any given moment, whenever we find that the new path we are getting that gives us better answer than whatever the previous answer we were getting, then we would update the new path and we will update the value of the path variable. So that is one tricky part that we have to understand in this question. And now let's see that after understanding all the concepts, now let's see that what would be the way to solve this problem. The idea is, let me clean this up a bit. Now I'm going to use the same example to quickly walk through this problem. So first of all, we are at this root position. What is the left contribution we can get, which is 2. The right contribution we can get, in this case it's going to be 10. We actually calculated all of them. Now the sum of these two is these three is actually going to be 10 only, but when we were calculating that, we had this path variable where we actually calculated the value of this to be 11 and we updated this path variable, and then we are going to have this maximum path value where we are going to keep track of the maximum path we have found so far, and in the end, because it does not have any more children, we are going to return the maximum path to be 11, and this is what the answer we need to return. So basically we are taking a bigger problem and then we are dividing it into bunch of different parts. That for this root we are actually trying to calculate this left subtree and right subtree. Then again for this root value we are again calculating this left subtree and right subtree, which means we are solving this problem recursively, and that is how we are going to approach it. And also let me show you the time and space complexity. So time complexity in this case is actually going to be big O of n. Why big O of n? Because at any given moment we will have to iterate over all the nodes that are present inside this given tree, and the space complexity is going to be big O of h, where h is the height of the tree. So first of all, we will need a separate method called max gain to calculate that what is the maximum value we are gaining. So for that we are going to create a new method that takes in a node as an argument. We will also need a maximum sum value. So we are going to initialize it as global variable. We are going to assign it to the most negative value possible. So okay, now let's start implementing our max gain function. So first of all, we are going to have the terminating case that if the given node is equal to null, we will return 0. If that is not the case, we will need the values of left gain and right gain for any given tree node. So we are again going to call the recursive function for that. We are going to create a variable called price new path that we are actually going to calculate by using the node value plus whatever the sum of left gain and right gain is. Now that is done, we are actually going to calculate the max sum. We are going to compare it with whatever this new path we are calculating. And once that is done, basically all we will have to do is simply return the node value with whatever the maximum value is amongst this left gain or right gain. From this max path sum method, we will have to call this max gain function. So let's do that. After all the calculation, we are simply going to return whatever the max sum we are able to achieve. Okay, and now let's try to run this code. Seems like our solution is working as expected. Let's submit this code. And our solution is actually pretty efficient and faster than a lot of other solutions, and I would be posting this in the comments so you can check it out from there. Hello friends, we are not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do binary tree level order traversal LeetCode problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Amazon, Microsoft, Facebook, Bloomberg, Google, Apple and Uber. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given the root of a binary tree. Now we need to return the level order traversal for this binary tree, and we need to return the nodes values. Now we are also told that we need to return them in left to right fashion and level by level. Basically we are given a binary tree over here. Now for any binary tree, basically we always have two things. We have a root node or a parent node, and that parent node has some children nodes. So, and furthermore, this children node can have children of their own as well. So every time a new set of nodes are being added at the bottom, essentially we can define a new level being created. So if we see this example over here, essentially this is level 1, this is level 2 and this is level 3. And we need to return the nodes level wise from left to right. So let's try to understand this with this example over here, where we are given 3 levels. So this is level 1. These two nodes, they are located at level 2, and this two nodes, they are located at level number 3. So in the answer, first of all, we are going to return this node 3 because this is the only node at this level. There are no other nodes. Now at the second level, we have two nodes 9 and 20, and we need to return them in the same sequence of 9 and 20. And in the third section, we have two nodes 15 and 7. First we'll return 15 and then we'll return 7, and that is the answer we are going to return in this case. Let's see that what would be different approaches to solve this problem. So when it comes to tree traversals, there are mainly two subcategories. First one is a depth first search and second one is a breadth first search. Well, in the depth first search, we actually expand upon the depth of any given tree and then we keep on iterating over all the nodes. While in the breadth first search, we actually visit the root node first and then visit its children and then keep on repeating the same process. So in this portion, for depth first search, there are three further subcategories: Inorder, Preorder and Postorder, which I'm going to show you first, and then I'll explain you how breadth first search work. And in this problem, actually we are going to use breadth first search to solve this problem. So during the in-order traversal, basically first we visit the left side of the tree, then we visit the root node, and then we visit the right node. So first of all, for this root node, we will keep on expanding until the left node exists. So left node exists over here and then left node again exists over here, which means this is the first node we are going to visit. So we start our visit traversal at 4. Now 4 does not have any more children, which means we can't go downwards anymore, which means now we go back to the root node. So root node for this 4 is actually 2, and then we again expand on the right side. For this 2, we still have right side 5 that we haven't visited, so we will do that. Now again we have visited all these 3 nodes, so now we are done with these. Now we again go back to the root node, which is 1, so we visit 1, and then again we repeat the same process, left, root and right. So again we go on the right side. So this is the strategy for in-order traversal. Now for the pre-order traversal, basically we follow the principle of root, left and right node, and this is the way we visit the node. So first of all, we are going to visit the root node, which is 1 in this case. Then again we are going to visit the left node, which is 2. Then again we are going to visit the left node, which is 4. Then again we are going to visit the right node, which is 5. Again we come back, and now in this case we again go back to this root node, which is 3. Then again we go to the left, and then again we go to the right. So this is the strategy for using a pre-order traversal. Now for the post-order traversal, basically we follow the principle of left node, right node and then root node. So first of all, we are going to visit up until left node exists. So this is the leftmost node. So we are going to visit that first. So we start our traversal at this position number 4. Then we visit the right node, which is 5, and then we visit the root node, which is 2 in this case. Now after this, we actually don't visit this node 1, because for this node 1 there exists a right subtree that we haven't visited. So we again go to the right side, and again this also has a left node, which is 6. So then we visit the node 6 in this case, then we visit the node 7, and then after visiting the 6 and 7, then we visit its root node, which is 3, and in the end, after visiting all the nodes, we visit the main root node, which is 1. And this is going to be the traversal strategy for the post order traversal. So when it comes to breadth first search, we actually expand upon its neighbors or its children for any given tree, rather than going in depth in any one particular direction. So if we see for this particular tree, the breadth first search traversal is going to look like this. So first of all, we are going to visit the root node, which is 1 in this case. Then we are going to visit its children. So its children are actually 2 and 3. So we are going to visit this node 2 and 3. Now for this left child, again it still has children of its own, so we are going to visit them first. So we are going to visit this node 4 and 5, and then for this node 3, it has children of its own as well, which is 6 and 7. Now in this case, we cannot further expand because this 4, 5, 6 and 7 does not have any children of their own. So we are done with the traversal. Basically we have iterated over all the nodes that were given. But if you see these nodes and the fashion we have visited them, it actually gives a very interesting perspective for the problem we are trying to solve. Well, first of all, we are visiting the node that is located at this position number 1. Then we visited its children, which are actually located at this level 2. So first we visited the level 1 node, then we visited all the nodes that are present at level 2. And then we visited all the nodes that were present at level 3. If we had any further nodes, then we would have visited them that were for the nodes that were located at this level number 4. So this breadth first search is actually a very good solution for the problem we are trying to solve, where we are trying to see that what would be the level order traversal for any given tree. Basically we are anyways iterating the nodes in particular levels. So all we will have to do is just simply make tuples of the levels that we are visiting and the nodes we are visiting at. So that is how we are going to optimally solve this problem. Now we are going to use the same tree that we have been using so far, and we are going to see that what would be the answer. So first of all, we will have to create an array list where we are going to store the answer. Now at any given position, whenever we start iterating over this tree and whenever we jump to a new level, we are going to create a new node inside our array list. So first of all, we are at this level 1, right? So now for this level 1, we are going to create a new node over here, which is this one. And for this level, because this node is located at level 1, we are actually going to create an entry over here. Now for this one, we are actually going to iterate over its children. We are going to call its children 2 and 3. Now because these are children of this node 1, they are actually going to be located at level which is whatever the level of this 1 is plus 1. So the level of this 1 is actually 1, so 1 plus 1 is going to be 2. So these nodes, they are actually going to be located at level 2. Now the moment we identified a new level, we are actually going to create a new node inside our array list. So over here we would have created this new node. Now in this new node, because we visited these values 2 and 3, we are going to actually add the value 2 and 3 over here. Now again we will have to further go down for this level 2 and 3. And remember that initially we only had this one node and we visited its children. Now again we have a node and we are visiting its children, and again we have a node and we are visiting its children. And suppose these had, if the new nodes, we would have visited their children as well. So basically we are doing the same work for different set of inputs, where initially this was a child, but now this becomes a parent for these nodes. So we are basically doing recursion, nothing special in this. So now from this level 2, whenever we will call these left and right children, basically what we would have done is we would have increased whatever the value of level was for this value 2 plus 1. So this was located at level 2, which means these nodes, they are actually located at level 3. So now again we created a new level. So because we created a new level, we are going to create a new entry inside our array list, and then all the values located at this level, we are actually going to store them in this portion of our array list. So now first of all we are going to visit node 4, so we are going to add node 4 over here. Then from this 2, we are going to visit its right children, which is this node 5, so we are going to add 5 over here. Now we still have nodes that we haven't visited. So now we have this node 3, so we are going to first of all visit its left children, which is this node 6, and this is also located at level 3 because this 3 originally was located at level 2. So this is also because this is at level 3, we are adding it in the third portion or third placeholder inside our array list, and then in the end we are going to visit this node number 7 as well at the end. Now this does not have any further children, so we are good up until this point, and we can stop our traversal and return this new array list that we have created as the answer. So this is the approach we are suggesting, and if we see, we did the breadth first search traversal, and basically we did it recursively. Now we could have done it iteratively as well, nothing special in there. So you can discuss with your interviewer what is the strategy you want to use, and 9 out of 10 times your interviewer is going to ask you to do this problem recursively because it's lot less code. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present inside this given node. And if we see space complexity, well, basically we will have to create recursive, we will have to make recursive calls, and that takes some space, and that space is actually dependent on height of the given tree. So space complexity is actually going to be big O of h, where h is the height of the tree. Now first of all, we are actually going to create a list of lists where we are going to store the answer, and we are going to declare it as a global variable because we are going to create a new method for our recursive call. So first of all, let me create this global variable called answer. Now we are going to create a new public method which is going to be acting as our recursive function, and it does not return anything. We are going to name it as order, and as an argument it is going to take any tree node and the level we are currently at. And now inside this method, first of all, what we are going to do is that whenever we are at any position or whenever we are creating a new node, basically we are going to add a new entry to our answer. After creating a new value for a new level, now all we will have to do is whatever this tree node is, based on its level value, we will have to add that value to our answer. Now after doing that, basically all we will have to do is for any single given node value, first of all we are going to check that whether it's left child and right child, if they exist or not. If they exist, basically we are going to call the same order method with this left child and right child, and we are going to increase the value of the levels. That is all we need to do for this order method. So now from this main method, first of all we are going to check for an edge case that if this given root is null. If this is null, we can simply return the answer. And if this given root is not null, basically we will have to call this order method with our root information and the current level that we are at. And now at the end, we simply have to return whatever the answer we get. Let's try to run this code. It seems like our solution is working as expected. Let's submit this code. And our code is actually pretty efficient compared to a lot of other solution. And I would be posting this in the comments so you can check it out from there. Thank you. So today we are going to do serialize and deserialize binary tree LeetCode problem. And if we see some of the companies where I want to get a job who already asked this question, there are companies like Amazon, Microsoft, LinkedIn, Uber, Google, Facebook, DoorDash, TikTok, Apple, Snapchat, Splunk, and Goldman Sachs. So that's why I'm paying my utmost attention. I hope you also enjoy the video. Hello friends, the reason I have not been uploading in recent days is because I just had twin baby girls, and so yeah, that's the update. And now let's move on to the video. So LeetCode thinks that this is actually a hard problem, but in my opinion, this is not a hard problem. It's actually very creative problem. Basically, we need to serialize and deserialize the given binary tree. Now, first we'll have to understand that what does serialize and deserialize means. Well, serialization is the process of converting the given data structure, which is tree in this case, and we need to convert that into a sequence of bits so that it can be stored in some memory or file buffer, and then we can transmit it across any network. Now in this problem, basically we need to design an algorithm where we are actually serializing and deserializing a binary tree. So serializing means that first of all we are finding a way to convert the given binary tree in some sort of bits, and in this case we are told that we need to convert it in strings, so we are familiar with that. And then deserialize means that we are given this string and we need to write an algorithm to convert this string back to a binary tree. So we'll have to do both the things. And if you see this problem, this is actually very similar problem that we did earlier with strings. This is the solution of that problem, so go and check it out first. We are also given a clarification that we can be as creative as we can with the serialization and deserialization process. So we can have different way of serializing the tree and different way of deserializing the tree, as long as we maintain the tree data structure. So let's see that what is the approach I am suggesting, and you can also come up with your own creative approach. Well, basically in this problem, we are only given the root of a tree, and then somehow we will have to go over the entire tree and then traverse it, convert this given root and all of the entire tree into a string. And after we have converted it to string, we will have to find a way that suppose if we are given the string as the input, how can we convert from the string this binary tree as well. So we are doing both the processes. So the important thing in this case is that we will have to traverse over the given binary tree. So there are mainly two strategies to traverse over the given binary tree, DFS and BFS, and I have explained this very carefully in the previous video. You can check it out over here. So basically in this video, what I'm suggesting is that we actually go with pre-order approach with using DFS to serialize and deserialize this given binary tree, and I would be showing you that what is the process we are following. So first of all, we are going to serialize this given tree, which means we are going to take this binary tree and we are going to convert it to a string. Now, as mentioned earlier, we are going to use the pre-order traversal for that. So if you are not familiar with the pre-order traversal, basically we visit the root node first, then we visit the left child of this root node, and then we visit the right child of this root node. And that is how we are going to end up creating the string from this given binary tree. So let's see that in action. So first of all, let's create a variable called s or string where we are going to store the string value. So first of all, we are going to visit the root node. The root node in this case is 1. So we are going to add an entry called 1 over here. Now we need to visit the left child of this root, and then we need to visit the right child of this root. Now remember, this is actually a DFS policy. So in the DFS, we go in the depth first. So first of all, we are going to visit the left child. So left child in this case is 2. So we are going to add an entry that 2 is the left child over here. And then again for this 2, because we still have left child left, so we are going to visit that. So for this 2, the left child in this case is actually 4. Now for this 4, we don't have any more left child and we don't have any more right child, which means that first we try to visit the left child. For this 4, there is no left child, so we enter a value called null over here. And then for this 4, again there is no right child, so again we add value null over here, saying that for this 4, the two left child and right child is actually a null value. Now after that, we still have nodes left that we haven't visited. So now for this node 2, we have this node 5 and it's right. So again, we are going to enter the value 5 over here. After entering the value 5, we are again going to check the left child and right child for this 5. So left child in this case is null, and again right child is also null. So we will add 2 more entries, null, null again. And now we go back. So now we have visited all of these nodes, but the thing is we haven't visited the right portion of this original root node. So again, we will have to iterate over the right subtree. So right subtree in this case is going to be 3. So we add 3 over here. Now for this 3, again, we don't have any more children nodes. So again, we add 2 null values. So this is the answer in this case that we have to return for this given tree, that this is the string value that represents this given binary tree. Now let's see that what would be the deserialization process. So now we are going to work upon the deserialization. So basically we are going to convert string into binary tree. So the idea is this is the string we generated from the serialization process. Now again, because we are using pre-order traversal, we are actually going to apply the same logic. So we are going to treat the first node to be the root node, then the next node would be the left subchild of this root node, and the next node is going to be the right subchild of this root node, and we are going to keep on iterating this process in reverse order. So the idea is that first of all, okay, we identified this node. So this node is actually our root node. Okay, so root node is actually 1 in this case. Now again, this 2 is actually the left child of this root node. So because this left child exists, the next node is again going to be the left child of this node 2. So again, we are going to create a node 4 that is left child of this node. Now for this 4, the next 2 nodes are actually null null. So because we encounter 2 null values, which means this 4 does not have any more children. So we can just ignore that. Okay, now we still have a node 5, which means that this 5 is actually the right child of this 2, because we have already visited the left subtree of this 2. So now because we are done with the left subtree, now we are visiting the right subtree. So we are going to create one more entry 5 over here as the right subtree. Again, we have 2 more null values, which means that this right subtree is done. Now we don't have any more values. Okay, now we still have values, which means that this actually refers to a root node where we haven't visited the left and right subtree. Because remember that this is the left subtree we have visited for this 2, and this is the right subtree we have visited for this 2, but we haven't visited the right subtree for this original one. So now we are going to do that. So now we are going to add one more entry 3 over here, which is the right subtree of this original given one, and this 3 actually has null values, which means 3 does not have any more children. So we won't be adding any more entries over here, and we can just ignore that. Now we have reached the end of the string. So because we have reached the end of the string, we have created the binary tree that we are supposed to create, and we have completed the deserialization process, and we have converted the string into the binary tree. So this is the approach we are going to take. If we see the time and space complexity in this case, for the serialization process, the time complexity is actually going to be big O of n, because we have to iterate over n characters that are present, and the space complexity is also going to be big O of n, because we will have to create a string where we are storing all the n values. Now for the deserialization process, again the time and space complexity remains the same. Now we will have to create two methods for serialize and deserialization. So first of all, we are going to work upon serialize process. So I'm actually going to create a new public method that returns a string where recursively we can apply the pre-order traversal. And as an input, it is going to take the root value, and we are also going to pass the string value. Now inside this recursive function, first of all, we are going to find the terminating case. So if the given root is equal to null, then simply add the value to the string as null. If that is not the case, which means that root still has some value and it could have left subtree and right subtree. So now we are going to call the recursive function. So first of all, we are going to add the value to our string. Now we are going to call the left subtree and right subtree. So we are again going to call this recursive serialize method. Again, we are going to repeat the same process for the right subtree. Once this ends, we are simply going to return the string. Now from our main serialize method, all we have to do is just call this recursive serialize method and return whatever the answer we get. We are going to pass in root as an entry, and we are going to pass in an empty string. So now we are done with our serialize method. Now let's work upon deserializing method. Now again, for the deserializing process, first of all, we will have to create a recursive method to iterate over this given string data, and then we are going to convert all the string values into binary tree. So we are passing a list of strings in this case for this recursive deserialize method. And now first of all we are going to work upon the terminating case. If the given node is null, we can simply remove the value and then we can return null. Okay, if that is not the case, first of all we are going to note the whatever the value of this current string is, we are going to treat it as a root node, and then we are going to call the left subtree and right subtree. So we are going to create a new tree node called root. So whatever the current value of this string is, we are going to treat it as a root node. Then after adding the root node, we are actually going to remove that value. Okay, now for the left value, we are again going to call this recursive deserialize method, and that should be it. After this ends, basically we should have a root variable, so we can simply return root. Now from this main method, first of all we will have to create an array of string where we are actually splitting the string based on the comma that we initially created. After doing this, we are actually going to convert the string array into a list of strings. Now we will simply return whatever the answer we get by calling this recursive method. That should be it. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. So I will be trying to see other faster approaches and see I can make a future video on that. But so far you can find this code in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do subtree of another tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Google, Facebook, Apple, Bloomberg and Tesla. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode easy problem, and basically we are given the roots of two different binary trees called root and subroot. Now we need to check that whether there exists a subtree of this original root tree where the structure is completely same as whatever the subroot binary tree that we are given. If that is the case, we will return true. If that is not the case, we will return false. So let's try to understand this with an example. Basically, we are given two different binary trees called root and subroot. Now over here, we can see that the structure of the subroot, which contains the root value as 4, left child as 1 and right child as 2, where 1 and 2 does not have any more children of their own. The same structure is also present in this example as well. And because it is a subtree of this original root binary tree, we can return true in this case. So now let's take one more example to make things a little bit more clear. So in this second example, we are also given two different binary trees. Now if we see the structure of the subroot, we have a node 4. It has a left child and right child of 1 and 2 respectively, and they don't have any more children of their own. Now if we see this original root, we can also see a similar structure, and I'm focusing on the word of similar, not exact same, because in this case we also have 4, 1 and 2 present. But the thing is, notice that this 2 actually has another node or another left child 0 that is present over here, which is not the case in this scenario. So because this is not the case, we cannot say that these two are same, and these two are actually not same. So in this case we will return false. And basically we are trying to see that whether one tree is a subtree of another tree or not. So that's why the name of the problem is subtree of another tree. It is self-explanatory. And now let's see what are the different approaches to solve this problem. So this is the root and subroot we are given. Now over here we are trying to see that what would be the optimal solution for this problem, and basically we can clearly see that the answer in this case is going to be true, because this 9, 1 and 2 is also present as a subtree in this original root tree. So that's why we can return true in this case. The thing is, let's see that what is going to be the strategy. Well, the idea is we are actually going to iterate over this given root tree in BFS fashion. Now if you don't know what BFS is basically breadth first search, and you can see more details about that in this video I have done previously. Now let's focus on the problem at hand. So the idea is that at every single time we are going to iterate over this root node, and we are going to iterate in BFS fashion, which means we are also going to iterate its neighbors for every single node. Now at every single time we are going to compare it with this subroot tree, and the moment we find a match, we are going to iterate over both the trees in BFS fashion. So let me quickly show you what I mean by that. So first of all, in this root tree, I'm going to iterate over this root number 5. Now this root number 5 is not same as this root number 9. So which means I can't do anything over here. I have already iterated this value. Now I'm going to iterate its children. So first of all, I'm going to iterate over this root value 8. So this 8 is again not same as this 9. So we can ignore this case. Now we are at this position number 9. So this 9 is actually same as this 9. So because these two values are same, now I'm going to do BFS traversal for both of the subroot and root trees. Now from this 9, if I see the BFS traversal, basically I'm going to go to the left child. So left child in this case is 1. So again, I'm going to see the same thing. Even in this case, the left child is also 1. So yeah, I'm good up until this point. Now I'm going to go to the right child. This is 2, and the right child in this case is also 2. So yeah, again, I'm good until this point. Now I'm not going to stop my traversal. I'm going to keep on iterating till I find all the null values. So in this case, this 1 does not have any children left or right. So in this case, I'll encounter a null value. So I'll try to see the same thing over here. So over here, this does not contain any subchild of its own as well. So this is also null. So I'm good up until this point. Now if I try to see this portion, so this is also null, and this is also null. So because all the values are same and I found no other children that I can iterate over, in this case I can simply return true. Now there are two ways to do this problem. I can do it iteratively or I can do it recursively, and if you know my videos, I like the recursive method better, so I'm going to show you the recursive solution. Now let's see one more case where the answer is going to be the false. So suppose for the same example, we do everything right, but over here this 2 actually has a subchild called let's just say 7 over here. Now because this 2 has a subchild called 7, now the moment I am done iterating these values and I don't find anything, I'm good up until this point. But now at this portion, at this node 2, I'll find a value 7 over here, but when I try to find the same value over here, I won't be able to find, and because I won't be able to find, I'll return false. Now the time complexity is actually going to be big O of m plus n. Why m plus n? Because we will have to iterate over all the nodes that are present inside this given tree root and subroot, and m is the number of length of all the nodes that are present over here, and n is the number of length of all the nodes that are present in this subroot. And if we see space complexity, well, basically because we are doing it recursively, we might have to iterate over all the values, and the space complexity in the worst case could be m plus n as well. And now let's move on to the coding. So before we start working on each subtree method, first of all, we are actually going to have to create a new method where if we pass in the value of any root node and subroot node, it can determine that whether both values are same or not. So first let's do that. So we created an isSame method which takes in the value of two tree nodes. Now first of all, we are going to check that if both values are null, which would be the terminating case for our recursive call. So if both values are null, we can simply return true. Now if that is not the case, we will also have to check the scenario where one value is null and other value is not null. If that is the case, we will have to return false. Now there is also one more thing we'll have to check, that and that is the value of this s and t. So if the value of s and t, if they are not the same, we can return false immediately. And if everything is not returned by this point, which means that the value of s and t is same, so now we will have to check the left subtree of s and left subtree of t, and same thing we'll have to do for the right subtree of s and right subtree of t. So let's do that. Now from our main method is subtree method, first of all, we are going to check that if the given root is null. If that is the case, we can return false immediately. So if that is not the case, we will have to call our isSame method for this root node and subroot node. So let's do that. And if we get the answer to be true, we can return true immediately. Okay, so if this does not return true, which means this current root and subroot, they are not the same. If they are not the same, we will have to iterate over this node root for its left child and right child to see if they are same with this subroot or not. So let's do that. So now for that, we will have to call this isSubtree method again, and we are going to run BFS on this tree node root. Let's try to run this code. Okay, seems like our solution is working. Let's try to submit this code. Our submission failed. Let's try to diagnose. Oh, in this isSame method, we will have to check that whether the answer of both of them, if that is true or not. So we'll have to use AND condition. Let's try to run the code again. Okay, seems like this is working. Let's submit this code again. Okay, and now our code runs perfectly fine. It's faster than a lot of other solutions, and I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do construct a binary tree from pre-order and in-order traversal lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Microsoft, Amazon, Bloomberg, Apple, Uber, ByteDance, Google, Facebook and LinkedIn. So that's why I am paying my utmost attention. I hope you also enjoy the video. Now this is a very hated lead code problem, and let me show you why. This is from the solution tab of the LeetCode problem, where people have expressed their views very abruptly. Some people are saying why God why, some people are saying that it's time to leave for Himalayas, some people are saying that if you get this question they do not want to hire you and things like that. There are many other comments. The thing is, we do not want to focus on the negativity. Let's try to see that what is the approach to solve this problem, and then we are going to see that how can we be able to solve this problem if we encounter this in any interview, because our aim is to get into FAANG, not just dream about it. Now this is a LeetCode medium problem, but in my opinion this should have been a LeetCode hard problem. Now let's try to understand the problem. Basically we are given two integer arrays called preorder and inorder, and basically they are the preorder traversal of a binary tree and inorder traversal of the binary tree. Now based on these two arrays that we are given, we need to construct and return the original binary tree. So let's try to understand this with an example. So over here we are given as an input, we are given two different arrays, pre-order array and in-order array. Now somehow if we iterate over this pre-order and in-order array, there is only one combination of binary tree we can make, and which is this one. So that is the example that is given over here. Now let's see that what is going to be the different approach to solve this problem. But before we do that, the important thing in this problem is to understand that what is a pre-order traversal, what is the in-order traversal, and how can we use their properties to our advantage. So first of all, I'm going to show you pre-order and in-order traversal, how it works. So first of all, we are going to learn about pre-order traversal, and basically pre-order is a DFS kind of traversal, which is depth first search. If you want to know more about different kinds of traversal, you can check out my video over here. Now let's focus on the pre-order traversal for now. So basically in pre-order traversal, first of all we visit the root node, then we visit its left subtree, and then we visit its right subtree, and we keep on doing that until the nodes exist. So let's see that for this given example, what is going to be the path that we are going to follow. So first of all, we are going to visit the root node. So in this case, the first node we are visiting is going to be node number 5. Then we are going to visit its left child. So left child in this case is 3. So again we are going to visit node number 3, and then again we are going to visit its left child, because remember it's root, left subtree and right subtree. So left subtree still exists over here, so we are going to visit node number 1. Now left subtree does not, nothing more exists in the left subtree, so now we will start visiting the right subtree. So we now will visit the node number 7. Now after visiting the node number 7, now there is nothing exist over here, so again we are going to go back to the root, because we still have to visit its right subtree. So when we start visiting the right subtree, again we are going to follow the formula of root, left and right. So root node in this case is going to be 8, so now we are going to visit node number 8. After that we are going to visit node number 6, and then we are going to visit node number 9, which is the right subtree, and this is going to be the traversal path that we are going to take. Now let's see that what would be the in order traversal in the same manner. So again, as mentioned, the in order is also a DFS kind of traversal, but in this case the methodology we follow is that first of all we visit the left node, then we visit the root node, and then we visit the right node. So for this given example, what we are going to do is, first of all we are going to go to the left node all the way possible. So left node in this case is 1. So first node we are going to visit is going to be node number 1. Now for now we can't go left anywhere, so now we are going to visit its root node. So root node is in this case is going to be 3, and then we are going to visit its right node. So right node in this case is going to be 7. After doing that, after visiting all 3 nodes, now we don't have any more nodes to travel on the left subtree. So now we are going to visit the root node as mentioned over here, because we have already taken care of this left part. So now we are going to visit node number 5. Now again we still have values that we need to visit on the right subtree. So again we are going to take on the same initiative. So now the first thing we are going to visit is going to be the leftmost element for this right subtree. So leftmost element in this case is 6. So we are going to visit the node number 6 over here. After that we are going to visit the root node, which is 8, and then in the end we are going to visit the node 9 over here, which is this one. So this is how in order traversal works. So after understanding both the values and both the different traversal mechanism, let's see that what would be the optimal solution and how we are going to approach that. Okay, suppose this is the binary tree that we are given that we need to iterate over, and we are given the pre-order and in-order traversal for both of them. So in this case, the pre-order traversal for this tree is going to be, and the in-order traversal in this case is going to be. Now once we have both the values, let's see that what is the approach we are going to take. So if you closely observe both of these values for pre-order and in-order traversal, they both have something to offer. The thing they have to offer is that this pre-order allows us to determine that what the root of any section of the tree is, and this in-order allows us to determine that what is the left subtree and what is the right subtree of any given tree. How? Let me quickly show it to you. So if we see this pre-order traversal, the first value in this case is actually the root of the binary tree, which is 5 over here, which you can clearly see that the 5 is the root of the binary tree. So well, that is interesting information, but the thing is this alone is not helpful. If we see with this in order traversal for this 5, if we see the left side of this 5, there is only one entry over here, which is 3. And if we see in this tree, actually this 3 is the left subtree of this entire tree where the root is 5. Now if we see on the right side, the values are 6, 8 and 9, which is these 3 items, and this is actually the right subtree of this original given tree where the root value is 5. So now we actually have something meaningful that we can use. If we keep on repeating the same process, now for this pre-order traversal, again we see, okay, so the next value is 3. So 3 is already the left subtree. Now if we again break it from this in-order traversal, for this in-order traversal, we only have 3 value over here. We have nothing on the side, we have nothing on the right side, because the right side value is actually 5, which we have already identified that that is the root of this original value 3, which means we can determine over here that for this 3 it does not have any values on the left subchild and right subchild, because the very next value of this 3 is actually 5, which was already the root of this value 3. So now again we have some meaningful information. So far let's backtrack. The information we have found so far, that let me create an answer value over here where we have already found that the first value is 5, the leftmost value or the first left value or left subchild of this value number 5 is actually 3, and for this 3 it does not have any more children, so now we can add the values null over here. Okay, now we are done iterating up until this point, but we still have some more nodes that we need to iterate over. So based on this pre-order traversal, now the next node we have is 8. So now we know that the current root we are iterating over is actually 8. Okay, so we have this value 8. Now from this in order traversal, we actually have these 3 values where this 8 is actually in the middle, because remember this in order traversal allows us to determine that what is the left subtree and right subtree of any given root. So in this case, if the root is 8, then the left subtree is going to be the value 6 and the right subtree is going to be the value number 9. So we are going to use it to our advantage. Now for this value number 6, again we are going to try to see that what is on the left of 6 and right of 6, but in this case, since we don't have any more information for this value number 6, the left value is 5, which was the original root which we have already iterated over, and this next value is 8, which was the root of immediate root of this value number 6, which we have already iterated over. So now we can determine that for this 6 we don't have any other value, so which means that we have 2 null values. So again, now and same thing we can determine for this 9 as well, that for this 9 the leftmost value is actually 8 and in the right there is nothing over here, which means this 9 also does not have any more children. So now let's again backtrack based on the information we have found so far. So now on the right side, the value we got was 8, that was the root we iterated over, and we found that information based on the pre-order traversal. After finding this 8, now we started iterating over the left and right children of this 8. So left children was 6, so we iterated the value 6. Now the 6 did not had any more children, so we had the values null over here. And now then we had the value number 9, and 9 also did not have any more children, so now again we had the 2 more null values over here, and this is the actual binary tree that we were able to create based on this original given pre-order traversal and in-order traversal. And that is the solution that your interviewer is expecting, and that is what is needed for this problem as well. Now there are actually 2 ways to do this problem. There is an iterative way and there is a recursive way. If you know me, I love the recursive solution, so I'm going to opt for the recursive solution. Basically, what we are going to do is, initially we are going to find the root value, and then we are going to find the left subtree and right subtree. Now again we are going to pick one value, so we are going to pick the left subtree. So now even for the left subtree we will have a root value and its left child and right child, and again we are going to keep on repeating the same process, and we will be continuing to building our answer. And same thing we are going to repeat for our right subtree as well. So basically we are taking a bigger problem and then dividing it into a bunch of different smaller problems. I know this looks really messy, but you get the idea of what I'm trying to convey over here. And let's see the time and space complexity in this problem. So time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree, because we will have to iterate over both in-order and pre-order traversal, and originally it's going to be 2n traversal. The thing is, generically we can write it to big O of n. If we see space complexity, well, space complexity is also going to be big O of n, because recursively we might have to iterate over all the nodes, and it worst case scenario it could take big O of n space. This is a wonderful time and space complexity given that how complex this problem was, and based on the pre-order and in-order traversal we were actually able to build the solution for the binary tree. Now let's see the coding. So before we start coding, we will actually have to define that how we are going to use this pre-order and in-order array. Well, we are going to use this pre-order array to determine that what is the root value for any subsequent positions. And once we have the root value, we are actually going to use this in-order array to determine that what is the left subtree and right subtree for any given root. And once we have both the information, we are actually able to build our tree. Now the thing is, if you clearly understand that for this in-order array, we will have to look up at information much in much broader fashion than compared to this pre-order array. So what we can do is, in order to iterate over this in-order array, rather than iterating it just by considering this to be an array, we are actually going to create a hash map where we are going, which is going to allow us to iterate over this in-order array pretty fast. And so let me define two global variables over here. First of all, once we have these two information, now from our main method, first of all we will have to iterate over this in order array, and then we will have to populate this in order index map that we just created. So let me quickly run a for loop. Now we have our hash map ready to go. Now we will have to create a separate method where we are going to call the recursion. So first of all, let me create a new public method. So now I have created a new method called array to tree that returns a tree node, and as an input I'm taking the pre-order array, the left portion and right portion, and now we are going to create this recursive method. Now before I do that, I will also have to initialize the values for this pre-order index and also for this in-order index map, so that I'm going to do it. Okay, now back to our recursive method. So for recursion, first of all, we will have to create a terminating case, and the terminating case in this case is going to be that if the value of left is greater than the value of right, if that is the case, we break out immediately and we will return null. If that is not the case, first of all, we will have to define our root value, and root value we are going to define from our pre-order array. So our root value is actually going to be the whatever this pre-order index value that we have, and then we are also going to increment the value of this pre-order index as well. So this is the root value, and after that we are going to increment the value of pre-order index. Now since we have our root value, we are actually going to create a new tree node called root, and for this root node we are going to assign the value that we received over here. Originally, the value of this pre-order index is 0, which means that the first value we are getting from this pre-order is the main root of the tree. Once we get that value, we will have to create the left subtree and right subtree. So we will have to call this array to tree method again, and we are going to populate the value for left and right child. So for the left child, we are again going to call this array to tree method. Inside the input, first of all, we are going to provide this pre-order array as we found as it is. Now for the left subtree, we are going to keep the value same for the left value, but for the right portion, the value is actually going to be different, and that is going to be different based on whatever this root value we had. So in this case, for the first value for this pre-order array, the root value is actually 3. So now for the left part, we already have the value, but for the right part, we are going to have to provide all the values that are present after this root node. So we are going to do that. So for that, now our in order index map is very helpful. Now we have both the information ready to us. Now we are going to call the right subtree in the same manner, but in this portion we are going to treat whatever the right variable we had already, but now we are going to change the left variable. So for the left variable we are actually going to use whatever the value we had for the root value, and we are going to do it +1, and uh, as the right limit we are going to keep whatever the right limit we originally had. And after this recursion ends and after this function ends, we simply need to return the root variable. Okay, so now our recursive method is ready to go. Now all we will have to do is, from our main method we will have to call this recursive method that we just created. That should be it. So we are calling this preorder method, but we are providing the preorder array, and as the left position we are providing the value 0, as the rightmost position we are providing the value of whatever the preorder length is, -1, and that should do the trick. Now let's try to run this code. It seems like our solution is working as expected. Let's submit this code. And our code is pretty efficient compared to a lot of other solutions. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do validate binary search tree lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Microsoft, Bloomberg, Facebook, Uber, Google, Apple, ByteDance, Lyft, LinkedIn and Netflix. So that's why I am paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and one of the most liked tree problems on LeetCode. Basically, we are given the root of a binary tree and we need to determine that whether that given tree is a valid binary search tree or not. We are also given the definition that what a valid binary search tree is. Basically, for any given tree, if this root value or the node value, so if this is the value of the node, basically every single value that is present on the left of the node should be less than whatever this node value is, and every single value that is on the right side of the node should be greater than whatever this node value is. So if that is the case and that is true for the entire given tree, we can define it as a valid binary search tree. So let's take a couple of examples that are shown over here. So in the first example, well, basically the node value we have is 2. So in the left subtree we only have one value, that is 1, which is less than this 2, and on the right subtree we only have one value again, which is 3, which is greater than this node value 2. So in this case we can consider this to be a valid binary search tree, and in this case we will return true. But if we take a look at the second example, so in the second example we are given this root value as 5. So this node value is 5, that is okay. If we see on the left subtree we only have one child, and that is the value is 1. So this is again less than whatever the value we have for the node value. Now if we see on the right subtree, the value of this is actually 4. So 4 is again less than 5. So because this 4 is less than 5, and remember that we have the definition of valid binary search tree that everything on the right subtree should be greater than whatever the node's value is. So in this case, this value is actually not greater than the value of this root node. So in this case, this is not an valid tree. So in this case, we will return false. And this is what we have to define basically. Now, based on the definition, we can define that what a valid binary search tree is. That for any particular given node, if its entire left subtree, if that is less than that node, and if its entire right subtree, if that is greater than that node, we can define that to be a valid binary search tree. Well, if that is the case, the first intuition that comes to our mind is that for any given node value, what we can do is we can check its left child and right child. If the left child is less than it and right child is greater than it, if that is the case, we will keep on repeating the same process for all the subsequent left child and right child with its root node, and in the end, if we reach to the end of this tree, we can return true immediately, saying that this is a valid binary search tree. Well, let's try to apply that same logic for this particular example. Basically, we are given this node 5. So this 3 is actually less than 5 and 8 is actually greater than 5. So in this case, this portion is actually valid. Now again, for this 3, this 1 is less than it and 4 is greater than it. Again, this portion is also valid, and same is true for this 8, 6 and 9 as well. So in this case, we can define this to be a valid binary search tree, and we can return true in this case, saying that this is a valid binary search tree. But the thing is, this solution is not the most optimal way to solve this problem, and let me quickly show you why. Because based on the same logic for this 5, this 3 and 8 again, okay, this is less than, this is greater than, so far this is valid. Again for this 3, this is 1 and 4, so this is less than, greater than, again this is valid. But now for this 8, this is also 2 and 9, so this is less than, greater than, again this is valid. So all three portions are valid. By definition we would treat this to be a valid binary search tree, and that would actually be a false positive. Why? Because remember that by the definition for this node, everything that is on the right side of this tree should actually be greater than this node 5, but in this case this 2 is actually less than this 5, and because of that particular case we will need to return false in this case. The thing is, based on our previous method we would have returned true. So let's see that what would be the actual optimal solution to solve this problem. So the idea for the optimal solution in this case is that we are actually going to do in-order traversal on the given binary tree to determine that whether it's a valid binary search tree or not. Well, if you want to learn more about different types of tree traversals, you can check out the video over here. Now let's get back to the question at the hand. So basically what the idea I'm suggesting is that if we do in-order traversal in any given tree, basically the idea for in-order traversal is that first of all we visit the left subtree, then we visit the node, and then we visit the right subtree. Also, this in-order traversal is a depth first search kind of a traversal where we are actually going in the depth first and then we are visiting the different nodes. So in this case, the traversal that we are going to do is that first of all we are going to go for the left subtree. So for this node, left node exists. Again for this node, left node exists. So first of all we are going to visit this left child. Then this child does not have any more children of its own. So now we are going to visit its node. So we are going to visit this node 3, and then again we are going to visit its right child, which is 4 in this case. After doing that, we are going to visit the node, and then we will keep on repeating the same process. So let's see that what is the path we are going to take for this in-order traversal. Well, for this problem, basically the path we are going to take is that first of all, as mentioned, we are going to visit this node number 1. So first node is going to be 1, then we are going to visit node number 3, and then we are going to visit node number 4 in the fashion of left node, and then right sub node. Then again we are going to visit the node, so we are going to visit node number 5. Now we are start going to keep on iterating on the right subtree. So even on the right subtree, again we are going to follow this method of left node and right. So for this left subtree, now this becomes the root node or the node, and this also has a left subtree existing. So first of all we are going to visit this node number 6, then we are going to visit node number 8, and in the end we are going to visit this node number 9. So this is the in-order traversal for this given binary tree. Now the thing is, if you see this traversal, basically everything is going in increasing order, and this whole thing is actually sorted. And this is the property of this in-order traversal that we are going to make use of, and we are going to solve it optimally. The idea is for any given tree that we are presented with, we are going to do up in order traversal, and during the in order traversal, basically the only thing we have to keep track of that any given node that we are iterating, whether that node is actually greater than its previous node or not. If it is not greater than its previous node, immediately we can return false. So in this case, because this was a valid binary search tree, we were able to get an in order traversal that is completely in increasing order, and all the previous nodes, they are actually less in value compared to its next subsequent node, and this property is maintained throughout the entire journey. Now let's see one example where this is not the case. So in this example, we can clearly see that this node 2 is at the correct place, and this is not a valid binary search tree. So let's see the in order traversal over here. So in this case, the path is going to be, the next node we are going to visit is actually 2, and if we compare this node 2 to its previous value, the previous value is actually 5 is actually greater than this 2, which should not be the case. And immediately at this point only we can conclude that this is an invalid binary search tree. We will return false immediately in this case, and that is the answer we are going to use. Now actually there are two ways to do in order traversal for any given binary search tree. There is an iterative way and there is a recursive way. If you know me, I like the recursion better, so I'm going to show you the recursive way in the coding, but it can be also done iteratively as well. And the tricky part in this problem is to identify that we need to solve this problem using in-order traversal. If we see time and space complexity, in this case the time complexity is actually going to be big O of n, where n is the number of nodes that are present. For the space complexity, we are using recursion, and we might have to store n characters in the worst case scenario. First of all, we are actually going to define a global variable called previous to store the value of the previous element. Now let me create a new in order method that would be our recursive method. So now I have created a new Enorder method that returns a Boolean answer, and we are taking just a root value as the input. Now, first of all, we are going to create the terminating case that if the given root is equal to null, we are going to return true. If that is not the case, first of all, for the Inorder traversal, we will have to call the leftmost function or leftmost value. So we are going to do that. So first of all, we are going to see that if the answer for the root dot left, if that is false, we will return false. If that is not the case, we will move on towards our next condition. Okay, so if we did not return false from our left side subtree traversal, then we are going to check our condition. So the condition we are going to check is that whether the current root value, if that is less than or equal to the previous value. If that is the case, which means that we have actually found an invalid binary search tree, so we can return false immediately. So if we don't return false by this point, which means the previous value was actually less than whatever the current root value we had, which is a good sign. So now what we are going to do is we are going to update the value of our previous variable. So that is going to be the current root value. And then after that, we are going to call the right side subtree as well. So we can simply return the Inorder for the right subtree. Now from our main method, all we will have to do is we will have to set up the value of the previous character. So initial value is going to be the null, and then we are going to call this Inorder method. Okay, seems like our solution is working as expected. Let's submit this code. And our submission runs pretty efficiently compared to a lot of other solutions, and that is because the code runs in 0 milliseconds. I would be posting this in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop LeetCoding till we get there. Today we are going to do Kth smallest element in binary search tree LeetCode problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Uber, Amazon, Microsoft, Facebook, LinkedIn, Apple, Google, and Bloomberg. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are given the root of a binary search tree, and we are also given an integer called k. Now we need to return kth smallest value from all the given values inside any given binary tree. So let's try to understand this with a couple of examples that are presented over here. So this is a binary search tree we are given, and if you notice the important property of binary search tree, where for whatever the root node, everything on the left subtree is less than that root node, and everything on the right subtree is greater than that root node that is present for this BST. So that is the definition of binary search tree. I'm just making it clear. And now for this example, this is the binary search tree we are given, and we are also given the value of k to be 1, which means we need to return first smallest value. So in this case, the first smallest value or the smallest value is going to be this value 1, and this is what we need to return as the output. Let's take one more example. So in this case, again, we are given a binary search tree, and we are also given the value of k is equal to 3, which means we need to return third smallest value. If we see in this case, this 1 is actually the first smallest value, same with this 2 is the second smallest value, and same with this 3 is actually the third smallest value. So in this case, we will have to return this 3 as the answer. So I hope that you have understood the problem by now. Now let's see that what is going to be the optimal approach to solve this problem. Okay, suppose this is the binary search tree that we are given, and we are trying to find the kth smallest value at any given position. So the idea I'm suggesting is that for this particular binary search tree, if we make the sorted array of all the values and we sort them in increasing order, then whatever this array we have created that is already sorted, based on this, it becomes pretty easy for us to find the kth value. How? All we have to do is just look up in this array, and we will be able to find the value. Let me quickly show you what I mean. So for this particular binary search tree, if we see the sorted path, where the first value is 1, then we have the value 3, then we have the value 4, and then we have 5, 8, and 9. And this is the sorted path that we have been able to generate. Now once we have this value, it becomes pretty easy for us to find any kth position. How? Suppose we are given k is equal to 2, we can immediately return second smallest value, which is the second value in this case, which is the value number 3. If we are given k is equal to 5, then we simply need to return this value number 8. if we are given k is equal to 3, we can simply return this value number 4. So now you get the idea that once we have this sorted path, it becomes pretty easy for us to find any kth position. So all we will have to work on is that from this given binary search tree, how can we actually create this sorted path? And if you know, or if you have followed my previous video, you know the answer. The answer is actually in-order traversal. So let me quickly show you the optimal solution using in-order traversal for this problem. Okay, so in-order traversal actually a depth first search kind of a traversal, which means that first of all, on the left side of the subtree, we go to the leftmost position, then we visit its node or its root value, and then we visit its right subtree, and we keep on repeating the same process. So let's see that what is going to be the path in this case. So path in this case is, first of all, we are going to visit the leftmost element, which is 1. So we'll visit node number 1, then we will visit node number 3, then we will visit node number 4 based on following this left node and right more formula. After that, we will visit the node again, which is 5, and then we will be on the right side of the subtree. So again, on the right side of the subtree, we will have to follow the same path, left node and right. But in this case, since this right side of the subtree does not have any left children, so we won't be able to update or traverse any left value, but we would be able to traverse the node value. So again, we will travel the value 8, and then in the end we would traverse the value number 9. So in this case, this is the path we are able to generate from this given input binary search tree using this in-order traversal. And if you see this path, this is actually increasing order, and this path is actually sorted, which is very good for us. So suppose we are given the k is equal to 3. So if kth value is 3, we can simply return 4 immediately. If we are given k is equal to 5, then again we can return this value number 8 immediately, as mentioned earlier. And this is the approach we'll have to take to solve this problem optimally. Now if you want to learn more about different kinds of tree traversal, check out my video over here. Now let's see the time and space complexity in this case. The time complexity is actually going to be big O of n, where n is the number of nodes that are present inside any given tree. And if we see space complexity, the space complexity is also going to be big O of n to accommodate our in-order traversal. There are actually two ways to solve this problem. One is the recursive way and second one is the iterative way. Now since you know me, I like the recursion better, and even in the coding, first of all, we are going to create our recursive method called inOrder, and that is going to return an array. So I have created the inOrder method that takes in a root value and also that takes in an array list. Now first of all, we are going to check the terminating case. So if the given root is equal to null, we can simply return whatever the array value we have. Okay, if that is not the case, first of all, we are going to call the inOrder function again, and we are actually going to call for the left subtree. So we are going to call with the root dot left child, and we are also going to pass in the value of whatever the array we already received. Once that is done, we are also going to add whatever the node value we have. So we are going to add the value for that particular root, and in the end we are also going to call the inOrder method again for the right side of the subtree, because remember, for the inOrder we are actually following the method of left node and right. So with this time we are going to pass in the value of the right child, and we are also going to pass in the value of the whatever the array we have created. Now once this method runs, simply we need to return this array list that we have been creating. Okay, now from the main method, first of all, we are going to create a new array list called nums. In order to populate this, we are actually going to call our inOrder method, and we are going to pass in the value of the root, and we are also going to pass in the value of a new array list. Once that is done, all we will have to do is basically from this array list, we simply have to return whatever the k minus 1th position element is, because remember, this k is actually 1 index, meanwhile the array list we have been creating, that is 0 index. So that is one tricky thing that we will have to take care of. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty fast compared to a lot of other solutions. It is also very efficient in terms of space complexity as well, and I will be posting this in the comments so you can check it out the solution from there. Thank you. Hello friends, we are not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do lowest common ancestor of a binary search tree lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like LinkedIn, Facebook, Amazon, Apple, Google, Microsoft, Uber, Reddit and Twitter. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode easy problem, and basically first of all we are given the definition that what a lowest common ancestor means. The lowest common ancestor is defined between any two nodes P and Q, such as that the lowest node in given tree that has both P and Q as the descendants, where we allow a node to be a descendant of itself as well. We are given a binary search tree and we are also given two nodes in that binary search tree, and now we need to find the lowest common ancestor between those given two nodes. So let's try to understand this with this example. Basically we are given a binary search tree over here, and we are also given the value of P and Q to be 2 and 8. So subsequently if we see over here, 2 is located at this place and 8 is located at this place. So the most common element or the immediate common element that we can find is actually 6 in this case. So that's why in this case we are going to return 6 as the answer, because that is the lowest common ancestor between the node 2 and 8. If we take one more example in this case, so over here we are given this P is equal to 2 and Q is equal to 4. So P is located at this 2 and Q is actually located at this 4. Now if you see in this case, actually this 4 is a descendant of this 2. So that's a given fact. But we are, remember, we are also told that we allow a node to be a descendant of itself as well. So in this case, since this 2 and 4, so 4 is already a descendant of this 2 and 2 is already a descendant of its self. So in this case, we will have to return this 2 as the answer. And that is what is given over here. We are given one more example where we are given only two nodes for this given binary tree. So the binary tree looks like this 2 and 1, and in this case we are given the value of this P to be 2 and Q to be 1. So again we can see that in this case this 2 is already a descendant of itself and this 1 is actually a child of 2. So because of that, 1 is also a descendant of this 2. So in this case we will again return this 2 to be answer. Now I hope that this makes understanding the problem more easier, and now let's see that what is the approach we are going to solve this problem. Okay, first of all, I'm actually going to show you a bunch of different binary search trees, and for all of those binary search trees I have created some P and Q values, and we are going to see that what was the lowest common ancestor and why that was the lowest common ancestor. Right now we already know that important property of binary search tree, and that is that for any given root value, everything on the left subtree of that binary search tree is actually less than that, and everything on the right side of that binary search tree is greater than that. We already know this important property, and we are going to take it to our advantage based on this given root value or any root value and with subsequent P and Q values. So if we see over here in this case, the given value of P is actually 6, and if we start traversing through this binary search tree, immediately we would find the 6 to be present over here. So because we find the 6 to be present, there can only be one possibility, that this Q or whatever the value of Q, that would either be on the left side of the subtree or right side of the subtree, but we already find the value to be 6 over here. So immediately we can return 6 to be the lowest common ancestor, because anyways this value of Q is somewhere supposed to fall inside the remaining binary search tree, and in this case it is on the right side of the subtree. So we will return 6 as the answer. This makes sense, right? Now the next example, again we are given the same thing. We are given this value P to be 11 and Q to be 9. So we know that this P is over here and Q is over here. 11 is going to be answer, but let's go ahead with our algorithm. So first of all we'll start iterating over this root. So the root value is actually 8. Now for this root value we are going to compare it with the values of P and Q, right? In this case the value of P and Q both are actually greater than this 8. So because both are greater than this 8, we know based on the property of binary search tree that they are meant to fall somewhere on the right side of this given binary search tree. So we will start iterating over the right side of the binary search tree to either find the values of P or Q, or if we can't find, we will try to find the lowest common ancestor. So when we start iterating over on the right side of the subtree, we will ignore this left side of the subtree. We don't care. Now this value is 11. This value is 11 is actually matches the value of this given P. So immediately whenever we find a match with either P or Q, we can return that to be the lowest common ancestor immediately, and in this case this is going to be the answer, because this 9 is meant to be somewhere below this binary search tree, and in this case it is immediately right here present. So we will return this 11 to be the answer, which is the lowest common ancestor. Let's take one more example which is very similar. So in this case this value is P is equal to 3 and Q is equal to 1. Now again based on our algorithm we will start start traversing over this binary search tree. Now the first value we traverse, whenever we compare its value with this P and Q, immediately we find a match with this P to be over here. So because we find a match over here, do we really need to iterate over this given binary search tree? Well, the answer is no. Why? Because we know that this Q value is somewhere going to be down below, and that is always going to be this descendant of this P. So again, we are going to return the values 3 as the lowest common ancestor. So far it makes sense that whenever either we identify the value of P and Q, we can return that to be the lowest common ancestor immediately. But what happens if the case is a little bit different? So in this case, I have given the value of P to be 6 and Q to be 9, right? Again, let's start with our algorithm. So we'll start iterating over this binary search tree. So first of all, this value is actually 5. So because this value is 5, we'll try to see that, okay, we'll compare it with this value of P and Q, right? So actually this 5 is less than P and less than Q. Both P and Q are greater than this root value. So immediately it is meant to fall somewhere on the right side of the subtree. So now we'll start iterating on the right side of the subtree. We'll ignore these two because we don't need them. Now again, this value is 7. So let's compare this 7 with this value of P and Q. Well, if we compare this 7 is actually greater than this P, and this 7 is actually less than this Q, right? So we can conclude this 7 actually falls somewhere in the middle, because for the 7, on one side 6 is meant to be because 6 is less than 7, and somewhere on the other side 9 is meant to be because 9 is greater than the 7, based on the property of a binary search tree. And if we utilize that to our maximum advantage, we can immediately determine that this 7 is the common point between this 6 and 9, where on one side 6 resides. So 6 resides on the left side over here, and 9 resides on the right side of the subtree. So on the right side of the subtree, this is where 9 resides. So we'll return 7 to be the answer in this case. And this is the approach we are going to follow. So every single time for any given tree, we will start iterating over that tree, and we are going to compare its value with P and Q. Based on that, we will decide that whether we go on the left side of the subtree or right side of the subtree. The moment we find a match between P and Q, whatever the value we found, if we find that, we will return that to be the lowest common ancestor. If we don't find a match, and if we are in a situation where this value of P is on the left side of this any root value and Q is on the right side of any root value, then immediately we can return that value to be the answer. And this is the approach we are going to take to solve this problem, and this is the optimal way to solve it. Now there are two ways to solve this problem. We can either solve it recursively or we can solve it iteratively. Now I like recursion better, but iterative method will also work as expected in this case. Now for the recursion, if we see the time and space complexity, the time complexity is actually going to be big O of n, because we'll have to iterate over all the values in the worst case scenario. And for the space complexity, the space complexity is actually going to be big O of n as well, because we will have to maintain the runtime stack for this recursion method. Well, one good thing in iterative method is that for iterative method, the time complexity is still going to be big O of n, but for the space complexity, we can actually use a constant space complexity for the iterative approach. But in the coding, because I'm trying to improve my recursion, I will be showing you the recursive method. But just remember that iterative approach would be the better option in this case. So we are going to use the same method as our recursive method. And first of all, in this method, as an input, we are given this root value, we are given the value of P and Q. So first of all, because we don't need to deal with this tree node, we will actually have to deal with this integer value. So I'm going to initialize three variables called the parent value, P value and Q value, and I'm going to assign the values based on this whatever the input we get. Now we will have to check that whether this parent value, if that is the common point between P and Q, or either P and Q falls on one side or other side of this binary tree. If that is the case, we will call our recursive method again. So first of all, we are going to check that if this P value and Q value both are greater than this parent value. If that is the case, which means we will have to iterate on the right side of the subtree. So we are going to call the iterative method on the right side of the subtree. If that is not the case, we are going to check that whether this P value and Q value both falls on the left side of this parent value. So again, we are going to do that. So if both P value and Q value are less than the parent value, which means we will have to search the left side of the subtree. So we are going to do that. Okay, if that is not the case, which means that whatever this root value we are at, that is either P or Q value, which means we can return root immediately. That's it. That should be working. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions in terms of time complexity. I already mentioned you that for the space complexity, this recursive solution is not the most optimal, but I want to practice recursion, so that's why I did that. You can find an iterative solution that works as well. And I would be posting this in the comments, so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today actually we are going to learn about a new data structure, and we are actually going to learn to implement a trie or a prefix tree. And if we see some of the companies where I want to get a job who already asked this question, there are companies like Amazon, Google, Twitter, Microsoft, Oracle, Apple, Facebook, Goldman Sachs, Uber and Bloomberg. So that's why I am paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and basically we are going to implement a trie over here or a prefix tree. So first of all, in the problem statement we are given the definition that what a trie is, and actually I'm going to show you very eloquently that what a trie is and how it works. But let's understand the definition first. Basically a trie is a prefix tree, which is a tree data structure that is used to efficiently store and retrieve keys in a data set of strings. There are a bunch of different applications of this trie data structure, and I'm going to go over all the applications soon as well. Now, if we see that what is needed in this problem, basically we need to initialize a trie object first of all. Then we need to create three different methods which are mentioned over here. So first method is the insert method, which does not return anything, and basically we are only given the input as a string word, and we need to insert this word inside this new trie object that we are initializing. After doing that, we could be given a search method where again as an input we are given a string called word, and we need to return true or false, which means that whether if this word exists inside this trie object that we have created, we need to return true, otherwise we need to return false. And there is also one more method where again we are returning true or false, and the name of method is starts with, where we are actually given a string and the name of the string is prefix. But basically we need to check that whether this prefix actually exists as a part of any existing word inside this trie object, and if that is the case we need to return true. If that is not the case, we need to return false. So here is an example that we are given. So suppose we are given as an input where actually first of all we are creating the trie, we are inserting some word, we are searching for some words, we are doing the start with operation, and this is the explanation. So basically we initialize the trie object as mentioned. Then first of all we insert the word apple. So okay, so currently apple exists over here. Now again we search for that whether apple exists or not, and because it exists we return true as the answer. Again we search for with the word app. But the thing is, remember, so far we have only inserted the word apple. App does not exist as a whole word, so that's why we return false. Again we search for starts with method for this word app, and remember, because this app is actually a prefix of this apple, so we return true in this case, and so on and so forth. We can do bunch of different operations. So this is what is needed. Now let's understand what a trie is. Okay, so first of all, let's try to understand that what a trie actually is. Basically, a trie is a tree-like data structure, but it's a little bit different and a different variant of a tree. Now, if we know for any single tree, the basic properties are that every single tree has a root node. Now, this root node has some subsequent children nodes. There could be n number of different children, and those children can have some children of their own, and their links actually found some meaningful relationship. So that is what we are going to use to generate this trie, but we are actually going to generate this trie to store different string values per character. That is the important property, per character. So it makes us easier to understand or find different words or different strings, and there are n number of applications of a trie. Let's try to understand trie with some example. So first of all, as any different tree, we are actually going to have a root node, right? Now suppose for this root node, what we are trying to do is we are trying to add some different string value. So let's take a string value. Suppose the first string we are trying to add is actually the word FAANG. So if we take this word FAANG, first of all we will have to add the word F, because remember I already told you we are going to do it character by character. Then we will add A, N and G. We are going to add it in this sequence. So in order to do that, logically speaking, for this root is going to remain common. The thing is, first word we will have to add is FAANG. But the thing is, first we will check that whether is there any children of this root node which is actually F. If that is the case, we are actually going to leverage that. But this does not have any children. So if this does not have any children, we are actually going to create a new children F. Now again, with this F, there is no children, that is A. So again we are going to create a new children, then again we are going to create a new children, and then we are going to add the values of N and G as well. After adding this, we have actually created a root inside this trie data structure which represents this word FAANG that we were originally trying to create. After creating that, we will have to find some way to identify that this FAANG word has actually ended. So what we are going to do is we are actually going to create a special character or a special node over here which we are going to denote as an end node, which defines that the word has actually ended over here, right? After doing that, let's try to add one more word. So suppose rather than FAANG, we are trying to add the character MAANG. So let's try to again add MAANG over here. Now for this MAANG, first of all we are going to check that whether this M exists as one of the children of this root node. So M is also no children. So first of all we are going to add M, and then we are going to add subsequent characters, and we are going to link them with this path. After that, in the end, we are actually going to add a special character and denote that the word has actually ended over here. So let's do a quick recap. Basically what we have done so far is we have actually created two separate branches where if we go depth first search diving in those branches, we would actually find those subsequent words in those particular branches. So it makes pretty efficient for us to identify any string and to see that whether it exists or not, and predict that what the person is going to copy. Now suppose I'm trying to add the next word fan. Now for the adding this next word fan, what we are going to do is first of all we are going to check F exists or not. So F exists over here. So because F exists, we are actually going to leverage that. So now we are not going to add any entry over here. Again, this A also exists as one of the children of F. So again, we are not going to add any entry over here. Now this N. So N is not a children of this original A. So we are actually going to create an entry over here. So we will create an entry over here. And we are actually going to name it as N. And now since this word ends over here, we are actually going to create this end node over here. So again, remember, if we go depth first search in this direction, we will actually be able to find this word fan, and that is the whole purpose of a trie. Now let's try to add one more word which is man. Sorry, M-A-A, ma. So if we try to add this word ma, so first M also exists over here, A also exists, and A also exists. So because these three exist, we are actually not going to break this link and create this end word over here, or we are not going to do that. Actually, we are going to keep this as it is, because this MAA is actually a prefix of this original word MAANG that we have already added to our trie, and that is why a trie is also called a prefix tree. So now the word makes sense that why a trie is called a prefix tree. And basically this is what we are trying to implement. There are a bunch of different applications of a trie, and let's see some of the applications that are really cool in real life world. So before we start implementing the method, first of all, let's understand that what are different applications of a trie. So applications like autocomplete, where you type something and it automatically gets completed or understood by that particular product, that is implemented using trie. So features like Google Chrome, Amazon, where you type few words and then it automatically understands that what you are trying to do and automatically gives you the answer, that is implemented using that. All the spell checks or all the dictionary related mechanisms, they are also implemented using some versioning of a trie. Games like word search, word puzzle, wordle, they are also implemented using a versioning of a trie. And features like predictive text search or expected text search, that you type something, it automatically expects that what could be the next potential words. Typically you see that in YouTube, Google all the time. They are also implemented using tries. So these are only few but very powerful applications of a trie, and there are hundreds of them. I haven't mentioned them. So that's why trie is important to understand. Now let's move back to our question and start implementing those three methods. So first method they are asking us to implement is an insert method, where we are not returning anything, but we are inserting different strings into our trie. So for this example, we are actually going to implement these 4 different types of strings into our trie, and we will see that what would be the logic behind it. Now, as mentioned earlier, that every trie actually has a root node. So again, with our trie, we are also going to have a root node. Now from this root node, the idea we are going to use is that whatever string we are trying to insert, first of all, we will check that whether the first word that we are trying to implement or the first character we are trying to implement, if that is present as one of the children of the existing root node or not. If it is children of that particular root node, we would keep on branching for that particular child and keep on updating the number of characters that we are trying to implement. If it does not exist, we will actually create a new node or a new branch, and we will add that entire word into that branch. Now, as mentioned earlier, the moment we reach to the end of that particular node, we will actually have to create an end node to denote that this word actually ends over here. So let's start implementing what is being asked over here. So first we are trying to implement the word apple. So A does not exist as any of the children of this root node. Currently it has no children, so we will have to create a new node. So first we are going to create a new node for apple. Okay, so let me create a new node A, and then I will keep on appending all the remaining characters. And after adding all the word, because this word ends at this E, I am actually going to create a special node, and I am going to denote it as an end node. So that is for us to understand that this word actually ends over here and we don't need to move any further. Okay, now next word we are trying to implement is G. And also remember one thing, I forgot to tell you that this root can have potential 26 different children, right? And this 26 different children can have 26 different children of their own. So the mechanism we are going to implement to find that whether a node contains any particular children or not is actually going to be used based on some key value mechanism. And because it's a key value mechanism, the whole operation of searching that whether any node or anything, if that is part of any children of that particular node or not, that is being done in constant time, so that it helps us understand, helps us to maintain the consistency and speed of our data structure. Now let's move back to adding the word Google to our trie. So for the word Google, we do not have any children that is starts with G. So we are also going to create a new node over here, or new branch over here, where first character is G, and then we will add all the remaining characters. As previously mentioned, at the end of the word, we are going to create an end node. Okay, now things become a little bit interesting with this word Amazon. So for this word Amazon, when we start checking that whether this A is a children of this root node or not, we find that A is already a children. So we will keep on updating the value over here that okay, we have already find a word or a character that is already a children, and then we will keep on moving to the next character. So first this A is already present, so we ignore that. Now next character we want to find is M. So for this M, we will try to see that whether this A contains any children that starts with M. But the thing is, currently this A only contains one children that starts with P and not M. So we will have to create a new branch over here. So let's create a new branch. So new branch starts with M, and then we will add all the remaining word characters over here. Okay, and now the next word we are trying to implement is amazing. For the amazing, okay, we already have a children of this root that starts with A, so we have taken care of this. M is also present as one of the children. Okay, now A is also present as one of the children of this M. Okay, so that is also good. Now this Z is also present over here. Now for this I is actually not present as one of the children of this Z. So we will actually create a new branch over here that starts with I, and then we will add this N and G over here, and in the end we will create, or we will add the end node over here. And now we have actually inserted these 4 characters as these 4 strings into our trie. And if you see, we can find each one of them by going in DFS motion in any particular branch. So first of all, this gives us the value Google, this gives us Apple, this gives us Amazon, and this gives us amazing. So that is how tries typically work. Now let's move on to the next method that is being asked. So for this search method for our trie, we will be actually given a word as the input, and we will have to check that if that word exists inside our given trie, we will have to return true. If it does not exist, we will have to return false. So let's start implementing the same method, and actually we are going to use the same trie that we have created. Okay, so let's use the same trie that we have created earlier, and we will try to see that whether these 4 strings do they exist inside this given trie or not. So let's understand the logic behind it. Well, if the string exists, basically all we will have to do is, first of all, we will check that, okay, whether the first character, if that is the one of the children of this root node or not. If that is the children, we would keep on checking its children for this next subsequent words and try to complete this entire word. If we are able to complete this entire word without this try breaking or not able to find the children, if we reach to the end, we can conclude that this word exists. If we cannot come to the end, we will conclude that this node does not exist. So first of all, let's try to see in this example. So for the first word is A. So A exists over here as one of the children. So we will ignore this one. Now next word is M. M also exists, so we will again ignore this one. The next one is A, again this word exists. Now Z, I, N, G, they all exist in this particular fashion. So this word amazing exists inside this given try. So because it exists, we will return true as the answer in this case, right? Now let's try to search for this word good. Now for this word good, the first character is G. So first character is G present over here. So okay, we are good up until this point. Next character is O. O is also present. Again, O is also present. So we can ignore first three characters of this good. Now for this next O, we do not have a children that starts with value D. So because of that, we do not have any new branch over here that starts with D. So we can actually conclude that the word good does not exist in this case, and because it does not exist, we will return false over here. Okay, now let's try to search for the word Googler. So again, for this word Googler, okay, G also exists, O exists, O exists, G exists, L exists, and E exists. Okay, up until this point all the words exist, but when we try to search for the next word, we actually encounter that, okay, this is the end node of our try or of our DFS search for this particular direction. So because it is the end word, we will actually return false over here, because this word has not been completely searched, because it does not exist inside our try, and we are actually able to do it pretty quickly and pretty efficiently. Okay, so now next word is app. So let's try to see that whether this word app exists inside our try or not. So first of all, we check for this word A. A exists over here. Then this word P. P also exists and P also exists, right? So we are up good up until this point, and our mind will say that, okay, because this word exists, we need to return true. But the thing is, that is not the case. The idea we are trying to do in this search method is that we are trying to see that whether the whole word that is given as the input exists as only a word inside this given try. But for this app, if we try to see the next node is actually the SL and E. So there are still some characters that exist inside this given DFS path that we are traversing, and the next node is actually not the end node. So because the next node is not the end node and there are still some more nodes that exist, this app is actually a prefix of original word apple, but not the whole word as it is. So that's why in this case we need to return false as well. And this is the important thing that is differentiating between this method, search method, and the next method we are going to implement. Now if we see the time and space complexity, in this case the time complexity for this method is actually going to be big O of n, where n is the number of characters that are present that we are trying to search in any given word. If we see space complexity, for the space complexity we are actually not using any additional space, so that is going to be the constant space complexity for this case, which is pretty efficient in my opinion. So now let's understand our starts with method, and we are also going to use the same try that we have created before, right? And we are going to see that whether the words that starts with these characters, are they present inside our given try or not. So again, this is very similar to the search method, where we are going to iterate over word by word or character by character for any given word, and we will see that whether that is present inside our try or not. If that is present, we can return true. If that is not present, we will return false. So let's see that in action. So first of all, we have this character A. So A is already one of the children of this root node. So okay, we are good up until this point. Then we have M. M is also a children over here, and then we have A. So A is also a children of this one. So we can conclude that because this word ended, we do not have any more things to search for, and all of the characters, they were present inside this given try. We would actually return true. In this case, they are saying that the word that starts with AMA is actually present as one of the children or one of the branches of this try. Now let's try to search for this word APK. So A exists and P exists, but the thing is, for this P we do not have any children that starts with K. So because of that, this K is not present. We can actually return false in this case, saying that we do not have a word that starts with APK as the prefix inside our trie. And remember, because we are searching through prefix, that is why this is also called prefix tree. So yeah, mind blown, right? Mine as well. Now let's try to search the word good. Well, there is Google, but there is not good. But the thing is, Google is pretty good. Yeah, so that's why it's one of my dream companies. But let's try to search that. So okay, this is GOO. So GOO is present over here, but this D is not present as one of the children of this O. So because of that, we will also return false in this case. Okay, now we have this word apple. So apple is actually the entire word that is present over here. And if you look at it, we do have a word that starts with the word apple, even though it ends at apple, but the thing is also it starts with apple, right? So and the name of the method is actually starts with, so why should not we return true in this case? So this will also become true, that okay, word that starts with apple is present inside our given trie, and that is the logic we are going to use to implement the starts with method. Again, very similar to the search method, just a little bit different variations. Now if we try to see the time and space complexity, in this case the time complexity is also going to be big O of n, that is where n is the number of characters that are presented inside any word that we are trying to search. If we see space complexity, the space complexity is also going to be big O of 1, or constant space complexity, because we are not storing anything in our text stack. This problem is asking us to implement insert, search, and starts with method. But before implementing these three methods, first of all, we'll have to define that what a trie node is. This is only a trie class. So I would be creating a separate class called trie node. Now in this trie node class, first of all, let's go over some basic methods that we are going to use that will enable us to do a lot of things. First of all, we have defined a finite number of cases R, which is 26, because any single node can only have up to 26 distinct children, because each children represents a character inside the alphabet. Now every single trie node has a certain set of links, and links are defined by the children of that particular node. We also created some more methods, so let's go over them. So one method is contains key method, where we pass in a character and we get the answer that whether any particular link or any particular node does that contain that particular character as one of its children or not. And we can get the answer in a constant time complexity, because remember, we are using array indexing, and the maximum possibility of indexing can be 26, and we can get the answer immediately. Same, we have a method get, where we provide the character and we get the answer that whatever the value of that particular character is inside any of the children of any trie node. We also have a method put, where we provide the value of a character and the node we are trying to put it as. And we also have set end and is end method. That is to define that whenever we run out of words that we need to put in any single trie block or any single trie branch, the last node is going to be is end node, and we will mark its value to be true. So now let's start implementing the trie node. So first of all, we will have to create a trie node root. So let's do that. Now since we have our root node, first of all, for this public trie method, we are going to initialize the root. After doing that, first of all, let's start working on our insert method. So for our insert method, we are going to have a root node. Now we are going to iterate over the given input word. We will define that what is the current character we are at. Now first of all, we will have to check that whether the given node we have, if that contains that particular key or not. So if the given node does not contain that key, we will actually have to create a new entry over here. So we will use our node.put method, and inside that we are going to pass in the value of the current character, and we are going to create a new trie node for that, and then we are going to update the node's value. And once this loop ends, basically the last node we are at, we will have to set its value to be the end node. So we are going to mark its value to be the set end value, and which would basically, so it defines that this is the last node. Before we work on the search and starts with method, remember, both search and starts with method, they are pretty similar to each other. So we are actually going to create a supporting method called search prefix. Once again, we are going to initialize the node to be the root node, and now we are going to iterate over the given word. So now we are going to check that if the current node, does it contains the given character or not. If it contains the given character, we can actually set the value of node. If it is not present, we simply need to return null, and that's it. And if we somehow reach to the end of this loop, we can simply return whatever the node we are at. Now from this our search method, basically what we are going to do is, first of all, we are going to initialize our try node and we are going to pass in the value of the word. Now we simply have to return that whether the current node we get in the return, and if it is not null and it is end, we can simply return true. And same thing we are going to do for our starts with method. So again, for our starts with method, we are again going to call the search prefix method, and basically all we will have to check that whatever the return value we get, if that is not equal to null, if that is not equal to null, we can simply return true, and that should be it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently compared to a lot of other solutions, and it is also very much efficient in terms of space complexity. The thing is, I was not able to come up with the solution on my own. I actually had to use a lot from the solution tab, so I just want to make it clear. So yeah, everyone has to go through it, and I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do design, add and search words data structure lead code problem. And if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Google, Microsoft, Apple, Facebook, ByteDance, Twitter, Uber and Lyft. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode medium problem, and as the name suggests that we are actually designing a data structure where for this data structure we have to support that we can add new words to this data structure, and if given any string we can actually find the previously added words or strings as well. So we are being asked to implement the word dictionary class. Now in the word dictionary class, first of all, we'll need to initialize the word dictionary object, and then we need to create two different methods. First method is add word method that takes in a string word as an input. Which being done, it adds the word to our data structure that we can use to match it later. And then there is a boolean method called search, where again we provide a string word as an input, and that returns true or false if that word has been previously added or not. We are also given one more condition, that for the search method there could be dots provided as inputs, where we can conclude dot to be any letter. So if we are given the word something like bad, that is already being added, and then we are asked to search for the word using b.d, actually these two words we can consider same, because this dot we can consider it to be a. So let's try to understand this with an example. Over here we are given a bunch of different add word and search word mechanisms, and this is the explanation provided. So basically, first of all, we initialize the object word dictionary. Now for that, first we add the word bad, dad, mad. We add all these three words. Now first of all, we search using pad. So pad is not present, so we return false. Then bad is present because we have previously added it. Then we are also given a word which is dot ad. So this dot can actually mean anything, and if we see, we already have a word like bad and dad, that both, and even mad, that all three of them, they actually match with this string, so we can return true in this case as well. And we are also given one more search criteria, where we are only given b dot dot, which means for these two dots we can conclude any other word, and since we already have a word bad added, we can conclude these two to be similar, and we need to return true in this case. So before we start the solution, first let's understand that what a trie is. If you want to check the full explanation, you can check out my previous video over here. Now let's move back over here. So basically a trie is actually a form of a tree, whereas any given tree, it has a root node. Now this root node can have many subsequent children, and each children can have some children of their own, and based on that we actually use trie to search, store and iterate over different strings. And for any given strings we actually use it character by character to store distinct values inside this given trie, and based on per character we actually store it in a manner where it becomes pretty fast for us to find that whether any particular parent node contains some character as one of its children or not, and then we iterate in some particular fashion, in DFS fashion, to find any words. So suppose these four are the strings we are trying to add. So let's initialize our trie data structure. So first of all, we are actually going to have a root variable. Now for this root variable, we are going to store all of these values one by one. So first let's store the value hello. As mentioned that for any given string, we are actually going to go character by character. So first of all, we are going to take the character h, and we are going to see that does this root node has a child that is actually starts with h. It does not. So we are actually going to create a new node over here, and this node starts with h. Now we are going to add all the values of subsequent characters because they don't exist. So I'm going to add append e, l, l, o. And after adding all of these values, actually we are going to have an end variable that denotes that this word has actually ended over here. So far, if we iterate in this direction in this given trie, we can actually form the word hello, and when we reach to this o, we will actually encounter a special node that denotes that this is actually the end node, and if whenever we identify that, we can conclude the word has actually ended. Now let's add this word hi. So if we want to add word hi, basically first of all we will check that whether this h exists or not. So h already exists as one of the children of this root, so we do not need to create a separate branch for this one. But the thing is, for this particular h, I does not exist as one of its children, so we are actually going to create a new branch over here, I, and we are going to denote that this represents this word h, and then because this word ends over here, we are actually going to denote an end node over here. Let's add one more word, that is pop. So if we want to add pop, again p does not exist, so we are going to add, or we are going to create a new branch, and we are going to add all of these values, and we are going to add the end node. Now this next word is pond. So again we are going to use the same methodology. So p and o exist as the children, so first two characters we are done with. Now from here we will have to create a new branch, so we will do that, and after that we will add our end branch, and this is the logic we are going to use to implement our insert or add method to add different strings inside our word implement data structure. And this is the logic we are going to use, that first of all we are going to check that any character exists as the children of the root or not. If it exists, we are going to leverage that particular branch. If it does not exist, we are going to create a new branch, and then we will keep on making separations, and based on that things becomes pretty easy for us to find different words. Okay, so for our search method, suppose this is the trie that we have actually created, and these are the words we have added. Let me quickly go over them. So first word is pen. If you look at this direction, we have the word pen, then we have the pot. So p is common, so then there is a branch out and we get the word pot as well. Same, we have cat, cars and bed in the similar sequence, and these are the words we are trying to search. So couple of words are just regular words. Then I have added some examples with the dots in it, so because they are more complicated ones, so we can understand that. So let's quickly start to go over and see that what would be our search policy for this given trie that we have created. So for this character pot, first letter is p. So from this root we are going to see that does there a children that contains the character p, and yes, we have a child that contains the character p. So based on that we will keep on iterating in that direction. So next character is o, so we have o as well, and the next character is t, so we have t as well. Now we don't care about this end node, because as long as we are able to generate the word that we were given, we are good up until this point. So over here we will actually return true to be the answer, that yes, this word is present inside the trie that we have created. Second word is pots. So again for the pots, we up until this pot we are going to go in the same direction, but this s is not present as one of the children of this pot, and because we encounter an end node over here, so we can drop out immediately and we can return false in this case, that yeah, we don't have any character that matches the word pots. Now this is a little bit interesting example. So for this .ar, the policy we are going to use is that whenever we encounter a dot to be a character, we will actually have to iterate over every single possible root using this dot to be the character, and see that can we make this AR to be part of that sequence or not. So let's quickly do that, and let me clean this up a bit. For this dot AR, the strategy we are going to use is for this particular dot, we are going to consider it that every single child of this root can be used over here, and then we will try to see that whether is there any place where second character is actually A. So first we go down this path. Okay, so P, we consider P as dot, right? Then we check that, okay, this is E and this is not A, so we cannot go on this path. Okay, now we backtrack. Now we keep this P to be dot. Now again we try to repeat the same process. This is A and this is O. So again this is not the path we are going to choose. That is going to lead us to this answer. We come back. Now okay, we are at this position. Again we check this child. So this child is actually C. We consider C to be the dot. Okay. Now from the C, the next character is actually A, and all over here the next character is also A. So that is good sign for us. So now we can continue in that direction. So now from this A, we will try to see that is there a child that is actually R. And yes, from this A, we also have a child that is R. And since we reach to the end of this word, we can return true in this case, that yes, this dot AR is present inside this trie that we created. Okay, so yeah, that's a wonderful news. Now let's focus on the next example. So next example is dot T. So for the dot T, actually we will have to branch out even more. So for this second dot T, what we are going to do is, again we are going to repeat the same strategy. We will have to go over every single child that is possible. So first we'll consider this P to be the first dot. So this dot is this P. Okay, now from this P, we will also consider two child to be separate dots. So for both the childs, okay, this is going to be the first dot. So we are good up until this point, but this value is actually not T, this is N. So we will have to backtrack. From this E, we do not have any child, so we will again backtrack and we will come back to this P to be one dot. Now from this P, we still have one more root that we haven't considered. So we will consider this O to be the second dot. And from this O, we actually have the last character T present. And that matches this string dot T. So if we go down this path, we will be able to generate this word, and that's why we will also return true in this case as well. And the same thing we are going to repeat for this dot ey strategy. So for this dot ey, what we are going to do is, first of all, we are going to consider this to be the dot. We will see, okay, this is E, so that is good, but this is not Y, so again we cannot go down this path. Again this is dot, this is not the path, this is not the path, this is not the path. So this dot ey is actually not present inside this entire trie block that we have created. So over here we will return false, but before returning false, we will actually check every single possible route to see that whether we can find a match or not. Okay, so that is how we are actually going to implement the search mechanism. Basically, the only tricky part is to take care of the dot values. Apart from that, it's pretty simple. Now let's talk about time and space complexity. So for the add function, the time complexity is actually going to be big O of n, that depending on the number of characters that are presented inside the input. And also for the space complexity, it's also going to be big O of n, depending on the size of the input. For the search mechanism, things become a little bit tricky. Over here, the time complexity is actually going to be big O of 26 times n. Why 26 times n? Because remember, for any given dot, there can be 26 child of any particular root element that we might have to iterate over, and again in the bottom we might have to keep on repeating the same process, right? So basically the maximum time and space complexity we might have to go over is going to be n times 26, but since 26 is a finite number, we can also consider this to be big O of n only. Okay, and for the space complexity, it's also going to be the same. It's going to be big O of 26 to the power of n. So for this problem, we are being asked to implement three things: word dictionary, add word, and search method. The thing is, before that, we will actually have to define a trie node. So I'm going to create a separate class to defining a trie node, where every single trie node has a different set of children, and we can easily quickly look up those children because we are actually using hash map to define them. Okay, now from our main method, first of all, we are going to create a new trie node. So now to implement our word dictionary, first of all, we are actually going to create an instance of this trie. Now for this add word method, first of all, we'll have to create a node. So we are going to create a trie node. We are going to run a for loop across the given word. If the current node, if that does not contain any children with this character, then we will have to create a new entry inside our node. And if the entry exists for this given character, we are actually going to go to the next element, and in the end we are going to define node.word to be true. So before we start our search method, we are actually going to create a helper method called search in node. That is going to take the input word and the try node as the input, and that is going to help us to iterate over the given try node. So first of all, we are going to create a for loop to iterate over this given word, and inside this given word, we are going to iterate over character by character. So I'm also going to create a new character variable. So first of all, we are going to check that if the given node does its children contains this word or not. If it does not contain, then we are going to check that whether the given character is dot or not. And if that is the dot, then we might have to iterate over all the subsequent characters of this node. Once we determine that the children does not contain this character ch, we are going to check that whether the ch is actually a dot or not. If that is dot, then we are going to run a for loop across all the children for every single character value, and then we are going to define a new try node called child, and basically we are going to call this search in node method iteratively for the next character in that particular word, because remember we are already eliminating the dot character and providing its child as the try node, and we will keep on repeating this we will keep on iterating this process, and we are going to return true. If that is not the case, and if this given ch character is not a dot, then in that case we can return false immediately. Somehow this ch is actually a child of this node. If that is the case, then we simply need to iterate over the next value inside this given node, and in the end we simply need to return that whether the node dot word is present or not. And remember, we are storing this node dot word value inside our this add word method as well. So the moment we identify a matching word, it would return true, otherwise it would return false. Now from this our search method, all we will have to do is we simply need to call the recursive search in node method that we have created, and as the input we are going to provide the value of the word, and we are also going to initialize a new try node, or we are also going to provide the try node that we initialized earlier, and that's it. Let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. Okay, seems like our solution worked as expected. It was not the fastest solution in terms of time complexity, but in terms of space complexity, it was pretty efficient. I would be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do word search to lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Amazon, Uber, Microsoft, Google, Snapchat, Facebook, Apple, Twitter, TikTok, Bloomberg, Spotify, Twitch, and Airbnb. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is the LeetCode hard problem, and basically we are given an m cross n matrix of characters. Now, and we are also given a different list of string called words. Now we need to return all the words that are present on the given board. We are also given one more thing, that each word must be constructed from the letters that are adjacent to each other. So, and we are also given the definition that what adjacent cells are. Basically, any cells that are horizontally or vertically neighboring to each other, we can consider them to be a part of the consecutive sequence series, and we can use them to create words. So let's try to understand this with an example over here. Over here, we are given a 4 cross 4 matrix, and for this matrix, we are told that these are the list of words. We need to check that whether they are present inside this given matrix or not. So if we try to just look at this example, basically we can see that this first word oath is actually present over here, where O, A, T and H, they are creating or forming this word, and if you see, they are all sequentially adjacent cells to each other. So that's why we can use them to form this words and see whether it's present or not. So in the answer, first of all, we are going to add the word oath as one of the answer. Then if we look at the answer, we can also find this word eat to be present. So E, A, T, that is present in this manner. And again, though this is on the left side, this is not the conventional way to write it, but still based on the adjacent cells we can actually form this word eat, and that's why this eat is also going to be part of the answer. So we will add eat in the answer as well. Now for this to PEA, P and drain, these two are not present inside this given matrix, so we will not include them in the answer, and this is the answer we will have to return. So basically it is one kind of a word search game or word search puzzle. So that is why the name is word search 2, and this is the little bit of advanced version. So first we will see that what is going to be like a basic, very trivial approach, and then we will try to improvise using a different set of data structures. Okay, so most basic idea we are going to have is that we will start iterating over all of the characters that are present inside this m cross n matrix, and then for every single character we are going to see that whether that matches with any of the starting words or not. If we find a potential match, then we will try to find the subsequent character and the neighbors of that particular character to see if we are able to generate any exact word or not. And the moment we do that, we will actually put it in a new variable called answer, and that is how we will be able to generate our answer. So let's try to see this in action. So first character in this case is x. So x matches with this character over here in the given set of words. So next we will have to see that whether any neighbor of x is actually y or not. Neighbor of x is actually h and a. We do not find y over here. So because we do not find y over here, this x does not lead to anywhere. So we can mark this as visited. That does not lead to any answer. Next character is h. So h matches with this first character, and then we will have to see that whether b exists as one of the neighbors of h, and b also exists as one of the neighbors of h, and then the subsequent character o also exists as one of the neighbors of b. So in this case, this hbo is actually a complete word we are able to make based on subsequent characters that are present adjacent to each other inside this given matrix. And because of that, we are going to create a new variable called the answer, and in the answer we are going to add the value hbo over here. Now we will start iterating over this a. So again, a is the starting point over here, and next character b and c, we are able to generate this pair using sequentially iterating over. And if we see over here, we can also generate this a, b, c in this fashion. Now this character is y. So again, y is not part of starting character of any other word, so we cannot do anything about this. Next character is again c, that we have already visited, so we don't need to visit this. And next character is z. Z again is not the starting point of any of these characters. So in this case, this is the answer we are going to have, and we can return this one. This solution works as expected. There are no issues with this one. But if you just see, we only have a 3 by 3 matrix, and for every single character, in the worst case scenario, we might have to iterate over every single word and check that whether it matches the starting word or not. We can maybe simplify using a hash map, but the thing is, this is still going to lead to a very bad solution. In terms of time complexity, this is going to be disaster, because for every single character, we might have to iterate over every single word that there is, and once we find a match, then we will have to iterate over all the neighbors of that particular character as well. So that leads to nowhere. So let's try to see that where we can find a better time complexity, and the solution to achieve a better time complexity is actually using a new data structure called Trie. Now I have already extensively worked on Trie, and you can find all of those solutions over here. Check out this video if you want to learn that what a Trie is and what are its applications. Now let's see that how we are going to use Trie in this case to improve our performance. Okay, so the previous example we see, basically what we are doing is we were iterating over every single character, and then we were trying to see that whether that character matches the first element or not, and sequentially we will have to check every single word that was present. And if we find a potential match, then we will have to check all the neighbors to see if the next consecutive element is present or not. And that was the major reason that why we were having a disastrous time complexity. So in order to improve that, if we can find some way to eliminate this checking procedure, that for every single character we might have to look up all the elements or all the words that are present, because imagine if there are million words present, we might have to check million times, and then that is going to be very disastrous. The idea we are going to use is that whatever the words that we are given, we are actually going to convert these into a Trie, and because we are converting them into a Trie, for any character, searching that whether it is the starting point of any word or not becomes pretty easy for us, and we can actually do it in nearly constant time. because in the trie it is very fast and efficient to find that whether any word exists or not, and if it exists, it is very easy for us to iterate over that particular word or not. So first of all, let me quickly create a trie block based on these three words. The trie block is going to look like this. So based on the words that we were previously given, we actually created a trie block. And now using this trie block, we are going to make things pretty easy for ourselves. Basically, we are going to iterate over in the same fashion for the given matrix. But this time all we will have to see is to look up in this trie that whether the current character, if that is any children of this given root node or not. And if that is the case, we will keep on iterating. So first we find this character to be E. E is not part of any children, so we can ignore that. Next one is F. F is actually part of a children. So okay, now we have found F to be part of the children. Now we will have to see that what is the next character in this trie block. So this next character is A. So we will have to see that whether any neighbors of this F is actually A or not. So we will have to check on three sides, and we find a match over here that this is A. Okay, now again next character is A. Again this neighbor is actually A. Okay, now this character is N. So again neighbor of this A is N present over here. And again the next character is G. So G is also present over here. And since we have reached to the end node inside our trie, because of that we can conclude that the whole word was actually present inside this given matrix, and we can return true in this case, and we will add it to our answer list. So inside the answer list, the first word we are going to add is FAANG, that is present inside this given matrix. So see how easy it is for us to find these things. And okay, now the next character is R. R is not children of any of these root nodes. Next one is T. T is also not a children. L is not a children. These are all visited. Now this G. G is actually a children. So now it becomes easy. Now we will have to start iterating over. Okay, so we are at this position G. Now the next element is O. The next element is O, and O is also a neighbor over here. Okay, so which is good. Now the next element is O. Again, O is a neighbor over here. So which is good. Now this next element is G. G is also a neighbor of this O, right? So we are good up until this point. Now we have to find this L. Now, if we look at this G, we do not find L to be a neighbor of this G. So because of that, we will actually have to roll back, and we cannot move forward with this path. So now we would have visited this G, and that did not lead us to anywhere. So again, we will start with our routine procedure. Okay, now this next character is O. O is not starting point of anything. T is also not starting point of anything. G is we have already used it. Now this is again G. So again G is the starting point of this one. Next character is O. O is present over here. Next character is O. O is also neighbor of this one. Next character is G. G is neighbor of this one. Next character is L. L is neighbor of this one. And next character is E. E is the first character, and because we reach to the end character over here, we can conclude that Google is also present inside this given matrix, and we will add it to our answer. So we will add one other entry called Google. Okay, and now next again this character is L. So L does not lead to any children of this root node, and F does not lead to any children of this root node. So in the answer we are going to return this FAANG and Google to be the answer, and this would be the most optimal way to solve this problem. Remember, because we used a trie block, things becomes much more faster for us, and we can immediately look up that whether any single character that leads to an answer or not. Okay, now let's do the tricky part. We will have to do the time and space complexity analysis. So for the time complexity analysis, it's actually a little bit tricky. The first thing that is a given fact is that we will have to iterate over every single character that is present inside this given m cross n matrix. So that's a given fact. Suppose that the total number of cells that are present are actually m. So now, okay, we already know that is whatever the time complexity is going to be the factor of m. Now for this particular m, imagine that for any particular character, what is the maximum work we will have to do in the worst case scenario? Well, the maximum work we will have to do in the worst case scenario is that any particular character, suppose this F matches this character that is present. Now, whenever we find a potential match, we will have to look for the next element in all three directions of that particular word. So suppose this O was a potential match, we will have to iterate over all four directions in any given case. So for any single cell, we might have to iterate over in all four directions, and for all four directions, the number of traversal that we will have to do for each one of them would depend on the next three or the next remaining three characters. Because remember, for this Google, suppose we find a match, this O to be a match. Now the moment we find this O to be a match, again we find this O to be a match. So now because we find this to be a match, we do not have to look for this particular element, we will have to look at the remaining three positions. So then we will have to, for any single character, we will have to look in the four directions, and for all the subsequent elements we will have to look in the remaining three directions, and that we will have to do depending on the length of that particular word. So for the remaining three elements we will have to iterate over to the length of that. So that's why 3 to the power of L minus 1. And why minus 1? Because for this first character we are actually looking in the worst case scenario in all four directions, and for all the subsequent length parameters, so suppose for this particular FAANG, for this F we might have to look in four directions, and for this A we only have to look in the remaining three directions because one adjacent cell is already F, so that we do not have to look at. So this is going to be the time complexity. So if I write the final time complexity, it's actually going to be big O of M into 4 times 3 to the power of L minus 1, and that is the final time complexity. This is a very difficult time complexity analysis. So yeah, it gives you an idea that why this problem is pretty popular. If we see space complexity, that is pretty simple. Space complexity depends on the total number of words that are present. So suppose we sum that up to big O of n, where m is the total number of characters that are present in the initial word list. So after doing this time and space complexity analysis, now let's move on to the coding. Before we implement our solution, we are actually going to create our class Trie node. In the class solution, we are going to define a couple of global variables. Now inside the find words method, first of all we are going to initialize our try block, and we are going to add all the words to our try block. After creating the try node, now we are going to start working on backtracking, starting with each cell in the board. So first of all, let's create the board variable, and now we are going to initialize a couple of loops to iterate over this full board matrix. So now for every single position inside this given matrix, we are going to check that whether that is actually any of the children of this root try node that we have created. And if that is the case, then we will create a helper method called backtracking, where we are going to iterate over all the adjacent cells of that particular row and column position, and also that particular entire DFS traversal for that particular branch inside our try node. After this loop ends, basically we should have populated our answer inside this answer variable that we have created, so we can simply return that. And now let's create our backtracking method. So this is going to be our recursive method. First of all, we are going to define a couple of variables. First of all, we are going to check that whether the current node is actually a word or not. If that is a word, we can immediately add it to our result. Okay, if that is not the case, we will have to start doing our traversal. So how we are going to do our traversal? Remember, whatever the current row and column is, we cannot use the same word again. So we are actually going to mark this as hash in a way for us to identify that that is the node we have already visited. Now for any given row and column, we will have to iterate over all of its neighbors. So we are going to use couple of variables to our advantage. Now with the help of row and column offset, it becomes pretty easy for us to iterate over all the neighbors of any given node. So now we are going to run a for loop, and we are going to iterate over all the neighbors of given row and column position. First we check that whether our new row and new column, if they are going out of bounds or not. If that is the case, we just simply ignore that. Otherwise, if we are at the correct neighbor, we need to check that whether that neighbor is actually subsequent character that we have already stored in our try or not. And if that is the case, we are going to call our backtracking method again. Now after our exploration ends, basically we will have to put back this hash to its original position, and that should be it. There is one more optimization we can do, and that is to incrementally remove the leaf nodes, which means that whenever we identify that the current node's children, if that is empty, then basically we can just remove that from our parent. That should be it. Let's try to run this code. We will also have to update the value of the node in the else condition. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs pretty efficiently. I will be posting this in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do top k frequent elements lead code problem, and if we see some of the companies where I want to get a job who have already asked this question, there are companies like Facebook, Amazon, Microsoft, Google, Uber, Apple, Bloomberg, Snapchat, Twitter, Tesla, Netflix, ByteDance, LinkedIn, eBay and TikTok. So that's why I'm paying my utmost attention. I hope you also enjoy the video. This is a LeetCode medium problem and also very well like problem on LeetCode. Basically, we are given an integer array called nums and we are also given a separate integer called k. Now we need to return the k most frequent occurring elements from this nums array, and we are also told that we can return the answer in any order. So first let's try to understand this problem with this example. I have actually drawn it much bigger over here. So this is the array nums that we are given, and we are given k is equal to 2, which means we need to return top 2 elements that are present inside this given nums array, right? So if we see in this case, well, over here this 1 is actually present 3 times, this 2 is actually present 2 times, this 3 is actually present 1 time. Now if we see, we are given that k is equal to 2, which means we need to return top 2 elements, and clearly we can see that the top 2 elements in this case is this 1 and 2. So we can return the answer to be 1 and 2, or we can also return 2 and 1, because remember we are told that we can return answer in any case, and this is the answer we need to return. So let's try to see that what is going to be the approach to solve this problem. Now let me make one clarification. There are actually two different approaches to solve this problem. One approach, or the first approach I'm going to show you in this video, is actually sufficient for your interview. Any interview would be more than satisfied with that approach. But the thing is, the second approach I have is actually the golden key approach for any like top k element problems, right? Any heap problems, you can use the second approach, and I'm actually planning to make a separate video on that, depending on whether you want to learn it or not. So let me know in the comments that whether you want to learn this second approach. If you do, I'll make a separate video. We are actually going to use the combination of a hash map and a heap in order to achieve the top k elements. So I have created a custom example over here, and I have given the value of k is equal to 3. Now remember, whenever we need to define that, we need to return top k elements or top 3 elements in this case. How can we define that? Well, we first of all need to iterate over this given entire array. We need to find that how many times any single character is occurring, and depending on that answer, we will have to iterate over that whatever the list we create, where we have the number of occurrences for each character, and then we can conclude this answer. So one thing is clear, that we need some way to store the information that how many times any particular individual character occurs. For that, we are actually going to use the hash map. In the hash map, as the key, we are going to denote the distinct value of this given array, and as its value, we are going to note the occurrence of that particular character. So first, let me quickly create a hash map for this given input, which contains the distinct values and their occurrences. So based on this given input, this is the hash map we can create. Now we need to select k is equal to 3, which means we need to provide top 3 elements. Now one approach to find the top 3 elements is that all the distinct values we have in this hash map, if we just simply create a sorted array, and in the sorted array we sort the arrays based on the descending values, which means the most occurring value to be first, and then we put down all the remaining values, we can actually generate a sorted array that looks like this. And now for this particular sorted array, we can simply return the top 3 elements. So we can return the answer to be like 4, 3 and 5 easily. And this is the solution that would give us the correct answer. But thing is, you would quickly ask me that why did I mention priority queue over here? Because over here, what I'm doing is I'm taking this hash map and I'm actually just sorting it, and we are able to generate the array. Well, first of all, in order to understand that, first of all, let's understand the time complexity of this approach. The time complexity of this approach is, first we need to iterate over the given entire input. For that, it takes big O of n time to generate this hash map. After generating this hash map, we will have to create the sorted array that takes n log n time to generate that answer. and this n log n is going to be the ultimate time complexity. So the thing is, this you would say, hey, n log n sounds reasonable. But the thing is, from n log n, suppose we have like 1 million distinct characters or 1 million characters, and we are given k is equal to 3, which means that we would have done like 1 million times log 1 million work. Meanwhile, the value of k in practice is supposed to be much smaller than whatever the input size is going to be. So the other approach is that if we create a priority queue, and remember, the concept of a priority queue is that inside the priority queue, basically we add the values and we remove the values, just like any queues. But the thing is, the values that we are entering, they have some meaning behind them, and depending on their valuation, we actually store the value. So whenever over here, suppose this is the priority queue and I have provided different weight to those elements. If I want to create, or if I want to enter an element that is an higher weight, then I would get rid of only the lower weight elements and add those over here. I would not be repeating everything. So based on that concept, what I'm suggesting is that rather than sorting this array, we get rid of it. Okay, so let me clean this up a bit. And over here, from this actual hash map that we have created, we actually create a priority queue. And this priority queue is going to be of whatever the size we are given of the k value. Okay, so k in this case is 3, so we are going to only have 3 values in our priority queue. Now for our priority queue, first of all, we are going to check that, okay, we only enter the values based on the number of occurrences they have, and we only keep the higher number of occurrences. So first we add the value number 1 over here because we don't have anything. Now we add value number 2 over here because we still have room and 2 has 2 occurrences. Then we add value number 3 because 3 has 3 occurrences. And remember, we are using the occurrence to add the value, not the actual distinct value, right? This is the key part. Okay, now we have this value number 4. 4 actually has 4 occurrences, right? And so far, if you remember, this 1 had 1 recurrence, this 2 had 2, and this 3 had 3 occurrences. Now we have a value that is 4 that has actually 4 occurrences, which means it is greater occurrences. So we are able to insert that value inside our priority queue. And in that case, we are actually going to get rid of the smallest value. So smallest value in this case was 1. Now we are not going to add 4 over here, but we are also going to maintain the ascending order in terms of the values that we are being added. So we'll just shift these values. Okay, so 2 will come over here, 3 will come over here, and 4 will come over here, and then we will have those subsequent values. Now after adding this, we still have value number 5 that we need to add. So 5 occurs 3 times. So 5 occurs 3 times. Currently we have 2 occurring 2 times, 3 occurring 3 times, and 4 occurring 4 times. Now 5 occurs 3 times, so 5 is able to enter over here because it occurs more times than this 2, and we can actually put 5 over here because it is also occurring 3 times, and this 3 is also occurring 3 times. So we are good up until this point. After that, all we will have to do is just convert this result into an array. So for that particular array, we are actually going to store the results. And remember, we can return result in any manner. So we can return like 5, 3, 4, or we can also return like 3, 4, 5, or whatever result we want to return, we can return. And this is going to be the solution. If we see time complexity in this case, the time complexity is actually going to be a bigger improvement than our sorted array approach. Why? Because okay, over here this takes big O of n time to generate this hash map. That process remains same. But now from generating this hash map to this priority queue, it takes n log k times because we are only maintaining k elements. This is the important part, and this is what your interviewer is going to focus on. So in this case, the time complexity is actually going to be big O of n log k, which is good. And in terms of space complexity, well, you must have guessed it correctly. It's big O of n because we are using a couple of additional data structures. We are using a hash map, and we are also using a priority queue. And this is a very good time and space complexity. And that is basically the ideal approach. Now let's move on to the coding. First of all, we are going to take care of an edge case that if the given k is equal to whatever the length of this nums is, we can simply return nums. That is not the case. We are going to initialize our hash map. Now we are going to iterate over all the elements that are present inside this given nums. So we are going to run a for loop, and after the for loop ends, we are basically going to populate the values inside our count hash map that we have just created. Now we are going to initialize our priority queue. And inside our priority queue, we are going to assign the method of insertion. So we are inserting based on the number of occurrences based on this count hash map. So let's put the condition for that. So now everything is set up. Now all we have to do is just iterate over all the keys that are present inside this count hash map that we have created, and for every single key basically we are going to add that value to our heap priority queue, and whenever the priority queue gets full to the size of this k, we are basically going to pop the element, and the element that will get popped is going to be the least occurring element. So we are only keeping higher occurring elements inside our heap. And now we check that if the heap size becomes greater than k, we remove the value from heap. That's it. So now all we have to do is just simply initialize a new array variable called answer, and we are going to populate this answer array. So we will run a for loop for k times, and we will keep on pulling the values from our heap. Then we can simply return the answer, and let's try to run the code. Okay, seems like our solution is working as expected. Let's submit this code, and our code runs pretty efficiently, and I will be posting this solution in the comments so you can check it out from there. Thank you. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. So the lead code problem we are going to solve today is called find medium from a data stream. It is a very nice problem. And if we see some of the popular companies where I want to get a job who have already asked this question, there are companies like Amazon, Apple, Uber, Adobe, Bloomberg, Google, Spotify, Microsoft, Facebook, Nvidia, ByteDance, LinkedIn, and bunch of more. So that's why I'm paying my utmost attention. I hope you also enjoy the video. So this is a LeetCode hard problem and also a very well-liked problem. Basically, we need to find the median from an incoming data stream. Now, in this problem, basically we are being asked to implement the median finder class. Now in this median finder class, we need to implement these three methods, where the first method is the median finder method by itself. Second one is a void add number, which means that if this method is being called, it will add an integer called nums from the data stream to our data structure. And third one is the find the median, that we need to basically find the median. Now let's come back to the problem statement. First, we are given the definition that what a median is. Median is the middle value in an ordered integer list. Now this is the tricky part. We are being asked to find the median from an ordered integer list, which means that the input, whatever the input comes, let's say the input comes like 11, 3, 5, something like that, we still need to find the median as if the input was 3, 5 and 11. So this is the tricky part. Like most of the people would not realize that the wording ordered integer is there, and then they will get confused. So now we have get that sorted. Now we need to see that what is the definition of the median is. Basically median is the middle value, and if the size of list is even, then which means there is no middle value. In that case, we need to find the median as the average of two middle values. And we are given some examples, but we are going to see this in much broader examples. So first let's try to understand this with some existing example. Suppose we are given a stream that looks like this: 1, 2, 5, 11, 15, 16, something like this. What would be the median in this case? Well, if we go based on the definition currently, well, this stream is actually an even stream, which means that there is no exactly one middle value. We are currently seeing two middle values in this case. And also notice that for this whole thing, I actually set it in ordered motion already. So we are going step by step. So first, this is an ordered list that is an even list, and it has two middle values. So in this case, the median is going to be the average of these two values. So which turns out to be 5 plus 11, 16 divided by 2. So the answer is going to be 8 in this case. So second, again, let's suppose that once again the list is ordered list. So 1, 2, 5, 8 and 9. In this case, we are dealing with odd numbers. Now for these odd numbers, the middle value is quite obviously clear, and that is going to be value number 5. And again, the ordered property is still maintained in this example as well. So in this case, the answer is going to be simply value number 5. Now let's take one notch a little bit more complicated. What would be the median in this case? Since this is odd number, we know that we need to find the middle value, but in this case, this is not in order. So first we will have to put this in order. So that is going to be 1, 3, 5, 8 and 15, and in this case, now since it is easy to calculate the middle value, it is going to be 5. So this would be another scenario. Now with these examples, you at least got one broader idea that how to deal with the median finder class, like when we need where we need to first of all create a method to find the median. Second, we need to create a method to add the median, and third, we need an object of this median finder class. So basically we need to focus on these two items the most. Now the most important part in this one is first we will have to see that what would be the actual problem is going to look like. So actual problem is going to look something like this, where there can be multiple options. So first, let's say that it selects, and the option is that you need to find the median. But currently, if we see our list or our input data stream, let's just mark this as input data stream. Currently in our input data stream, there are no values, which means if we call out this find median function, basically it is going to return 0. So this time, or return null value, actually not 0. So let's say that this returns the value null. Okay. Now again, we are calling add number method. So if we call add number method, and we say that okay, add number 5. So in this case, currently in our data stream, there is only one value, that is 5. Now we call add number method again, and we add value number 6. So now our data stream has value number 6. Once again, we call the add number method, and we add value number 2. So in this case, currently our data stream has value number 2. And then if we call the find median method, which means we will have to find the median. Now in this case, ideally this find median method should give us the answer according to all of these examples we saw. So basically, first for this data stream, it's 5, 6, 2. So we are going to put it in the ordered list, that is going to be 2, 5 and 6. And the answer in this case needs to be returned as value number 5. So 5 is what we would return over here for the find median. Now again, there can be bunch of more operations to be performed same way. So let's say that again we add a number, and this time we add the number 11. So our data stream is going to have value number 11. Now if we want to find the median, then again there would be an additional bit of changes. So it would be like, this would be our sorted data stream, and the median is going to be 5.5, and this is what we will return. So basically it will keep on changing. Now our job is to do this in the most efficient manner. Okay. Now in this array list, what we are going to do is from whenever our main method, whenever we see add number method being called, we are going to simply push one number down this data structure. So let's say we got numbers coming in as 6, 8, 2, 1, 5. Okay, this is the sequence of numbers that came in, and then we encountered the find median method. Now again, since this is a brute force approach, we are going to take this step by step in the very preliminary fashion. So first thing that we would do is that we need to find the median of this array list, but currently this array list is not sorted. So because this is not sorted, we are going to simply sort this. Now sorting an array or array list, actually there are a bunch of different ways, but typically this can be achieved in n log n time if we use something like quick sort or merge sort, but we are not even going to bother implementing those quick sort or merge sort. What we are simply going to do is call collection.sort method. So if we call collections.sort method in any programming language, basically it sorts the given array for us in n log n time. So after that, we are going to have a sorted array, and the sorted array is going to look something like this. It's going to be 1, 2, 5, 6, 8, and this sorted portion took us n log n time. Okay, now for this 1, 2, now finding the median, it becomes quite simple, because we know that for array, fetching takes big O of 1 time, and also putting the value takes big O of 1 time. We already know the size of the array, so in this case the array size is going to be 5. So because array size is 5, we know this is odd number, and since this is odd number, we need to find the middle value. So middle value has to be located at position number 3, or if we see in the array, it has to be sorted array, and the index value has to be 2. So because this is 0, 1 and 2, and whatever the value is located over here, we are going to simply return that, and that is going to be our answer. So let's break down how does our brute force solution compare to everything we have done so far. So it actually seems to do justification, because if we see in this case, the finding median is being done through two processes. First process is that we are sorting the given input, and second process is that we are actually finding the median by doing the average depending on the odd or even value. Now this case is a constant operation, so this can be done in big O of one time, but the sorting is actually a little bit tricky, and this takes n log n time. So overall the finding median is going to be done in n log n time, and adding number is actually quite quick, so that is being done in big O of one time. So if we see the total time complexity in this case, the total time complexity for this brute force approach can be considered as n log n, and that is not so bad. But we want to do it in much faster manner. So we will have to strive for something that where we can store or where we can save in terms of time complexity. Well, optimal solution is actually comprised of couple of different components, and what those components are, first we will have to find the room that where we can actually save in terms of time complexity. So we are currently taking care of finding median by using first sorting the given input, and second one is finding the actual median. Now this portion is quite easy, so we can ignore this one. This portion is the trickiest. And why this is the trickiest? Because we actually have an incoming data stream that is generating bunch of different random numbers, and we are taking these random numbers and creating them in a beautiful sorted list, and this sorted list is then being used to find the median depending on the middle values. Now since we already know that the input that is coming in at one at a time, so if the input is already coming at one at a time, why can't we design a structure that automatically sorts itself, and we are not going to need to care about the sorting property? So we already took care of one portion of it. And what would be that automated sorting mechanism data structure is? Well, you already know it. It is actually called a heap or a priority queue, where depending on the how you configure it or how you set up, you can actually configure it to have in either in increasing order or decreasing order. So no matter the sequence of numbers that are coming in at random, eventually this is always going to be in the sorted manner. So if it is always going to be in a sorted manner, then it becomes very easy for us to basically find the median, because we already know that how to find the median from a sorted property. Now there are a couple of tricky parts over here, and first let's break those down. Currently we have already decided that we are going to use heap. Now what are the trade-offs with heap? Well, the first trade-off is that if we want to insert any data, basically the insertion takes big O of log n time, right? So that is adjustable because it is maintaining the sorting property. So how it does it is that let's say that you have this initial heap that is being created, and currently this heap is empty. Now you have this one incoming value 15 coming in. So 15 comes in. So it currently, because there are no values, it puts 15 as it is. Now let's say that there is one more value coming in, and that is value number 16. So now for this value number 16, heap is not just going to append it anywhere in the sequence. It is going to see that, okay, let's assume that this is actually a min heap, which means that the topmost value has to be the minimum value, and all the other values would be greater than that. So in our min heap, basically we need to make sure that the first value remains the smallest and everything is sorted in increasing order. So in this case, because of this is a min heap, it is going to put 16 over here, and 16 is going to store over here. Now suppose we have another value coming in, and that is value number 5. Now this value number 5 is actually lesser than 16 and 15 both. So in this case, it is actually going to find a proper bucket or a proper place for 5 to be stored, and that it is going to do using the binary search. And we all know that binary search takes log n time, so that is why first it is going to do the binary search to calculate that where to put this 5. It calculates that okay, currently the 5 is the lowest or the minimum value, so that is why it is going to put 5 at the beginning, and it is going to take care of all the other values. So basically our heap is going to look like 5, 15 and 16. And because of this property, there is this log n time penalty that we have to pay. But this log n is actually much better than n log n because we are only doing it once. So that is the trade-off. Now I hope I was able to explain you that how does a heap work. Once we have that sorted, now let's see that will this make any improvement to our problem? Well, of course, it is going to make significant improvements to our problem. Currently, let's assume we are using a min heap. Again, using the same example, let's say that we have our data stream. Now in our data stream, assume that we have all the values coming in at random. So the random values that are coming in at the moment are going to be, let's say 1, 15, 3, 8, 9, 11, 13. Okay, these are the random values came in, but we have a heap and we have a min heap, which means it is going to take care of all the values in the sorted manner. So sorted manner is going to be, now in this case, since we have 7 digits or 7 values stored inside our heap, which means that this is odd number. So because this is odd number, we need to find the middle value. Now this is the tricky part. We know that with array, it was actually easy to fetch any value from the middle because we were able to do it in big O of 1 time constant time. But that is not the case with the heap. So fetching the middle value, it is actually going to take big O of n divided by 2 time because we are doing it sequentially one by one to reach to the middle point. So in that case, since it is taking that much time, can we do some improvements to actually find the median quicker? So now we know that what is the issue with the typical ordered list. Basically inside the ordered list, despite having all the values properly set up using the heap, it will still take us time to reach to the middle pointer, and we want to basically make this process much faster. So how do we do that? Well, one simple conclusion is that breaking this heap into 2 portions. And how do we break this heap into 2 portions is that first we are going to have a max heap. Now what does a max heap means? Max heap is going to be this portion of the given existing list. And if you notice, one property in this portion is that every single element at the end of this heap is always going to be the maximum value compared to all of its peers. And this is the only value we care. Same way, we would have another partition being made inside our heap, and that is going to be this remaining portion. Now inside this remaining portion, we can actually call this min heap. And why we are calling it min heap? Because the only value that is of concern to us is this middle pointer. We don't care about all of these values. We only care about this value because this is going to be the minimum value compared to all of its peers. And if, for an example, if the current heap size, or if let's say that max heap and min heap, we will try to make them exact equal in terms of the number of elements that are currently present. So let's say that in our current data stream, if the values are even, basically in that case, max heap and min heap, they are going to have even values. And in our data stream, if the values are odd, then in our case, our max heap is going to have one more value compared to our min heap, and that's it. So if the values are even, or if min heap and max heap are same in the size, then the median value is going to be the combination of, or the average of, this max and min heap. And if it is odd, basically we simply need to return this max heap value or the max element. Confused? Don't be. Let me show it to you with an example. Suppose this is our current data stream. What would be the ordered list? First, let's just try to understand. So median in this case, again, that is quite easy to find. the median is going to be this value number 3, that is the middle value. And why we came up with this value number 3? Because once again, this is the total number of elements are in the odd number, so that is why it is easy to find the median. Now let's see that how would my approach work. So first let me quickly create a max heap and a min heap. So I'm just first giving you the end result, that how they are going to look like, and then we will go step by step on how to implement that. Okay, so end result is going to be that this max heap is going to have all the values that are greater than the very first element inside the max heap. So max heap is going to look something like this: 3, 2 and 1. Actually it's going to be 1, 2, 3, but I'm giving you more general idea so that visually it is more interesting that the very first element is the element that we are looking for. So in this case, this is going to be that. And if we see it with the original list, basically we are taking care of these first 3 values. Same goes with the min heap. What are going to be the values? So the values are going to be simply 4 and 5. Why? Because the very first element is going to be the minimum value compared to all the other values. Now again, going back to our equation of the values being equal or one value being higher than the other. So in this case, currently if we see the number of values in our, okay, this MH is not the best abbreviation, in our max heap. Okay, max heap and min heap. So currently in our max heap the number of elements are 3, in our min heap the number of elements are 2. Because max heap has one greater element, the whatever the value of max heap is, or the whatever the value of the very first character in the max heap is going to be our median. And in this case, if we were to ask find the median, we can simply return the answer as 3. Now let's see that how step by step we are going to maintain this property. So first we have our max heap, and then we also have our min heap. Now the property inside the max heap is that the very first value has to be the biggest value compared to all the other values, and the min heap is that the very first value is going to be the smallest value. And also there are one more property, that every single value inside the max heap is always going to be less than or equal to the min heap, nothing more than that. So first we are going to enter the value inside the max heap, and that is this very first value 52. So first we add 52 over here. Currently min heap does not have anything, we took care of this value. Now the second value is value number 2. First we are going to check the size difference between max heap and min heap. And what the size difference is going to tell us is that whether the value should be added to max heap or min heap. So if we were to add this value number 2 to max heap, then the size difference between max heap and min heap is going to be value 2. So because this is greater than 1, we cannot have them, which means we will have to push one value to the min heap. But the question is which value, and that is the interesting part. So we know the property that every single value in the min heap has to be greater than max heap because of this one. So if we enter value number 2 in the min heap, will it make sense? No, absolutely not. Which means first we will have to push the maximum value that is currently present inside our max heap to the min heap. So the first we are going to have value number 52 being pushed over here, and then we are going to have this value number 2 being pushed to our max heap. I hope this makes sense. If not, try to rewatch the video for this portion and you will understand what I exactly said. So now we already took care of value number 2 as well. And also remember, because we have both the values at the same time, if we want to find the median, it becomes quite easy. We can do it in just constant time at any given moment. Because let's say I tell you that after these two values, there is a find median command. You can do it quite easily. You can just say that, okay, 52 plus 2, 54 divided by 2, I think it's going to be 27, and 27 is the answer. You can find it quite obviously. So that is why this approach is very fast. Now again, going back to our example, now this value number 3 we need to push in. Currently both of the min heap and max heap, the sizes are same, which means the value has to be entered into the max heap, because max heap can have one more value than the min heap. So 3 we know we have to push it into the max heap. Now what is the property of the max heap? That very first element in the max heap has to be the greatest element or the biggest element compared to all the other values. So in this case, because 2 is the small element, we are going to adjust our max heap. So first element is going to be 3 and second element is going to be 2. Now we took care of this value number 3 as well. Now we have this value number 5 to take care of. Again, 5 has to be added to the min heap. So if should we add 5 directly to the min heap, or should we add it to the max heap? We are going to check the very first or the biggest element inside the max heap. The biggest element of the max heap is lesser than the value of that we are trying to enter, which means 5 can easily enter our min heap. So since we are entering 5 into the min heap, we also want to maintain a property inside the min heap that the very first element inside the min heap is always going to be smaller, which means 52 we will have to move on the side and value number 5 we will have to put together, because up until this point, even if you see that what are the elements, so the original elements were 52, 2, 3 and 5. If you just want to put them in a single ordered list, the value is going to look like 2, 3, 5 and 52. And we are only concerned with these two values 3 and 5, and which we are able to make sure or use using this min heap and max heap. So that's why we are going to get rid of all of this. This was just for explanation purposes, but you get the idea that what we are trying to do. Now once again we have the value number 11 that we are trying to enter. So for this value number 11, it has to go to the max heap. What is the property of the max heap? That the very first value has to be the biggest value. So currently the value is 3. So because 3 is smaller, so 11 will go over here in the middle in the very first value. So we are going to get rid of these two, and the value is going to be 11, 3 and 2. And currently what is going to be the median value? The median value is going to be value number 11, the biggest value of our max heap. But question is, can 11 stay there? Of course not. Why not? Because every single element inside the max heap has to be smaller than every single element in the min heap. And currently we have value number 5 that is actually smaller, that is residing in the min heap. So that should not happen. So once again we will have to first before adding 11 over here, first we will have to add value number 5 over here. And then since the size differences between max heap and min heap is greater than 1, so 11 would rather going there, it would enter over here. And in this case the values are going to look like that 11 and 52. Okay, now we have the very final element 7 that we need to enter. So where should 7 go? Again this already has one element greater, so we know for sure that 7 has to go to min heap. But 7 we are going to compare 7 with the very first element. So 7 is greater than 5, which means 7 can easily go into our min heap. And since 7 is the smallest element, we will have to make adjustments before we enter 7 over here. So the values are going to be 7, 11 and 52. So in the end, we are going to have our two min heap and max heap. So max heap is going to look like 5, 3 and 2. And the min heap is going to look like 7, 11 and 52. And now if we are being asked to calculate the median, it is quite obvious. We are just going to do addition of 7 plus 5. So our value is going to be 12 divided by 2. And the answer is going to be 6. And this is the beauty of heap. And this is why this problem is a hard problem, but also very popular problem. Let's calculate the time and space complexity. So again, for the time complexity, first we need to find that for the max heap and min heap. So insertion takes log n time. And essentially we are going to be inserting values in the max heap, min heap, sometimes from max heap to min heap and sometimes from min heap to max heap. But in either case, we are going to be achieving that in log n time. So essentially we are doing log n 4 times, and then for the one time we also have to enter the value from the data stream to one of the heap. So essentially we are actually doing the log n operation 5 times. So if you want to be very specific, you can mention 5 log n to be the exact time complexity. And plus, in order to find the median, this operation is actually constant. So big O, that is being done in big O of one time. So this is a very good time complexity. Now let's calculate the space complexity. So space complexity is basically going to be big O of n, where n is the number of values that are currently present inside the incoming data stream. So here is the coding solution. First of all, we are creating our class called median finder, where we have our two priority set. First one is a priority queue named low, that is our max heap, and second one is our min heap. Now we need to create a method to add number. Basically, to add number, we are first of all adding it to the max heap. Then we are balancing the both the heaps, and then we are checking that if they both are maintaining the proper sizes or not. If not, we would pop the element and move it to the other heap. And in the end, it becomes quite easy to find the median, and that is essentially you just check the size. If the sizes are equal, then you do the average of both the lowest and the highest value and divide it by 2. Otherwise, you take the value from the max heap and return it as the answer. So let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code. And our code runs decently efficiently, and I would be posting this solution in my GitHub. So this is my GitHub repository, and you can find bunch of different solutions over here, and it is going to be quite useful. Good luck. Hello friends. So I'm gonna be very honest with you. The question we are going to do today is related to bit manipulation and binary manipulation. Basically, these are not the most popular technical interview questions, and if you want, you can skip this video entirely, even during your technical interview preparation. I personally created these questions because I wanted to learn them, and maybe for anyone like me who wants to know that what these questions mean, because there is always going to be some benefit on learning a new skill. But apart from that, to be very honest, you can also skip this one. So it's up to you. I just put it out there, and let me know if you find it useful. But anyways, let's see the questions. Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to work upon a lead code medium problem, sum of two integers. So let's understand the problem statement. Basically, we are given two elements a and b, and we need to return the sum of two integers without using the plus or minus operator. And the problem statement is really simple. Basically, we are given two values a and b, and we need to return the sum of a plus b equals to in this case 3, but without using the plus operator. So let's see how can we do that. We are going to use 2-bit manipulation operators. First one is something called XOR or exclusive OR, and second one is AND. So let me show you what each of them does and what does it mean. So we will consider a table like this, where we are given the values of A and B and the value of A XOR B. Now these are binary elements, so we can the only possible values we can have for A and B is 0 and 1, and we can have four possibilities. Either both are 0 0, 0 1, 1 0, or 1 1. And the answer for A XOR B would be 0 0 is 0, 0 1 would become 1, 1 0 would also become 1, and if both are 1, we would again consider it as 0. So this is just something that we keep in our mind, and we will use it further down in our equation. Now let's see what would be the table for A and B. Now as the name suggests, A and B, we only set the value as 1 if both entries are 1. Otherwise, if there is any single 0 present, we get the answer of A and B as 0. And now let's see how can we use these two operators to find the sum of any two values for our given problem. So suppose we are given two values like this, A equals to 5 and B equals to 3. So the sum of A plus B, as we know, is 8. And let's see how these values are represented in binary. So A would be represented as 1 0 1, and B would be represented as 0 1 1, because in binary operator the value of any element is actually done as 2 of 0, 2 of 1, 2 of 2. So this becomes 4 and this becomes 1. So 4 plus 1 equals to 5. And same over here, this is 2 and this is 1. So 2 plus 1 equals to 3. Okay, now let's try to do a summation of these two values. So 1 plus 1, we cannot do 2 over here because this is a binary representation. So we will do as 0 and we would have 1 as carry that we carry on towards the left value, and again we get 1 plus 1. So again the value becomes 0 and we have a carry that we need to consider on the left side. If we take the carry again, we get the value 0 and we will have a carry over here, and we don't have any value over here, so we can just consider this as 0 0. So with the carry the value becomes 1, and if we do the if we find the binary value for this one, this is actually 2 of 0, 2 of 1, 2 of 2 and 2 of the power 3. So the value 2 of the power 3 is actually 8, and which is our answer. So if we do the simple addition of binary values, we can also get the answer as 8. But the problem over here is that we should not be using the plus operator, so we cannot just simply add these two values. So the longer route we can take is we can try to do A X or B first, and then we would do A and B, and we would move the values to one point left. This is simply what we are going to do for the given elements until the point where we find that the values of A and B uh, as 0. So this is the broader idea of our algorithm, and let's see what I mean by that. So the value of current A is 1 0 1 and B is 0 1 1. So let's try to do A XOR B. This is the symbol for XOR in computer language. So we will simply use this one, and let's see what the value becomes. So we know that 1 1 is 0, 0 1 is 1, and 1 0 is also 1. Now we need to do the operation of A and B. We are doing this operation to find the carry value with A and B values. And because we are finding the carry values, we know that whenever we have a carry at any location, we need to move it one step on the left side. So we will again use the same logic that we will use A and B to find the carry value, and we would move it one step on the left side. So let's see what the values would be for A and B. So basically we have 1 1 over here, so that value would become 1. And notice that we are writing 1 over here and not over here because we are shifting the element on one step towards the left side. So we have 1 1 as 1. Next values we have is 1 0, sorry 0 1, and we set it up as 0, and again we have 1 0, so again we set it up as 0, and because we don't have any value over here, we shifted one value on the left. We can consider the value as 0 over here. Now we have calculated the results for A XOR B and A and B, and we have moved them towards the one step on the left. In our algorithm, this would become our new A and this would become our new B, and we would have a loop that until we get a value of B that is not 0, we would continue with this operation, and let's see where we will get. So now the values for A and B would be A would become 1 1 0 and B would become 0 0 1 0. And now let's repeat the operations again. So first we will do A XOR B, which gives us 0. 1 1 becomes 0, and we will have a carry, but we will consider it later. 1 0 becomes 1 and 0 becomes 0. Now let's do A and B and shift it to 1 bit on the left side. And because we have to move it 1 bit on the left side, we will start it over here. So 0, 0 becomes 0, 1 1 becomes 1, 1 0 becomes 0, and 0 becomes 0. And because we don't have any value on the rightmost part, we will consider it as 0. So again, we will assign the values as A and as B. And we notice that B is still not 0. So we will continue with our operations and we will continue with our loop. So again, let's repeat the same operation. So A mod B becomes 0, 0, again 0, again 0 and 0. So all zeros we are getting as A XOR B. And now A and B shifted one element on the left side becomes, we start one element on the one element from the rightmost element. So 0, again 0 for these two, 1 1 becomes 1, 0 0 again becomes 0, and we have one blank element on the rightmost bit, so we can consider it as 0. This becomes our new A and this becomes our new B. We notice that B is still not 0, so let's repeat the operation. And now we are going to do A XOR B equals to 0 0 0 1 0, and A and B shifted one bit on the left side. So notice that on this A value, we don't have any ones, which means that under no circumstances we can have this A and B where we get one answer, because A is always 0. So same thing applies over here, and basically this value would become all zeros, 0 0 0 0 0. And now again we assign our values. So this becomes A and this becomes B. And notice that in this scenario, B is completely 0. So we can break out of the loop. And when we break out of the loop, we can simply return the value of A. So the value of A we have found in this scenario is 0 1 0 0 0. And this is a binary number. If we were to convert it to decimal value, we can understand this as 2 of 0, 2 of 1, 2 of 2, 2 of 3, 2 raised to 3, and 2 raised to 4. So all of these values are 0, so we don't consider them. This one is 2 cube, which is 8. So we can return A as 8, and this would be our final answer. And if we see the original two values in our request, basically we had the two integers A equals to 5 and 3, and we get our answer perfectly defined over here, and we reach to this answer without using the plus operator. So this would be our solution. And now let's calculate the time complexity for the given problem. So basically, if we see the given input over here, we have a constraint that all the values are between -1000 and +1000, which means that essentially we can calculate the time in a constant time complexity, big O of 1. We don't need to calculate anything additionally, because overall the input is quite small and we can simply do it constantly. And also the space complexity would be big O of 1, because we are not using any additional space. We are just using a couple of variables to store just few values. So this is a really ideal approach. And I know that a lot of people don't like to have bit manipulation, and they simply ignore it or they hate it. And most of the times companies don't tend to ask this kind of questions, but we are preparing for FAANG. We are not preparing for some random company. And if you want a dream job, why would you compromise? So I would just suggest that go over it. It might take you like 2-3 hours to go through all the bit manipulation questions and understand the concepts. But once you are done with that, you will have an extra edge in the interview. So I would highly recommend not to skip anything and not to put anything on the chance. I will, and now let's move on to the coding and we are going to implement the solution.
So if our intention is to just submit it for the sake of submitting it and have it accepted by LeetCode, we can simply write one line of code. We can simply return a plus b, and apparently it works. Yeah, but this is not what we want. So we would be writing the complete solution that we would use in an actual interview. So first of all, we will create a while loop to see if the value of carry is actually 0 or not, and we are going to store the value of carry in the b element. So while b is not equal to 0, now we will create a variable to store the value of a XOR b. Let's name it temp, and now we will calculate carry as well. We will do a and b and shift it to one place left, shift it to one bit on the left side. And now we simply store the value of temp in a, so a becomes our temp, and as mentioned earlier, we will store the carry in b. And yeah, that's pretty much it. Once this loop runs, our solution should be stored in a, so let's return a. Let's try to run our code. Looks like our solution is working. Let's try submitting it. And yeah, our solution works pretty neatly. It's apparently 100% faster than all other solutions, but actually this is not true. All other solutions are also 100% faster because the runtime is in constant time. So hope you liked the video, and let me know in the comments if you want me to update anything in the video. Our aim is to clear FAANG interviews. I'm making these videos so I can practice for myself, and also I can spread the knowledge I have gained to other like-minded people. And yeah, see you soon.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to work upon a lead code easy problem, number of one bits. And this is a bit manipulation problem. I know a lot of people don't like it, but it's really simple to understand. So the problem statement is pretty simple. We just need to check that in any given integer, if we represent it in binary form, how many times the one value is being repeated. So in this given example, we are given a number like this, n is equal to 1011, which is the binary representation of the decimal value 11. That we need to check that how many times this one is repeated in the given integer, and clearly over here we can see that the one is being repeated 3 times, and which is the answer of this problem. And notice that the number is represented quite long because it is showing that all the 32 bits of any integer, and all the input types would be of 32 bit, and we need to find that how many times one exists. So the first approach we are going to take is quite simple, and we are going to use a binary operator AND. Now let me show the table for AND binary operator for any given two values. We can have four possible combinations. And A and B means if the value of A and B both are 1, in only that scenario we are going to consider the value of A and B as 1. Otherwise, if there exists any single 0 or both values are 0, we would just simply put the values as 0. Using this logic, we can solve this problem really fast. And the most basic approach is we would simply run a loop 32 times, and every single time we are going to compare each element with 1 and see that if we AND the value that exists at any given location with our value 1, and if the answer is 1, we do counter plus, and after running the loop for 32 all the 32 bits, we would just simply return the value of our counter. Let me show you by an example what I'm trying to say. Suppose the input we have is 13. If we represent it in binary, it would look like, and we would have 28 zeros and the prefix. Now we will create a value, just any random variable, and we would give it as value number 1, and we will run a loop from 0 to 32, and inside the loop for every single value we would compare that whether this 1, we would compare it with the rightmost element in our given input array, and we would do an AND operation between these two values, and we would have a counter that we initially set it up as 0, and whenever we find that the answer of these two AND variables is actually 1, we would simply increase the counter. So for the for the rightmost position, we would increase the value of our counter, so counter would become 1, and after we are done with this condition, we would simply do a left shift for this random operator in the for the given input. So now 1 would be shifted one position to the left, and we would again do the same operation. So this time we will do an AND operation between this 0 and 1, and the value of AND operation would be 0. So we won't update the counter, and again we would do a left shift for this one element. And again we would do an AND operation. The value we would get is 1, which means we need to update our counter. So counter becomes 2, and again we would shift our element. We do an AND operation again the value still remains 1, so we update our counter again, and we update the counter to 3, and then we would subsequently update the value of this random character to 1 bit to the left. And now notice that all the remaining bits are 0, so the AND operation will always equal to 0, so we won't update the count, and at the end of the loop we can simply return whatever value of count we found as our answer. Now this approach works perfectly fine, and this approach actually runs in big O of one time, because we only have to run the loop 32 times, which is a minimal amount of work that we have to do, and the answer would always be constant. So this is in itself pretty neat solution, but let's see if we can go one step further and we can reduce this loop counter time to less than 32. In order for us to understand the optimal solution, let's first take an example. So, say we are given a value n equals to 36. Now let's represent this value in binary, because we know that binary works like 2 to the power 5. And if we do the summation of these values in decimal terms, uh, this would become 4 and this would become 32. So 32 plus 4 becomes 36. Now, the intuition behind this solution is that if we take one value lesser than 36, let's say 35, and if we represent this value in binary terms, the binary representation looks like And notice that the first one that we encountered on our original input, the one value lesser than that has the exact opposite in terms of number of ones up until this point. That if we do a AND operation between these two values, the value we would get is like this. So notice that this one has already disappeared in the AND result of these two values. And if we repeat the same process, so now this value that we got in binary, the value is actually 32. And again, if we repeat this same operation, that we do an AND between the number by itself with one value lesser than that, we would gain a result like so. First, let's represent the value number 31 in binary. And now if we do an AND operation between these two values, the answer we would get is all zeros, which exactly means that we would only run the loop the number of times one we have in our original given input. Because over here we only had 2 1 in the input. So during the first iteration of our loop, we got rid of this first one and we can see it over here. And during the second AND operation, we got rid of the second one as well and we got the answer as all zeros. So at the beginning, if we create a variable count and we originally set it up to 0, and every time in the given loop, if we just go through the loop and the value of the value of current n is not equal to 0, we just simply increase the value of count to 1. So which means that during this first iteration the value of count would be 1, and during the second iteration the value of count would be 2. And after that we found that the value of n is actually equal to 0. So we can simply break out of the loop, and when we break out of the loop, we would return whatever the value of count we had found. And in this case, the value of count we found is actually 2. And this solution would work perfectly fine, and this would be our optimal solution. The time complexity for this solution is also big O of 1, which is a constant time. But the thing is, the number of loop iterations that we have to go through would only be equivalent to whatever the value of 1 we are given in the original input array, and we don't have to run the loop 32 times like the previous solution. So we are actually in our constant time solution, we are also saving a lot of time, and this would be the fastest solution we can reach into. And in terms of space complexity, we are not using any additional space, so complexity would also be constant time. And now let's move on to coding. Thank you.
So first of all, we will create a variable for count and set it up to 0. Now we simply run a loop. We will run this loop till the number is not equal to 0. And with every iteration, we will increase the value of count, and we will simply do n equal to n and n minus 1. At the end of the loop, we just return count. Looks like our solution is working. Let's try to submit the code. And yeah, submission works as expected. It's pretty efficient and neat. And let me know what do you think about this video. And if you have any more suggestions, feel free to reach out to me in the comments, and I can address them. Thank you. Bye bye.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to work upon a lead code easy problem, counting bits, which in my opinion should be a lead code medium problem. Let's understand the problem statement. So basically we are given an integer n as input, and we need to return an array such that it defines that for every single value from the range of 0 all the way to whatever given n is, how many times the value 1 is repeated in its binary formation. So let's try to understand this with an example. Suppose our given input is 3. So the range from 0 to n would be 0, 1, 2, 3. And if we represent these values in binary, the representation would look like 0, 0, 1, 1, 0, 1, 1. And we need to return an answer array such which is of n plus 1 size, such that it represents that for every single value from 0 to n, how many times this bit 1 is being repeated. So now for the 0th position, we don't have any ones, so we enter the value 0. For the first position, we have one bit, so we enter as 1. Same goes for the second value, so we again add 1. And for the third value, we have two ones, so in the answer we provide as 2. And this would be our array that we would return as our answer. So let's see what are the different approaches we can take. So the first approach we can take over here is of one of the previous lead code questions that we have already solved, a number of 1 bits. And let me give you an overview of the solution we had achieved previously. So if we are given any number n is equal to 5, and if we represent it in binary, it becomes 101. And if we want to find that how many number of 1 exist in the given input, we would simply do an AND operation between the number and its one value lesser than the number of itself. So one value lesser over here would be 4, and if we represent it in binary, it becomes like this. And if we do an AND operation between these two values, the answer we get is 0, 0, 1. And this would be our first iteration. Now we would repeat the same process. So now again the number we found after doing this AND is 4, and we would do an AND operation with one value lesser than 4. So 3 would become 0, 1, 1. And if we do an AND operation between these two values, the answer we get is 0, 0, 0. And the moment we get 0 answer, we break out of the loop. And at the beginning of our loop, we would create a variable count, and only initially it would be set up to 0, and with every iteration we would increase the value of count. So during this iteration the value of count would become 1, and during this iteration the value of count would become 2, and at the end when we find that the number is actually 0, we would return whatever value of count we found as the number of ones that exist in our given input. So we found that in our given input 5, it has two number of ones. We can repeat the same formula for the given input, and let me show you how we can do it. Suppose the input we are given n is equal to 4. We need to create an array from 0 to 4, and we need to calculate that for every single value how many number of ones are present in that given input. So the answer array would be, we would need to provide that how many number of ones exist. So we can create a function called count1, and for and we can run a loop over all these values, and every single time we would pass on whatever the current value we are trying to find the count for. And whenever we run this function that uses this logic, the one that we just discussed, then we would be able to find that how many number of 1 exist for every single given element. And when we get the answer back, we can just simply fill in our array and return this as answer. This solution would work perfectly fine, and the time complexity for this solution would be n, because we will have to run a loop towards the entire towards all the given values. and we for every single value we would have to run this operation, count the number of ones, and this loop runs for the time being of number of ones that exist in any given input. So over here for number 5 there exists two ones, so we will have to run the loop twice. Suppose if we are given any n is equal to like this, then the loop will run 6 times. So we can say that this solution basically works in the time complexity of big O of n times log n, because in order to find this count, because in order to find number of ones, we would have to run multiple loop, we will have to run multiple iterations in this count one solution. So this is in itself a pretty efficient solution, but we need to see that if we can find a better approach and can we have an optimal solution. We can have optimal solution, and let me show you how we can achieve that. Now, in order to find the optimal solution, first let's try to understand that how the logic actually works if we want to find the number of ones in any given element. So the operation we are doing is basically we take n and n minus 1, and then we do a counter plus plus. We can represent it in a different manner. So first let's try to understand that suppose n is equal to 9. The actual calculation we are doing is n minus 1. We are doing an AND. So basically this means that after the AND operation we get the value as, and the value this comes up as 8, and we do an a plus 1. So keeping this in mind, and again if we do it for the value number 8, what we are actually going to do is we are going to, now our n is 8, so we will do n minus 1 as 7, and the answer is 0. So basically our n is 0 at this moment, and we again do plus 1 in our counter. So if we write this in other way, we can write it as that answer for the number 9 is actually whatever the answer we found for 9 and 8 plus 1. And if we go down one step further, the answer for actually this 9 and 8 is actually the answer for whatever the value of 8 we found plus 1. We can write this exact same formation as this. And if we try to calculate the value for this a of 8, actually we can write it as a of 8 and 7 plus 1 for this particular value. And this actually becomes a of 0 plus 1. And we know that a of 0 is actually 0, plus 1 is 1, and this 1 is actually the value of a of 8. Now, if we replace this a of 8 over here, we can say that the a of 9 is actually a of 9 and 8 plus 1, and we know that the value of a of 9 and 8 is actually a of 8 plus 1, and we know that the value of a of 8 is actually this 1. So we can say 1 plus 1, and we can come to the conclusion that the number of ones present in value number 9 is actually 2, and which is what we are given over here, and which is what we know. And basically what we have done is we have taken this input for any single individual element, and we have actually computed the results, we have actually stored the results, and based on those results we are able to find the future values. And basically we are applying dynamic programming. We can simply calculate the solution for our entire array in just big O of n time. Let's take another example to make things more clear. Suppose our given input is equal to 6. So if we want to find the answer for 6 using the logic we found over here, we can consider this as answer for whatever we find for 6 and 5 plus 1, and the answer for 6 and 5 is actually this equals to 4. So we can write this as answer for whatever the value of 4 we got plus 1, because this turns out to be 4. And subsequently, if we calculate the value for 4, we can break it down further as, so we can write this as answer for 4 and 3 plus 1 for this portion and plus 1 for this one. The answer for 4 and 3 is actually n is equal to 0. So we get answer of 0 plus 1 plus 1. This would be our final answer for our answer for value number 6. So see over here that we have, when we get to value number 6, we would have already calculated all the values from 0 to 5. And since we have the answer for from 0 to 5, we will use those answers to quickly determine the answer for value number 6. And this logic enables us to get our solution in just single iteration, and this would be a better time complexity than our previously suggested algorithm. And in terms of space complexity, anyways, we have to create an answer array in order to return it as a part of the answer, because it is given as requirement uh, for the given input, that we are not using any additional space, and we can just use the same array to represent the answer and also use it as our dynamic programming solution. So space complexity would also be a big O of 1. And this is a really ideal approach. And let's move on towards the coding.
So first of all, we will create an answer array and we would give it the size of n plus 1. And now we initialize the answer array of 0th value to 0. And now we just need to run a for loop. We'll start the loop from I is equal to 1 because we already calculated the value for 0. And we will run it while I is less than or equal to n. And we just have to write one line of solution, that if our answer of current I is actually equal to answer of I and I minus 1, and whatever the result of this is, we just add 1 to it, and yeah, basically after the loop we should have our answer array completely filled up and we can simply return it. So let's try to run our code. Oh, we forgot to initialize the value. Yeah, looks like our solution is working. Let's submit this. Our submission works pretty fast compared to a lot of other submissions, and as we can see that this is just a couple of lines of code that is really doing the trick. So though this is really simple to see, but in order to come up to this answer requires very strong knowledge of dynamic programming. Hope you like the explanation and the videos. Let me know if you want me to do anything else with the videos, or provide me any suggestions on how can I improve.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to work upon a lead code easy problem, missing number, and let's understand the problem statement. basically we are given an array of numbers containing n distinct numbers in the range of 0 to n, and we need to return that there is one number that is missing, and we need to return the missing number. So if we take the first example, the range we are given is 0, 1, 2 and 3, but when we see the actual input of nums, in the input we only have 3, 0 and 1. That if we start cancelling out the numbers that are present in nums and also present in our given range, 0 can be cancelled out, 1 can be cancelled out, and 3 also can be cancelled out. But the value number 2 is present in our range but not in the given input. So we would simply return the value 2 as not being present, and 2 being the missing number. So there can be multiple approaches on how we can solve this problem. Okay, and we would try to keep in mind with this follow-up as well, and we will try to solve this problem in big O of 1 space complexity and big O of n runtime complexity. So the first two trivial approaches we have in our mind is first one, that if we sort the input array, we can clearly we can solve this problem easily. But the issue with the sorting approach would be that the runtime complexity would be n log n, because we need to do sorting first, and that takes n log n time. Second approach is to use a hash set, and we would keep on storing all the values of nums input in the hash set, and then we would iterate with the range loop and go over hash set to see if the value exists in the hash set of not, or not, and eventually we would find a value that exists in range but does not exist in hash set, and that would be our solution. And the good thing about hash set approach is that runtime complexity would be big O of n, and but the issue comes for the space complexity, and the space complexity for this approach would also be big O of n, which is not what we want. So let's see what would be the optimal solution, and I would be showing two optimal solutions in this coding problem. So our first optimal approach is actually pretty simple. Basically, we are given two items. First one is range, that is from 0 all the way up to n. And second one is nums input array, where the values are 0 all the way up to n, but one of the value is missing, and we need to find this missing value. So the most simple approach to do is we run a for loop on this range parameter, and for every single value in the given input from 0 all the way up to n, we simply do an addition of all the values. We store the result of all the elements in the range in a parameter called range sum, and we would find some value over here. And again, we repeat the same process, but this time for nums. So we do the sum of all the elements in the num with another for loop. We store the result of sum in a new parameter called num sum. You can put any name. This is just randomly something for taking the name. And then when we do a difference between range sum and this number sum, the difference would actually be the missing number. And this way we would be able to find the solution pretty quickly. Let's take it by a quick example. So clearly we can see that this value 1 is missing. So the sum of all the elements over here would be 10, and the sum of all the elements over here would be 9. So if we simply do 10 minus 9, we would find the value 1, which is the missing number. And this solution is pretty simple to do, and the time complexity would be big O of n, because we are just simply running two for loops separately. So we are not doing much work in terms of time complexity. And for the space complexity, other than storing the value for just couple of parameters, we are not consuming any additional space. So the space complexity would be constant. And this is an optimal approach that we are asked as a follow-up in our original input. For the second optimal solution, we are going to use bit manipulation. And specifically, we are going to use XOR operator. So if you don't know what XOR operator is, let me give you a quick tutorial on what each value is being represented when it gets XORed with some other value. We can only have four possible values for A and B because all the values in computer system are represented as binaries. Now in the XOR, if both values are 0, we consider the value as 0. If any one value is 1, we consider the A XOR B as 1. Same goes for this one. And if both values are 1, we again consider A XOR B as 0. Now, let's see that using this logic, how can we find the missing number? So, now consider this property that for any given value n, if we XOR n with itself, the answer we would get is actually 0. And let me show you what I mean by that. Suppose our current n is actually 6. And now let's represent this in binary. And now let's try to do n XOR n. And this is the symbol for XOR in in programming language. So if we do the result, uh, 0 0 is 0, 1 1 is 0, and 1 1 is again 0. So if we XOR two values together, the answer we get is actually 0. But if we XOR, so suppose if we XOR the values like 6, XOR 6, XOR 3, the answer we would get is actually the value by itself. So because 6 XOR 6 would be 0. And now let's try to XOR 3 with this given 0. So the binary representation for 3 is equal to 0 1 1. And now when we try to XOR these two values, 0 and 3, the answer we would get is 0 1 1, which again means 3, the number that we XORed 0 with. And we also notice one more additional property over here, that whenever we XOR two values, so 6 XOR 6 XOR 3 gives the result as 3. Also, if we change the order and if we put any order like 3 XOR 6 XOR 6, this will also result in 3. And if we do like 6 XOR 3 XOR 6, this will also result in the value 3. Because order doesn't matter. If we are XORing two values by itself, both are going to eliminate themselves and their answer would be 0. So whatever is remaining would be the answer of this one. And we can repeat this for whatever number of times you want. So we can, if we do something like 2 XOR 3 XOR 2 XOR 6 XOR 6 XOR 7 XOR 7. If we run this entire thing, still the answer after this would be 3, because notice that over here 2 cancels itself, 6 cancels itself, and 7 cancels itself, and only 3 is going to be remained. So now since we have established all of this, let's try to see that how can this be useful for us in this given problem. The input for our given problem is actually we are given range and we are given the input number. So suppose for an example, the range we have is 0 to 4. So 0, 1, 2, 3. Let's consider 0 to 3. And the input parameters we have is suppose 1, 3, and 0. So notice that number 2 is missing. Now, if we were to use this XOR logic, that if we XOR all the values in the range with all the values in the nums, we would get something like this: 0 XOR 1 XOR 2 XOR 3 for this range portion. And if we XOR this with the nums input, we will get 1 XOR 3 XOR 0. And if we combine both of these, basically all the values that are same would be eliminated and would be turned to 0. So this 0 would cancel out this 0, this 1 would cancel out this 1, and this 3 would cancel out this 3. And notice that right over here we just determine that the order in which XOR happens does not matter. Everything is not right next to each other, still they will cancel out each other, and at the end we are only going to be remained with the value that is not at all present in this nums input. So in the nums input we don't have the value number 2 present, so the result of range XOR nums would actually give us the value 2, and the result 2 we can simply return it, and this would be our solution. So this is a very neat, very unique solution, and because we have the knowledge of XOR, we are able to come up to this result. And if we use this in any interview, this clearly shows that you have very sound knowledge of computer concepts, and you know how to apply them when they seem fit. This would definitely give you a very sharp edge over all the other candidates. And let's do the complexity analysis. So for the time complexity, we are actually doing everything in just the single loop, for one loop for range and one loop for nums. So the time complexity would actually be big O of n, and the space complexity would actually be big O of 1, because we are not using any additional space. So this would be the most optimal solution, and this is what the problem is asking us to find. Now I showed two optimal solutions, but first optimal solution is very trivial to understand, so I'm not going to code it up, and I'm only going to code up this XOR solution.
So we will first of all create a variable XOR and we initialize it to 0. You can give any name, and now we will run a for loop starting from the range. So int I equal to 0 to I is less than or equal to nums dot length I plus plus, and every time we will XOR the number with itself. So now again we will run another loop, and this time we will run it for the given input array. Notice that we are only using I is less than number of length, and over here we are using less than or equal to, because in the range we have one value more than whatever the length of number is. And again we repeat the same operation, XOR with the value in the given input array. And now we will simply return whatever we found in XOR, that this would be our missing value. Let's try to run this code. Looks like our code is running. Let's try to submit it. And yeah, our solution works perfectly fine, and it's actually pretty fast and pretty efficient. And hope you like this video. I'll be posting the solution in the comments, and let me know if you have any suggestions for the videos. Yeah, let's clear FAANG together.
Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a LeetCode easy problem, reverse bits. And this has something to do with bit manipulation. So let's understand the problem statement. Basically, we are given a 32-bit unsigned integer and we need to reverse all the bits in it. Let's consider it by an example. Suppose the value we are given n is equal to 5, and if we represent it in binary, the binary representation would be, and since the given input is 32-bit, all the other bits would be 0. Now we just need to return a new element, reverse, that looks like the exact reversal of this binary value. So this so the rightmost bit on the original input would be the leftmost bit on our new variable. So the value should look like 1, 0, 1, and all the remaining zeros, because this one is also 32-bit. So basically the rightmost zero would be at leftmost position in our new variable, and we need to return this. The problem statement is really easy to understand, and let's see that what could be the approaches we can take to solve this. In order to solve this problem, we are going to use bit manipulation, and specifically we are going to use two bit manipulation operators. First one is AND operator, and second one is OR operator. And let me show you by truth table what each of these operations represent, and these are the symbols to represent them. So the possible value for A and B we could have is, so for A and B, if both the values are 1, then only we consider A and B as 1. Otherwise, if there exists a single 0, we will keep their value as 0. So this would be the table for A and B. And in A or B, if there exists a single 1, we would consider the value for A or B to be 1. So if both are 0, then only we would have A or B as 0. Otherwise, the value would always be 1. Now let me show you that how can, using these two operators, we can calculate our solution. We are only given one thing over here, the input parameter n. And suppose our n is 5, so the values would be like this. The new variable that we are trying to determine, reverse, is actually unknown to us, and that will have all the values that are in reverse order for the given n. And we know one thing, that all the values in given n is actually 32 bits, not more than that. So the first intuition is that if we run a loop 32 times, and every single time we take whatever element is present in n, and if we put it in our reverse variable, so whatever element we have present in our n, we put it in the reverse variable, and then we start shifting the reverse variable one step to the left side. So at the end of the loop, our reverse variable would be exact reverse of whatever value that is present in the given n. So let's determine that what would be our algorithm. Initial value for our reverse parameter would be 0. So the entire value would be, and when I say 0, I mean that all the 32 bits would be 0 for the reverse element. Now, at the beginning of, and we would run a loop from I equals to 0 to I equals to 32. And at the beginning of our loop, we would have a condition that every time we are going to left shift the value of reverse parameter to 1 bit. So at the end, we would have rotated any value that is present over here, we would have rotated it to 32 times, and it would end up on the leftmost position. After the rotation of the value, so first of all, so inside the loop, first of all, we will rotate 1 bit to the left, and we would represent it with this symbol. Next, what we are going to do is, somehow we will have to get whatever value of n is present. We need to copy that value for that particular element and somehow put it on the subsequent position. at our reverse order. So how can we do it? And we know based on our and or operators. So at any given moment, the possible value for n would be either 0 or 1. And we want to copy whatever value of n exists in our reverse parameter, a reverse variable. So if we do an n and one operation, then this would specify and this would provide us with whatever value of n there exists. So suppose if the value of n exists as 0, and if we do an AND operation with 0 and 1, the result we would get is 0. If the value of n exists as 1, and if we do an operation 1 and 1, the value we would get is 1. So this is how we can get the exact value of 1 that is present, exact value of n that is present. And once we calculate this value, that n and 1, we need to put this value in our reverse variable. But the thing is, in our reverse variable, all the values are initially set it up to 0. So all the values are 0, and the potential value of n and 1 operation could be either 0 or it could be 1. And whatever we get over here, we need to transfer it to our reverse variable. And the way we can do it is if we simply do whatever element is present at our reverse variable, and if we do an OR operation with whatever the answer we get from n and 1, we would be able to put the exact value that was present at n at any given moment. So the operation that we are going to do is current value of reverse we have with, and we would be ORing that with n and 1. And suppose initially, so if the value of n is equal to 0, the answer after this operation would become 0, and we know that the value of reverse is initially set to 0. So we would be doing 0 or 0, and the answer we would get is 0, and we would shift it to our reverse. And at every single iteration, we are going to do a left shift on the reverse parameter. So whatever value we set up at the first, at the end of the 32 iterations, it would end up over here. And so we are taking care of the value of reverse parameter by shifting them one parameter left. But we also need to shift the values of given n one parameter, one bit to the right side, because we need to calculate every single value of n. So suppose the value of n is like 0, 1, and then bunch of zeros, and then 1. And this comes out to be the whole 32 bits. We need to calculate every single value of n that is present, and we need to put it in the reverse order. So at the beginning of our loop, we will calculate this value. We would put it in our reverse loop, and once that is done, this value would be stored over here initially in our reverse variable. But we know that we are doing a left shift operation on our reverse variable. So eventually the value will keep on transporting on the left side, and it would end up at the first position, which is what we want. But the thing is, on the n way, on the given input, we need to do a right shift operation. So we keep on eliminating the values that we have already calculated, and we are eventually, when we come to the end of the 32nd bit, we would come to this value. So 31st bit would become this value, and this value would be entered at the second position, reverse variable. So I hope this makes things clear. I know it's a little bit tricky to understand, but once you will do an example by yourself with this expression, that reverse, the value of reverse is actually the reverse we currently have, or n and 1. And after this, we would be able to copy whatever value of n we have to our reverse for that particular bit. And then it's just a matter of shifting the values of reverse on the left side and shifting the value of n on the right side. And at the end of the loop, we can simply return the value of reverse variable, and this would be our answer. So now let's calculate the time complexity for this approach. Basically, the time complexity would be big O of 1, because the only work we need to do is we need to run a for loop for 32 times, and that can be done in constant time. And even for the space complexity, we can complete the entire iteration in just constant time, because we are not using any additional data, we are just using couple of parameters to store some values. And this would be a very fast solution, and it's really simple to understand. But the thing is, we need to come up with a little bit of logic, and we need to have a little bit of understanding of the bit manipulation operators. And now let's move on to coding. So first of all, we will create a variable reverse and initialize it to 0. Now we will run a for loop. Inside the for loop, we will first of all do a left shift on reverse. Then we will apply our logic to calculate the value of n to reverse. So we will do reverse or with n and 1. And now we just do a right shift 1 bit for the variable n. And at the end of and after the loop, we simply return the value of reverse. Let's try to run this code. Yeah, looks like our solution is working. Let's try to submit it. And yeah, our submission works actually 100% faster than all the other submissions, but this is not true. This is because the solution runs in the constant time. And hope you like the video. Let me know what kind of videos you want me to do next, and if you have any suggestions regarding my videos, feel free to let me know so I can improve upon them. Our aim is to clear the FAANG, and we are not going to stop till we clear FAANG interviews. Thank you. Bye.